All right, folks, this is day 3 of RSS. Please start taking a seat. We are going to start very soon. Very quick announcements before we start. So, first of all, yesterday I mentioned that we are going to have plenty of food for dinner. Apparently, I lied. I don't know. We're going to have even more food tonight. So hopefully, we're slowly going to fix, the dinner part. And that's announcement number 1. Announcement number 2, I heard people mentioning limited restroom options during the lunch break and the dinner break. We're going to make an announcement right before lunch about where the restrooms are, around here, because the auditorium is going to be locked during lunchtime. I think that's the main issue. With that, we're going to pass it to our session chairs for the first session, which is HRI.
Good morning, everybody. We'll be your session chairs for HRI this morning. Thank you for being here bright and early. I'm Jonathan Bisk from Carnegie Mellon, and
So Tong-hee Lee from TU Vienna.
we have 14 papers, and without further ado, we will welcome our first Morpheus, a neural-driven anamorphic face with hybrid actuation and diverse emotion control, presented by Zhongjiang Zhang.
Hi everyone, I'm Zongjing Zhang from Tsinghua University, and I'm very excited to introduce our work, Morpheus, a neural-driven animatronic system with hybrid actuation and diverse emotion control in human-robot interaction. So as human-robot interaction becomes increasingly important in fields like the healthcare, education, and entertainment, emotion expression remains a key challenge. While language understanding and computer vision grows rapidly, most robots still lack the facial expressiveness needed to truly connect with users. So both rigid and tendon-driven facial mechanisms have limitations. Rigid drive offers precision but struggle with reproduce complex macro expressions. And the tendon-driven designs allow more flexible motion, but their control is less stable. So these limitations motivate us to design a hybrid actuate system with neural control for realistic expressive face. So our system consists of 3 key modules. First, the emotion facial animation module takes audio input and extracts content and emotion features. These are used to predict a sequence of blend shape coefficients, which shape virtual facial expressions. Next, the face inverse learning module turns these blend shapes coefficients to the actuator control signals. And finally, the mechanical face platform executes these signals to generate synchronized lifelike facial expressions in the real world. So our face uses 33 actuators, 29 for rigid and 4 for tendon-driven, like our nose and cheek areas. The eyebrow module has 4 actuators to express emotions like surprise and anger. The eye module has 6 actuators, and the mouth module with 16 actuators enables complex lip motions, and the neck module adds 3 actuators for head turning, shaking, and nodding. Our software has 2 parts. First, the emotional facial animation module presents speech with 2 encoders, 1 for content and 1 for emotion. And we also apply the dynamic time wrapping loss to align audio features with the same content is spoken with different emotional tones. These aligned features are fused and passed to a transformer decoder with emotion-guided attention to predict a sequence of blend shape coefficients. And in our face inverse learning module maps the coefficients to actuator commands using an MLP network. We use MediaPath to detect 2D landmark between our facial and virtual faces and apply an R1 loss between them. These self-supervised loss allow us to backpropagate the gradients and without manual labels. Here are show 25 representative expressions from sad, happy to some subtle ones like skeptical and shy. And on the right is the demos with look at the sky with 4 emotions.
Look at the sky. Look at the sky. Look at the sky. Look at the sky.
Here are more visualizations showing how our system generates expressive face across different sentences and emotions in both virtual and real faces. We evaluated our system in 2 ways. The top table shows the quantitative results in using the RV and EV metrics. The RV metric is to measure the lip sync accuracy, while EV evaluates emotional expressiveness in regions like the eyes and our forehead. And our method performs all baselines on both 2 datasets, while with the lowest LV and EV, confirming that we achieve both accurate form, movement, and non-state motion expressions. The bottom confusion matrix will result from a facial recognition with high accuracy for happy and angry expressions. That's all. Thank you.
We have some time for questions. Oh, sorry, I couldn't see in the back right of the ground floor. Thank you.
Thanks for the great presentation. So one of the questions I have is that when your face interacts with a human being, does it actually predict the human's emotion and then therefore respond to it? And if you do that, then what is the amount of time it takes to do that prediction of the human face?
Yeah, that's a good question, and we solved that in our Morpheus version 2. And in this version, we only use the emotional sentence to produce the signal comment. But there are some techniques like the flow matching to reduce the time reduce the time and probably that's okay. And the latency we measure is probably 300 ms, and I think that's okay.
Thank you.
Yeah, unfortunately, we won't be able to sneak in another one. But sorry about that. So we'll move on to our next speaker. But thank you very much.
Thanks.
Yes, next talk is interface level intent inference for environment agnostic robot teleoperation assistance and presented by Larissa Roque.
Sorry, hi. Hi everyone, I'm Larissa. I'm a fifth-year PhD student at Northwestern University, and today I'm presenting interface-level intent inference for environment-agnostic robot teleoperation assistance. So teleoperating assistive robots is challenging because accessible control interfaces are often limited in dimensionality and continuity due to physical actuation needs. While joysticks allow continuous multi-degrees of freedom control, interfaces like the sip and puff are single-dimensional and used discretely. To bridge this dimension mismatch, control actions are mapped to robot commands through modal control maps, and users need to switch modes to access different robot functions. The greater this mismatch, the more complex and mentally demanding the control becomes. On top of learning a complex map, users must also actuate the interface precisely. And for the 1D sip and puff, which we use in this work, this means inhalation or exhalation into a straw at different strengths. This breath pressure signal, which is the blue line in this plot, is then interpreted as one of 4 interface actions. So we have hard puff, hard sip, soft puff, and soft sip. This is not easy in practice. In this example, we see cases where interface actions are misinterpreted by the standard interface map, showing that measured input often diverges from user intent. This motivates the need for modeling user intent at the interface level. Standard teleoperation models that ignore these deviations between measured user input and user intent are insufficient, and we instead adopt an interface-aware approach. Prior work on interface awareness modeled the user's interface input and control mapping model noise via histogram binning, but assumed a known human policy. While this is feasible in simulation, it is difficult to define the human policy in real-world task-agnostic settings, and thus previous hardware work assumed a safe policy to estimate intended robot actions. Our approach augments the interface-aware teleoperation model to address these limitations. We first assume that suboptimal internal models, H, may be addressed through adequate training and user interface adaptations, and so we focus on modeling the user input distortion model, F inverse, and we explicitly represent this as a mapping from raw interface signal to interface actions. Using the raw signals lets us account for temporal dynamics in the interface signal time series, and we also consider the previous executed interface action in order to model interface use during consecutive actions. We use a network of gated recurrent units to learn this user-specific mapping from raw inputs to the current intended interface action. We implemented this in an assisted teleoperation framework and conducted a user study with 8 participants with spinal cord injury. Participants were first trained to issue the 4 sip and puff interface actions through a screen-based training task. After this, using the same task but without the feedback of the pressure signal, we collected data to train the personalized interface-aware model. During this model training, participants then learned the control mapping from sip and puff actions to robot actions, where they have access to the robot control mode display and can practice using the robot arm. And finally, they completed a complex pick-and-place task under 4 different teleoperation conditions. For all participants, we see that the interface-aware map significantly improved mapping accuracy. In particular, the interface-aware map made no confident wrong predictions, which makes it very reliable for runtime use. In the ADL task, both versions of the interface-aware map condition, with and without environment-aware safety-based assistance, reduced collisions compared to the standard mapping. And finally, we also found that users prefer our method as they reported lower mental workload, and among those who noticed assistance, the map without safety-based assistance was rated as the most preferred. So in summary, we contribute an interface-aware teleoperation framework that requires no access to the human policy or environment information, a data-driven modeling method that captures real-world interface use, and we evaluate our method in a user study which showed that our interface-aware map outperforms standard teleoperation mappings and is most preferred by users. Thank you. So the poster number is wrong because it got changed. So we are at poster 4, if you're interested.
So we have time for some question. Yeah, but yeah.
Thank you for the nice presentation. Do you think there's any way to extend your NICE method to have multidimensional input? For example, to do more complex motions, to allow the user like a greater variety, a greater expressiveness of robot motion?
Yeah, I think so, because our method specifically focuses on the interface only, and from my interpretation, I think what you're saying is the map between the interface action to the robot command. So because the method is so modular, our method focuses on the interface signal interpretation, and then we can change out the map. And I think, like I showed earlier in my slide, we say that that internal map that people have of the robot control can be addressed through adaptation specific to the user. So if we can have a map that is like macros that does like specific motions, pre-programmed motions, I think that's also possible. Yeah.
Do you have more questions? Was it the back side or no? Okay, I would ask a very quick question. It's very short maybe. We have time, very little left. So how would you do the training of your model in order to be more personalized, or is it general? How much, can you talk about this training data, model, and then personalization?
Okay. So we designed a training task that specifically tries to mimic what interface use is like when people are actually operating a robot, which is why we have like a series of 3 prompts, which is an improvement from what we did before, which is like a single action. And by collecting that, we're able to get basically a window of actions that people do. And we collect this for every participant, and we train a network for every single participant. So everyone's using like a personalized map.
Okay, yeah, thank you very much. Let's next speaker.
Thank you.
Next, making his first of more than one appearance on the stage is Pablo Gonzalez Oliveras, who will be presenting Sense and Sensibility, what makes a social robot convincing to high school students.
Hi. Okay, sense in our study is critical judgment, and sensibility is responsiveness to confident behavior. So robots today can definitely support learning, but the social influence that they can exert can backfire due to the errors that they can commit and the certainty cues that they display. So to what extent this influence has been happening, if at all? How much is it driven by sense to errors or sensibility to certainty of the robot? So we explored these two dimensions in a realistic HRI, where the is academically relevant for the students. So our design had 4 phases. In the first one, we manipulated the robot Ferhat to obtain 3 certainty modes, manipulating the visual cues with different gestures, different semantics, different speech cues like speech rate or different pauses. And we also conducted a pre-study with the students before the experiment to conduct an item response theory analysis that allows us to get question difficulty, student ability, and above all, the probability of correctness per question and student. So with this analysis, we selected 8 questions symmetrically, 3 levels of difficulty, 2 manipulations in 3 different groups. The first manipulation was on certainty, so you see the red questions in 3 and 7 that the robot was wrong, and the green questions, where the robot was different levels of certainty. So the 40 students through and through the same 8 questions, the same cycle. In the first part of the cycle, the students were exposed to a question, reflected in silence, decided an answer, preliminary answer registered. The robot then revealed the answer, and they started to discuss 4 arguments of the robot. The student decided what to change it or not in the final answer. So how would you measure this influence, right? So one intuitive way would be to count alignments and get a heat map, put 40 columns, 8 questions, count the dissents on the preliminary answer. We counted 139 dissents in the preliminary answer. The answer didn't match, right? And then we counted what happens in the final answer. 117, the students align with the robot. So there's a strong signal for 84% of rate alignment. However, is there a better way to answer this question? So, for example, how likely is that the students would have reached those final answers on their own, without the robot? So we used the probability of correctness in the RRT analysis to calculate how far from expectations they were in the preliminary answer and the final answer and compare. So we found that in the preliminary answer, 5 students got beyond the expectations, their own expectations, and then in the final answer, they reached 75% after the influence of the robot. That's a more realistic way to measure this. What you see here is the alignment question difficulty correlation. We didn't get surprised by this. We did expect the harder the questions, the more doubts, the more alignment with the robot. However, if you see the reception, the robot was wrong. So the students faced 4 wrong arguments, and they didn't resist what we expected. In terms of certainty levels, we do find differences in the certainty levels, and the more certain the robot, the more alignment we saw. But the striking figure here is that even in uncertainty, the students were over the top with rate alignment. So our key takeaways for you is like 75% of students perform beyond their expected capacity due to the direct influence of the robot. Robot confidence shapes student alignment even when they're wrong, so that means much sensibility to errors. And students fail to resist their robot flawed arguments, even on easy questions. That means little sense. So I leave it here. If Thank you very much.
Questions? We have one in the back here,
Yes.
the center.
I'm a bit deaf, so
I will speak loud then. Can you hear me?
yes.
Okay. Thank you for the great talk. My question was that, did you randomize the order of the questions for the students? So I could expect if I were a student and the robot, gave a correct answer on a medium question, right? A question I thought was kind of hard, then I would be prone to kind of trust the robot more, right? And if on the simple question, its answer was actually different from mine, I might doubt myself and be like, oh, well, it did well on a medium question, right, or a hard question.
I didn't get the last part.
So, right, if I wonder if the order of
that's
the questions mattered, if the robot got a correct answer on a medium or a hard question, then that would influence the students to trust it more.
Got it. No. It was all script, in the sense that it didn't need to be randomized. On the opposite, it's the other way. This study was 4 questions symmetrically mirrored in the second part. They went through exactly the same. All of the groups were exactly the same script in order to find out not only these 2 dimensions, but also how carryover effect had. I can explain more in the poster, but it's not only that we repeated the same, to know if that had an effect by having aligned with the robot at the beginning, that has an effect later, maybe, or there were uncertainty first. So it was all thought out before. It's not random. It's the opposite.
We'll continue this at the poster session, but thank you very much.
Yeah. Thank you.
So next work is Feast, a flexible mealtime assistance system tackling in the wild scenarios, and presented by Raja Kumar.
Hey everyone. We present Feast, a flexible mealtime assistance system that can be personalized in the wild by end users and deployed in various contexts with minimal researcher intervention. We developed Feast using community-based participatory research in collaboration with 2 care recipients, Amy, who has multiple sclerosis, and Benjamin, who has a spinal cord injury. We evaluate Feast in a 5-day in-home study, during which they successfully feed themselves 6 meals in 3 diverse contexts. To better understand personalization and mealtime assistance, we begin with a formative study with 21 care recipients. We use speculative videos to guide in-depth conversations, and the study yields 2 outcomes. The first is 3 key tenets for in-the-wild personalization: adaptability, transparency, and safety. The second is a collection of personalization requirements for mealtime assistance. Our paper outlines 46 distinct personalization requirements grouped into various categories. Motivated by this, Feast uses modular and user-personalizable hardware. At its core is a feeding utensil with motorized wrist-like joints that enables various food manipulation skills, such as curing and dipping, and bite transfer, either outside mouth or directly inside mouth. Our system can also pick up drinks using an adaptive handle that attaches to the user's mug, and also assist with mouth wiping. Feast offers multiple interaction interfaces, including voice, LEDs, physical buttons, a web interface, and personalized gestures that can be generated on the fly. Feast skills are encoded via parameterized behavior trees. For adaptability, it processes user requests in natural language and uses a large language model to translate them into structured behavior tree updates that can be statically validated for safety. This structured representation can also be analyzed by a large language model to process user transparency requests and form transparency responses. All of this enables Feast to address the 3 tenets of in-the-wild personalization. For adaptability, we show that our system can meet 36 of the 46 adaptability requirements, which is significantly more than baselines. For transparency, it tackles levels 1 to 5 of the IEEE transparency standard, which includes answering user-initiated queries and providing continuous explanations of what it is doing. For safety, Feast is designed in accordance with an ISO standard for personal care robots. It features multiple safety measures, such as monitoring all perception outputs, tracking forces on the fork, detecting collisions using joint force torque sensors, switching to compliant control during transfers, and providing emergency stops accessible to both users and researchers. And if all else fails, our feeding utensil includes a mechanical weak point that is designed to brake under excessive force to ensure user safety. A 5-day in-home study teaches us 5 key lessons. First, we observe significant variability that highlights the need for in-the-wild personalization. For example, in a social setting, the robot occludes Amy's dining partner while at the default rest position. Thus, she asks it to move to a retract position between bites so that she can comfortably socialize during the meal. Second, transparency helps users understand the system and adapt to it. This is especially important when adaptability commands fail. Like in this example, where the system mistakenly applies a change meant for only SIPs to all tools, the user then asks clarifying questions and submits a more detailed adaptability request, which succeeds. Third, providing multiple interfaces is essential for transparency, as shown when Benjamin was stuck with the wiper near his mouth and couldn't check the web interface to recall what gesture the robot expected. He noted that a small display on the gripper could have helped. Fourth, user cognitive workload generally decreases with use, but Amy noted that it also depends on the context and the system settings users choose. Finally, unexpected failures arose in the wild, but users recovered by smartly leveraging system flexibility. For example, when transfer failed and the robot attempted to acquire another bite despite food still being on the fork, Amy switched to manual mode and sent it to stab an empty location on the plate so that she could retry bite transfer. Thank you.
Any questions? Oh, yeah, we have here in the middle, ground floor. Here, ground in the middle.
Great talk and great work. Wanted to ask, how many types of food can you cater to, like based on different categories? And like the way you showed the recovery failure, what kind of recovery failure would be there for, maybe there is a ramen which has multiple different kinds of food all together. Then how are you going to deal with all these food together in the same bowl for the long horizon food acquisition?
Thanks for your question. So for Feast, we specifically looked at food that can be manipulated with a fork. So we cannot like tackle finger food, for example, or like burgers, unless you cut them up into pieces. Feast does feature a wide variety of skills, so things like skewering, scooping, twirling, and even pre-acquisition skills when you need to like cut something, for example, or like group noodles together. I wouldn't say it can tackle all kinds of food items within this category because like the range of food items you come across is crazy. But it's reasonable enough for us to get food items from like the user's fridge, which we did during our study, heat it up, and have them eat it. For your second question, so the recovery behavior I showed, we have a manual mode for acquisition where the users can select the skill itself as well as the parameters. And this is essential when, let's say, like the outputs from our like learned models, maybe they are not predicting them correctly and the users want more control. So you could select like key points for twirling or key points for scooping and so on.
Thank you very much.
Thank you.
Next, we will have demonstrating a control framework for physical human-robot interaction toward industrial applications presented by Bastian Muraccioli.
Hi, good morning, everyone. So I'm Bastian Muraccioli, and today I want to present our work on how to develop a control framework for PHI toward industrial application. So let's begin by just a bit of context. The Industry 5.0 is reshaping how we think about robots, not just as a tool, but as a true coworker. To evolve from fence robot to responsible collaboration in industrial setting, we need to have inside the robot controllers safety guarantees. Human safety is an important factor, but there is also the trust in automation that is usually made by compliance in torque control. But more the compliance the robot is, it will make the robot safer but less repeatable. So for the productivity, the industry decided to widely use high-gain position control. That is, make the robot stiff and can be dangerous for shared workspace. So the main core challenge of this paper is to have a control architecture that is compliant, performance, and safe. So to embed safety in our framework, we are using quadratic programming in second order. This QP solver helps us to enforce safety and feasibility constraints such as collision avoidance, joint limits in position, velocity, and torque. And with this solver, we can also guarantee to have robustness near singularity scenario, thanks to a poster tag that is still maintained by the solver. So this is an overview of all our control framework that is open source and work at 1 kHz for the Kinova Gen 3. We are using the torque sensor of the Kinova and an additional FT sensor to have a precise external torque estimation that we're using for two things. First, to ensure the constraints, and secondly, to make the QP knowing the external force. And with that, we are using the explicit compliance principle that let us having compliance gain on each task of the robot. And another contribution of this paper is to have a new low-level control for the Kinova that we made us with a feed-forward component and also a feedback component made with rotor inertia, friction compensation identification that we made by us, and the inverse dynamic models. And then when we have the torque motor, we can convert it to current to control the robot. So we made several compliant control modes. The first one that you can see here is in the null space. We can have also full body compliance. We can check every parameter of the robot to adjust the compliance that we need for the industrial settings. And also we introduce a new implementation of the dual compliance that makes the robot stiff when you touch the poster, but compliant on the end effector when you interact with it. So it's really convenient to create some kinesthetic teaching behavior or to control the robot intuitively. And here is the result of our approach. We made a comparison with our new level torque control and the one from the manufacturer. And as you can see, we have less error in position and velocity than the manufacturers. We made also another comparative with the position control that was used in the industry. And as you can see, we have similar precision with smoother motion for the robot, which is also important. And we have the posture task that is compliant. So thank you, everyone. We have also a demo today, so please join at our booth. Especially for the conference, we made a kinesthetic teaching mode that you can play with. You can play with all the framework that I presented today. So thank you for your attention, and please, I would be happy to answer every question. Thank you.
Do we have any questions in the audience? If not, I get to ask one. But so maybe, if it's okay, I'll throw you. So one of the things that you discuss in the paper is this question about how much access you get to the internals of for example, the Kinova. And you talk about how it would be useful to have access to sort of all of the internal sort of control parameters there. And so I'm curious if you could speak a little bit about why, like what's missing basically, and if you were sort of designing this on a different system, how that would inform what you would do differently.
Yeah, so basically, the Kinova robot, especially, that we use as the robot manipulator for this demo, can have some problem in torque tracking, as you saw in the video. And these robots can be controlled directly by current. That's why we can make a new level torque control. So all of the way that we implement this torque control can be used by manufacturers for the newest robots that are equipped by torque sensor.
Thank you.
Thank you.
Thank you very well. I thank the speaker once again.
So our next talk, the co-authors of this paper couldn't make it, so we have a delegator to present this work. And the work is users and wizards in conversations, how the Wizard of the Oz interface choices define human-robot interaction, and will be presented by our third speaker of this session, Pablo.
Okay. Hello again. Yeah, so I'm here because Katarina and the authors cannot be here, so let's see. So Wizard of Oz is a very common methodology in HRI, especially useful for complex social interactions where autonomy is not perfect. So we, despite of being this common, it's not well explored, and so we are thinking and telling, do not discard wizard data. Yes, the role of wizard is demanding, it's proved to be error-prone, but if we can tone down these issues, it definitely contains a lot of potential data that can be used for social immersive interfaces or future automation. So, what we try to do is to use the classic button-based GUI for wizarding and compare it to the virtual reality immersion. What you see in the left is the headset of MetaQuest Pro that for virtual reality. So it includes face tracking. So that was the main reason we chose the Ferhat robot, that is capable of mimicking human expressions really well. So this headset allows the operator to be immersed right in the scene, just see through the robot's eyes. He has a stereo camera, and he captures all the head movements and the face expressions, can transmit back to the robot. So the design was 5 wizards, 5 different participants, 3 different wizard modes that they went through in different restrictions. So the first one was they saw a fixed video of the scene. They received the transcripts in text. They could play with the buttons and for predefined utterances or gestures. And the second one was the same, except that they had the audio as well. The VR, the key one, had the immersed video and the headset, the real audio, and the robot was mimicking all the expressions and all the utterances, even with the natural voice of the operator. Right. So what we expected is that the users would foster deeper engagement and more social connection in the scene, in the setting, and the wizards will provide a more intuitive control, more control. So what we can see now is some examples of real action. Whoa. Okay, so the results showed that the VR was by far the most preferred one by the users. It was the most fluent turn-taking flow of all, like less gaps, less overlapping. From the wizard point of view, well, we had to point out two aspects. One, they were feeling more socially connected with the participants, but on the other hand, they felt like the more demanding task. It's a double-sided. So it's like they felt like a more responsibility for the whole endeavor, the whole setting, participants, etc. So all in all, social immersion in wizard methodology is double-edged. On one hand, there are some phenomena that need to be explored further, but on the other hand, I think HRI community has an opportunity here to pursue two avenues. One, to pursue more natural and intuitive settings and interactions, and on the other hand, to pursue a more ambitious to advance in robot automation in the future. Thank you. 7 seconds.
Yeah, we're not gonna take questions here, but thank Pablo to present this on behalf of the authors. Thank you.
Thank you. No questions.
No more encores, but our next will be cross-modality force and language embeddings for natural human-robot communication, being presented by Carlos Velasquez.
Greetings, everyone. I'm Carl Velasquez, and today I'll be presenting our cross-modalities force and language embeddings for natural human-robot communication.
So kind of like you're wiping the table, and then I'm going to bring you back.
We can see from the video that the physical therapists from the observational study demonstrated how humans naturally coordinate verbal instructions, such as gently forward, with precise physical forces. And so far, commonly in HRI, robots interact with humans using only force. However, we believe the combination of force and language in HRI is advantageous for two reasons. One, forceful demonstration alone misses critical understanding and intent behind physical interactions. And two, verbal descriptions alone may not fully describe the physical interaction. And if we want robots to use both forces and language, we need a method for translation between force and language. Therefore, we ask ourselves, how can we bridge the gap between continuous force signals and discrete language to create a unified representation for more intuitive HRI? Now, onto our preliminaries. First, force. It's simply a series of 3D force vectors over time. You can see in the bottom left an example of the three components broken up over time. And intuitively, we can think of humans applying force in an overall direction, magnitude, and duration, which motivates us to develop a minimal viable vocabulary made of 18 direction words that describe overall force application direction, and 12 modifier words that describe overall force application magnitude and duration. And a phrase is simply defined as a direction word plus an optional modifier word, for example, down or sharply up and forward. And we can leverage SentenceBERT, a contextual large language model, to produce semantically meaningful continuous vector representations of entire phrases, which enable mathematical operations such as cosine similarity to judge how aligned two different phrases are. And finally, our cross-modality embedding itself, we aim to develop a framework that can model the shared representation of force and language as a shared latent space to align force profiles and phrases, which enables translations between modalities via encoding and decoding instances to and from the latent space. And a key property that we would like to have is corresponding forces and language are mapped distance-wise closer than non-corresponding. Now, this moves on to our method, the dual autoencoder model, which features two fully connected neural network autoencoders for each modality that is responsible for encoding and decoding instances to and from the shared latent space. And to train this model, we leverage multitask learning across 3 different cost functions to minimize: 1, reconstruction loss; 2, contrastive loss; and 3, translation loss. And this forces the model to perform well in multiple tasks instead of a single one, which encourages to learn a more robust cross-modality space representation and prevents overfitting. Now, I'd like to highlight specifically contrastive loss, which specifically aligns corresponding force profile and phrase embeddings similarly in the shared latent space by bringing them distance-wise closer and pushing away non-corresponding instances. And you can see from the conceptual figure that the on-diagonal elements of the distant matrix are minimized while off-diagonal are maximized. And to collect data, we had 10 volunteers come in and complete a total of 840 trials involving human demonstrations of force and language translation. Now, to evaluate, we decided to compare our method against multiple baselines. The first is a non-parametric approach, specifically the support vector machine and k-nearest neighbors. The second is just a basic multi-layer perceptron, which does not feature any shared lane space. And finally, the dual autoencoder our method. And across 3 different experiments, we were able to demonstrate that our method is capable of translating between force profiles and phrases. Our method outperforms in generalizing to examples outside of training, and using specifically expert embeddings enables even greater generalizability. And for some further results, here's some inference examples of going from arbitrary phrases to force profiles using our dual autoencoder of expert phrase representation. As you recall, we use minimal viable vocabulary phrases, which are just simply primitives, but we can use cosine similarities to map any arbitrary phrase input to the closest MVV phrase. And finally, our demo, the robot is given arbitrary verbal commands and it translates them into force profiles.
Okay, first, let's ease left slightly. Awesome. Now I want you to move up with great force. Okay, let's now try to move forward and down gradually this time.
And for more details, you can visit our website, and we'll be actually demoing that exact same demo out in the park behind, so please visit us during lunch and dinner. Thank you so much.
We have time for some questions from the audience. Right up here in the front.
Hey, thanks for the cool work. I have a quick question. Can you explain a little bit how do you deal with the temporal aspect, and if you have longer horizon like behavior, like act happy, like I don't know, like longer goals, how do you translate that into force profiles?
Of course, yeah. And so right now we simply, for the purposes of the demo, we can just simply have a 4-second window. However, we also experimented with versions where we actually append the time as one of the features that was fed into the model, and even that was able to show capabilities of demonstrating dynamic time horizon generation for force profiles. And then for longer horizon for actual phrases, this is further work where ideally using expert, which is a sentence transformer, should be able to take arbitrary inputs and still find the key words or essentially the key concepts that would be necessary to translate to force profiles.
If not, I get, oh, okay. No, you get it. I'll ask mine at the poster session. Right here.
Yeah, hi, awesome talk. I was curious how you handle the fact that the magnitudes of forces are oftentimes contextual. So for example, a gentle nudge is small if you're just nudging a person, but the same force in surgery is really high magnitude. So how are you do you have any suggestions for how to navigate that?
Fantastic question. Yeah, I have 2 responses to that. The first response is going to be, the simplest would simply be, you would train 2 separate models, similar to how we train models on basic human demonstrations. You could, collect data, for example, surgery, or for example, box lifting, to contextualize those forces. However, I think that further work can show that by using specifically more advanced models, and leveraging more transformers and more advanced models, you can actually have it contextualized to those different scenarios with, again, large enough data. We believe most of the bottleneck was just collecting the data, and realistically, you would just have to collect for the data for the scenario that you want to have it for. But no, fantastic question. That's pretty much the future work.
Awesome. Well, thank Carl again.
Our next talk is optimal interactive learning on the job via facility location planning, and will be presented by the Shivam Vat.
Hello, I'm excited to present COIL, a framework. I'm excited to present COIL, a framework for cost-optimal interactive learning that is designed for multitask interaction. Our framework is designed for facilities. Our framework is designed for factories of the future, which will be collaborative and fundamentally human-centric. Robots in these factories will have to work alongside humans to perform diverse physical tasks over extended periods. Robots may ask human coworkers for help, but they must ensure to place only minimal burden on their human teammates. Such scenarios are quite common in factories, but frankly remain underexplored in robotics research, which focuses on developing partial solutions. For example, existing methods are designed for single task learning, but they are not applicable to multitask settings, which are common in factories. By contrast, our approach is designed for multitask interaction, and it can scale to hundreds of tasks. It can perform task allocation in addition to interactive learning, and it provides strong guarantees on the minimization of human effort. COIL can decide when to teach new behaviors to the robot, when to assign tasks to the human worker, and when to assign tasks to the robot worker. COIL can also request for clarifying the preference of the user whenever the robot is uncertain. Each of these queries imposes a different amount of burden on the human worker and is therefore associated with a distinct query cost. For example, teaching a new skill to the robot is usually the most demanding. COIL accounts for these variations in query costs by trading off the cost with the expected reward for completing a batch of tasks according to human preferences. Our key insight is to prove a surprising connection between multitask interactive learning and the classical computer science problem of facility location planning. This allows us to compute bounded suboptimal solutions only in polynomial time. The facility location planning problem requires a set of demands to be satisfied by opening facilities, where opening each facility incurs a fixed cost. Once opened, a facility can satisfy demands by paying additional service cost. The overall problem here is to satisfy all the demands by minimizing the cost of facility and service cost. In our formulation, we show that multitask interactive learning maps exactly to facility location by thinking of tasks as demands to be satisfied and queries as facilities to be opened. COIL can incorporate asking for user preferences by additionally building upon the facility location formulation. We evaluated COIL in 2 simulated domains of grid world and bin packing, and 1 real-world conveyor domain on batches of up to 30 tasks. Compared with several interactive learning baselines, we found that COIL reduced human effort by up to 23%. So a question here is, why is COIL so effective? And we found that this is because of 2 reasons. Because COIL can plan ahead for the entire batch of tasks, it computes solutions that are globally optimal. By contrast, single task methods are only locally optimal and hence myopic. Also, COIL can replan on the fly, and whenever failures in teaching happen, which is quite common, frankly, COIL can replan and change the behavior. So for example, when existing methods encounter a novel object, such as the scan, they typically immediately request teaching a new skill. However, because COIL can look ahead, it realizes that there are more mugs in this batch, and hence proactively chooses to learn the more useful mug manipulation skill instead. However, failures can happen, and in our perception system had trouble detecting the shiny white mug. So the question is, how do you deal with that? And because COIL can replan, it can reassign that work to the human worker so that the task is ensured to be completed. To summarize, for the first time, we have a theoretically grounded framework COIL that works well in practice for multitask interactive learning. In the future, robots and humans are going to work side by side, but we have to think about human needs first. And we will achieve that through algorithms that carefully balance autonomy with human effort. Thank you.
So do we have questions from the audience? Yeah? We'll see, yeah? Backside of in the middle, or? Yeah.
Hi, thanks so much for the great talk. I was curious how you quantified the cost of the different queries and types of human input, and then also human effort in your experiments.
Yeah, that's a great question. So our framework can basically account for any sort of cost, right? And in the paper, we do experiments for different cost profiles. In general, when the costs are higher, the benefit of planning is also higher. For the experiments that we did, for example, the conveyor experiment, kinesthetic teaching is typically much more challenging, so that gets a higher cost. But asking the user a quick question, do you prefer box A or box B, that's much easier, so that gets a lower cost. But the cost of queries are going to be domain specific.
Okay, we have one more question. Yeah, so also in the middle. Yeah.
Great talk. I had a question about how you model the benefits of kinesthetic teaching. How do you model the benefits of teaching the mug demonstration, and how do you take that into account for future planning?
Yeah, good question. So I guess there are two aspects of that. The first aspect is that once you get a demonstration, what's the probability that the robot learns to solve that immediate task, right? And we model that using a probability of the success of teaching. And we can adapt that if we see that actually teaching is failing. And the other aspect is how does that generalize to future tasks, right? So if you have similar tasks in your batch, then that's a much more useful query. Whereas if you have an outlier, like for example, the can example we had, then that's not very useful.
So let's give applause to the speaker.
Thank you.
Great. Our next talk will be a robot-assisted approach to small talk training for adults with ASD, presented by Rebecca Ramnath.
Hi, my name is Rebecca Ramnath. I am a 6th and final year/month PhD student at Yale University, and today I will be talking about building a robot for adults with autism, the design, development, and deployment. So when my younger sister was diagnosed with autism about 20 years ago, the rate for an autism diagnosis was around 1 in 200. Today, it's closer to 1 in 30. So alongside its rapidly growing diagnostic rate, the rate of robotics research dedicated to autism has also rapidly grown in the past 2 decades. And though I show a small sample of these studies on the screen, we notice a huge gap in the literature. Can you see it? Did researchers forget that kids eventually grow up and become adults? Because what kind of support exists for adults with autism? So we interviewed 50 adults with autism to figure out what kind of skills they wanted to improve on. And there were 5 main themes, ranging from initiating conversations to some said, well, I fixate on very specific, narrow topics, so how do I handle more unpredictable, open-ended, interactions better? So when we step back and we look at all of these needs, all 50 adults had identified a skill directly related to small talk, the kind of taken for granted, lighthearted, casual conversation that you would have with a stranger sitting next to you on a bus. And when connected to real adult life outcomes, our participants said, if I can improve in any one of these skills, I can make friends more easily, I can go on dates more confidently, I can make better first impressions during job interviews. But when building a system for small talk training, there are 4 technical challenges. First, are current LLMs even suitable for good small talk? The short answer, and we demonstrate this in the paper, is absolutely not. These systems are designed to provide assistance and information in a way that's completely opposite of the nature of small talk. And second, let's say with extensive prompt engineering, we do achieve reasonable small talk. The behavior is not reliable or robust enough to interact with users that are improving in their own ability. In our early work, we proposed a guardrail mechanism based on principles of robotic action selection. And in this paper, we actually show its efficacy. But ultimately, as researchers, how can we safely deploy an LLM-driven system for long-term autonomous operation with vulnerable users in their homes? So we overcame those challenges, and we detail those in the paper. But we eventually deploy the resulting system into the homes of 25 adults with autism for at least a full week of daily training. And this resulted in a rich data set of over 280 hours of active engagement. And it showed that all 25 users significantly improved in their nonverbal behavior, including eye contact and specific small talk skills. And here's what those interactions look like.
I'm so excited to see you. Hope you're having a great day.
That's awesome to hear. Anything exciting happening today?
I went to the beach.
Going to the beach sounds like so much fun. Was the weather nice there? Did you do any swimming or just enjoy the sunshine?
I just enjoyed the sand.
Thanks for chatting with me. It's good to share personal experiences like going to the beach, as it helps create a connection. Keep up the friendly tone. You did well in showing interest in the other person's hobbies. To improve, try to be more proactive in sharing about your own interests or experiences. This can help deepen the connection in the conversation.
Thank you. That was so cool. I like the feedback. Feedback? No, that was really cool. I actually did the opposite.
Anyway, there's so much I can convey in a 4-minute presentation, so feel free to come by our poster or check out my website for more details. Thank you.
Do we have questions from the audience? I think in the back here in the middle.
Hi, thanks for the great presentation. I was wondering about what you've noticed about the role of the caretaker, the human caretaker, in encouraging and helping adults with autism learn how to interact with these robots. In the video you just showed, I noticed that after every single interaction, the person looked back at their caretaker and the caretaker gave a smile, a nod, and I felt like that I would guess that gave them the confidence to carry on and keep going, doing what they're doing. I wonder what other examples you noticed of that.
Yeah. What I particularly love about this study is that we didn't recruit just high-functioning adults with autism. They spanned the entire spectrum. In fact, this participant is 18 years old and was diagnosed nonverbal for most of their life. And it was, the caregivers, I think about half of our users actually lived with caregivers because they required that daily in-home support. And we definitely did see a range of caregiver to sibling feedback, positive encouragement. But among these 25 users, it varied so much. And we do report a few case studies and interviews from individual users in the paper.
Thank the speaker again. Thank you so much.
Thank you.
So we move to the interruption handling for conversational robots, and will be presented by Xie Chao.
Hi everyone, my name is Shreya Tao, a computer science PhD student from Johns Hopkins University. I'm interested in designing more dynamic, engaging, and natural human-robot communication. Today, I'll present my most recent work on designing an interruption handling framework for conversational robots. Interruptions are a fundamental component of human communication. Interruptions can be classified into cooperative or disruptive, based on the intention of the person interrupting. Cooperative interruptions are intended to express concurrence or understanding, to aid the speaker, or to ask for clarification. Disruptive interruptions, on the other hand, occur when the listener is challenging the speaker's control and disrupts the conversational flow for intentions such as changing the subject. Interruptions can enhance the dynamism and effectiveness of the conversation, but only when it's properly handled by all parties involved in the conversation. However, user-initiated interruptions during human-agent communication frequently lead to conversational breakdowns, as most existing conversational agents either ignore interruptions or always yield to any overlapping speech. So while the types of interruptions have been well studied, there are limited prior work on how people handle these different types of interruptions. To address this, we extracted behavioral patterns of humans handling interruptions from natural human conversations on YouTube. We use these interaction patterns that we identified to guide the design of our interruption handling framework. To handle user-initiated interruptions, our system actually listens for any overlapping speech or interruptions. Then we use a large language model to classify the intention of the interrupter based on what the interrupter said, the conversational context, and the timing of the interruption. Once their intention is determined, the interruption handling system selects the interruption handling strategy based on the predicted intent of the interrupter. Lastly, to support user control, we integrated standard practice from commercial voice assistants where the robot stops talking every time it hears its voice cord. We validated our system's ability to handle user-initiated interruptions through a user study. We recruited 21 participants who have varying experience in using speech-based AI technology. We contextualized our system in a time decision-making and a contentious discussion task, anticipating that time pressure and the controversy can lead to more interruptions. We identified 121 user-initiated interruptions from 207 minutes of interaction data containing 525 user query robot response pairs. Our intention recognition system correctly classified user intention in 88.78% of the interruptions. Overall, we successfully handled 93.69% of interruptions.
Argue that knowing the perpetrator has been executed can bring a sense of finality and justice. They believe it can help families move forward by ensuring the criminal cannot harm anyone else. However,
But can you give me
understand that not
can you give me more like data? Like, has it actually prevented any has it worked as a
I can
deterrent?
provide more information. Deterrence is the idea that the threat or implementation of severe punishment, like the
Handling user-initiated interruptions is a first step towards having more dynamic, engaging, and natural human communication. By letting users interject seamlessly, we empower users to have more flexibility and to naturally control the flow of the conversation. However, we observed the participants develop a habit of using wake words from interacting with commercial voice assistants, which constrained their interaction to be rigid and fragmented, even though our system was capable of having more natural conversational exchanges. So going forward, I'm excited to continue working on exploring how to break these user habits and to transitioning users to having more natural and meaningful conversations with more capable agents. Thank you.
So anyone have questions? Oh, yeah, in the middle.
Thank you for the presentation. Can you go a little bit into detail in how you model the inference using large language model? And did you notice any failures or misclassification during the inference?
Yeah, that's a great question. So we started from literature looking at what the different types of interruptions are and what the user's intentions are. And then we also looked at some videos from YouTube and used that to guide our prompting for the large language model. And then the large language model was not perfect. So it actually only classified about like 88% of the interruptions correctly in our actual study, but that did not always lead to interruption handling failures. Happy to talk more at the poster session.
Any very quick question? If not the case, then yeah, we'd like to thank you. Yeah, that's perfect.
Our next paper will be Astrid, a robotic tutor for nurse training to reduce healthcare-associated infections, presented by Peiju Qian.
Good morning, everyone. Thank you so much for coming. My name is Peiju. I recently finished my PhD from Rice University, and I am an incoming assistant professor at the University of Houston. Today, I'm excited to talk to you about Astrid, which is a robotic tutor for nursing education, developed at Rice University and Houston Methodist Hospital. So nurses are an essential part of our healthcare systems, but the world is experiencing a dire nursing shortage. According to the WHO, we need 4.5 million more nurses by 2030. As a result, hospitals need effective and scalable programs for training and onboarding new nurses. The current model for training and onboarding new nurses is through a nurse-to-nurse model, where the experienced nurses train new nurses. But given the current nursing shortage, this model is not sustainable because novice nurses often find limited opportunities to practice and learn from experienced nurses, as the experienced nurses also need to take care of their patients. And our key insight is that robots can help fill these gaps, serving as tutors and teaching assistants. They have the potential to help novice nurses practice skills and provide them with targeted feedback. We identified this novel and impactful domain and application through a 2-year co-design process that first started with understanding the needs of nurses. During this time, I attended nursing classes. I learned a lot about nursing. I also met with different stakeholders to understand the needs from different perspectives. During this time, we also developed several prototypes to conceptualize the idea of a robotic tutor for nursing education. This was an iterative process where we had nurses coming in to test out the prototypes so we can get some feedback. And when we are finally happy with one version of the prototype, we conducted a formal feasibility study. So in this picture, we can see a nursing student standing on one side of the table. And on the table, we have the patient and the stereo field. That is basically like the workstation of the nurse. And on the other side, we have the stretch robot delivering glucose injection. And on the far left side, we have another RealSense camera that's in front of the nurse. So Astrid provides 2 key features. First, it observes as nurses practice skills and delivers targeted feedback. And this is achieved by using the RealSense camera to capture the training environment as well as the movement of the nurse. This data is sent to the post-estimation module that was built by fine-tuning media pipe for our use case. This data is also sent to another perception module that detects the stereo field on the table. So if Astrid detects a mistake from the nurse, it will issue a task time warning and explains to the nurse what they have done wrong. And at the end of the practice session, Astrid also provides a summary of feedback. The second feature is that Astrid simulates curriculum of nursing scenarios that involve the physical intervention and communication between the robot and the nurse. These are scenarios that represent practical scenarios that could happen on hospital floors. For example, here, the patient's blood sugar is dropping very low very quickly, so the nurse has to take actions right away. To evaluate our system, we worked with nursing experts to annotate 32 recordings of nurses using Astrid for nursing errors. Here we have a high accuracy of 98.6% and an F1 score of 0.89. In addition, we also had collected qualitative data to understand how useful and engaging the participants perceive Astrid. For perceived usefulness, we obtained a mean score of 4.7 on the scale from 1 to 5. I want to emphasize that this is particularly promising and important because successful adoption of robotic tutoring systems for nursing education depends not only on their physical performance, but also on how the users perceive such systems. So as a summary, we introduced Astrid, which is a first-of-its-kind robotic tutoring systems for nursing education, and we are really excited, and we would love to invite you to work on this novel and impactful domain. As mentioned, I'm an incoming assistant professor, so if you are interested in working with me or collaborating with me, please come to talk to me. Thank you.
Great. Do we have questions from the audience? Oh, sorry, Ike, you were behind.
Yeah, thank you so much. Yeah, I was thinking just spontaneously, maybe it's a silly question, but I was wondering if this robot is only, it was not 3D perception, I guess, it was my perception, that it was only moving one side, right? So the question is it useful? Because I mean, I can imagine that this could be even useful in the future if it goes faster, for example, if we manage to go faster and more dynamic. But is it useful to make it 3D aware, like moving in those spaces, or it would be more useful and safer to do this way? What do you think is the future?
Yeah, definitely. Thank you so much for the question. So the question is, right now the movement of the robot is only right in front of the table, and that is designed to protect the safety of the nurse. And of course, this is the first iteration of the system. Right now, we are also improving the system, and one particular improvements we're working on is to have the robot move around the nurse to find the best angle to observe the nurse. So you can see right now there is the table in front of the nurse, so that blocks a lot of the vision, prevents a lot of the vision capabilities. Thank you for the question.
Also, we are perfectly at time, so we'll thank the speaker one more time. Thank you so much.
Yeah, we move to now towards uncertainty unification, a case study for preference learning, presented by Xiaoting Pan.
Hi everyone, I'm Xiaoting Peng from UIUC, and this is our work towards uncertainty unification, a case study for preference learning. Yeah. Oh yeah. So uncertainty is inherent in everyday interactions. Imagine a scenario where the robot wants to learn the human's ideal path of passing a cup of coffee above the table using preference learning. Suppose the keyboard is more expensive than the headphone, she thinks trajectory x2 is slightly better, which reflects her uncertainty toward this preference query. After collecting unpreference data, typical uncertainty-averse models, they only use the preference answer x1 or x2, ignoring their uncertainties, which result in these suboptimal trajectories. And we argue that by integrating human uncertainties, we are able to learn more desirable paths. So in this work, we first introduced uncertainty unification in HRI as integrating human uncertainty into robotic uncertainty-aware algorithms, thus enabling the decision informed by both human and robot uncertainties. And specifically for preference learning, we introduced uncertainty unified preference learning, UUPL, which algorithmically integrated human uncertainties into robotic uncertainty-aware algorithms. I mean, Gaussian process-based preference learning framework. Yeah, this is the overview of UUPL. So the robot is learning users' ideal room temperature. Suppose one preference pair is 20 Celsius better than 80 Celsius with high confidence. First, notice that different people define uncertain and confident differently. So we designed a user-specific uncertainty calibration process to decide those parameters mathematically for individual users. And with the calibrated uncertainties U1 to U4 as Gaussian variance sigmas, we can get different probit models as likelihood of the given comparison data. So with Bayesian update, we can scale the posterior GP variance to be larger with a high confidence comparison U1 and smaller with a uncertain comparison U4. When using the probit model, the GP posterior variance becomes uninterpretable. To address this issue, we introduce an uncertainty weighted GMM, which is updated as new data comes in, and we use the inverted GMM to scale the posterior variance. So intuitively, if a data point is observed many times, or the human uncertainty is low, the variance of the reward function should be low, like here around x equal to 18 and 20 Celsius. Combining these two results, we can get the uncertainty unified GP, which provides a more accurate posterior mean and interpretable variance. Next, we introduce two real-world experiments. The first one involves the robot moving a cup of coffee above the table while avoiding important objects. The other one navigates the robot from the blue to yellow to red star with different route options. This is one example for the first experiment. We learned the human preferences over points on the tables through 20 pairs of comparisons using the interface on the top right. And here are the results learned by the three models. So we can see the no uncertainty and the uncalibrated uncertainty models, they generate undesirable paths. And in contrast, our UUPL can better capture human preferences. So we can see the robot moving velocity is also scaled, so it conveys the robot uncertainty to humans. For the second experiment, a red trajectory color indicates a high moving velocity, and a blue trajectory color indicates a low moving velocity. And suppose the user wants the robot to do the task as quickly as possible, and here are the results learned by the 3 models. So in the video, yeah, we can see the no uncertainty model generate a long and slow trajectory, and the uncalibrated uncertainty model improve the path by moving closer to the rack and increasing the velocity. However, our UUP are better capture human preferences in both travel paths and moving velocity. So we also have quantitative results for simulation experiments, application study, and user studies. Please come to my poster for details. Thank you.
We have some time for questions. Yeah, in front. Yeah.
Hi, thanks for the talk. I have a question about how do you imagine, like, the human preference is not static, but it might be a function of the capability of the robot itself. So if the robot is executing very precisely, confidently, I may not care that if it go over my laptop or not, versus if the robot is really shaky and have, like, I don't know, 50% of chance of like actually stealing the Coke, I would care more. So I'm just curious, how do you think this framework would capture that aspect?
Yeah, that is a good question. And currently, we learn the human preferences not by showing the robot actually doing these stuff. Basically, we learn it by like using an interface. So basically, it's just showing the trajectory. It's not the robot actually doing that. So, but it's a good point. Like, we should consider the robot action itself. Yeah.
Thank you.
Maybe anyone has a pressing question. Otherwise, I invite you to come to his poster for further discussion. Yeah, thank you very much.
Next, we will have demonstrating Arena 5, a photorealistic ROS2 simulation framework for developing and benchmarking social navigation, I believe being presented by Lynn Kastner.
Yes. Okay, yes, let's start. My name is Lynn Kastner. I'm from National University of Singapore, and today I'm going to present Arena 5.0, a photorealistic ROS2 simulation framework for developing and benchmarking social navigation. So we all know simulators are a crucial part in the development cycles across all industries, especially robotics and social navigation, but there are long-standing problems that we aim to address. So first, realistic simulation of human behavior and social interactions are very challenging. And second, the manual creation of simulation environments is very labor and cost intensive. Also, we noticed that there's a lack in unified benchmarking methods for social navigation approaches. And last but not least, translating research into applications is often very difficult as different papers have different setups, settings, or use their own simulators, and it is very difficult to incorporate them into your application for benchmarking. And we aim to address these problems and provide a framework or a platform which is called Arena, and it is consisting of multiple modules. And so there's the Generation Worlds module, which I will showcase in a bit, and it's basically simplifying the generation process of creating simulation environments, so using generative models. So for example, you can input a prompt or you upload a 2D image and interactive 3D environment will be created. And we have a suite of different robots, social force models that you can plug and play. And we also have different benchmarking tools, for example, data processing, data recording, and plotting. So now I'm going to present the demo of our web application, the world generation, basically. So the user inputs a prompt, for example, generate a house with 7 rooms, and then using a diffusion model, a scene graph, a 3D scene graph is generated, which is the structure of the room. And you can also modify the scene graph. For example, you add different assets, you can add different, like a window, a bed, or a table, and click proceed, and then another diffusion model will generate the floor plan for you. And then you populate the furniture inside, and then you can also, in the next step, set the parameters for the pedestrians, so how they move, and then there are different kinds of modes, panic, escape mode, so essentially how the humans behave and move. And then you can export this to your simulator. Next, another example is you upload a floor plan, a 2D floor plan, and the 3D simulator will, the 3D environment will be generated. So it's the same steps. First, the scene graph, the 3D scene graph, and then the floor plan. And then you can download the zip file, which is the folder structure of your simulator. And this is basically abstracted across 3 simulators. So Unity, we have Gazebo, we have ISAC and this is, in this case, we just import it into Unity. And you can see it's fully interactive. It's a 3D environment working with ROS2, and you can operate your robot. You can have a lot of environments, which is very nice. So you can also input, I want 500 environments, 500 similar environments, and then the diffusion model will generate very similar environments for you, which is great for data acquisition and training and testing environments. So this is some examples of worlds that we generated in ISAC and you can see it looks very nice, and you can use it for training, benchmarking, and you have different situations. You have social interactions, you can have emergency situations, and yeah, it's a good platform for training and testing your approaches. And yeah, so we have demonstrations after this talk, so please come to our booth, and there you can test it out. So basically the world and generation across different simulators. You can plug and play different planners, different robots, and we will showcase our web application. And yeah, you can try it out. We will also showcase different task modes for benchmarking. And yeah, so this is pretty much it. This is my, the demo, and please come and have a look. Yeah.
Do we have questions from the audience? Over on the right-hand side, yeah.
This is super cool work. Within this space, I'm right here.
Oh,
yeah,
yeah, okay.
Within the space of language modeling, we're super interested in like simulating societies, where basically you give each of these humans a language model as a backbone and give it a personality and so on. And one of the problems within language modeling is actually creating these environments.
Mm-hmm.
How feasible is it to basically integrate, you know, some personality, some character?
Yeah, this is a very interesting question, very advanced, of course, to use that. So currently we use the language model only to generate the static environments. So actually not the pedestrians themselves. The pedestrians is still using some social force models that we spawn on the next step. So the language model is only for creating the static environment, like a residential home, kitchen, or hospitals. We also so actually this is we need to train it because the data sets is only for residential areas, and we have hospitals and everything too, and offices. But yeah, for these pedestrians, we haven't incorporated it yet. Yeah.
If we can go really, really quickly in the back there.
Okay, thank you.
It'll be quick. Similar question, I guess. How hard in general would it just be to change the behavior, like change it from a social force model to something else for the pedestrians? If I want to do some custom, we can do custom planners for the robot, but can we do custom planners for the people?
Yeah, this is a good question. So actually, now we only have limited set of different social force models that you can choose from. So we have UNFSIM, we have Pi social force model, for example. So this we haven't developed on our own. So this is actually another research direction, like how to model the behavior of humans. But you can use this platform to do that, actually, which is a great opportunity. But yeah, we haven't looked into that ourselves. Yeah.
Great. Thank the speaker once more.
Yeah, thank you.
Yeah.
Next work is safety with agency, human-centered safety filter with application to AI-assisted motor sports. And I believe the presenter is Donggan Oh.
Hi everyone, I'll be excited to share our latest work on human-centered safety filters for highly dynamic environments. Today, we have AI assistants helping people with the safety in a range of settings, from driving to piloting planes and even walking with the exoskeletons. However, humans don't always find the AI system to be helpful. While AI co-pilots may keep the system safe, they often deliver abrupt interventions that neglect human intention and agency. This leads to human operators getting annoyed by lane keep assist, scared of emergency braking, and surprised by autopilot. These uncoordinated co-pilots can lead to a phenomenon known as automation surprise, where sudden AI intervention leads to confusion and even catastrophic failures such as crashes. This calls for a human-centered co-pilot, which should provide smooth, agency-preserving, and transparent safety interventions. But how can we design such a system? To answer the question, we investigate one of the most highly dynamic and safety-critical environment, motorsport. At speeds of over 200 miles per hour, everything hinges on split-second decisions, and human drivers can definitely use some AI assistance to keep them safe. We started by observing non-expert human drivers in a high-fidelity racing simulator, Assetto Corsa. People often made mistakes that led to collision, and cars leaving the track boundaries. The first challenge we're facing is how to compute a safety filter that we can deploy in this extremely complex dynamical system that is only accessible to us as a black box simulator. To tackle this challenge, we synthesized a safety filter using model-free RL-based reachability analysis. We trained the best effort fallback policy together with the safety queue function to decide how and when the filter should intervene. Unlike classical reachability tools, this method scales to our unknown dynamics with over 100 state variables. Great, a natural way to deploy our learned safety analysis is through a last resort or least restrictive safety filter, which gives drivers a lot of flexibility on how to drive as long as they're not in imminent danger, and otherwise switches to the learned best effort safety strategy as a last resort fallback. It works. But when the filter does decide to intervene, its corrections can be abrupt, and because they disregard the human's original intent, they can unnecessarily disrupt people's driving, causing exactly the kind of automation surprise that can leave humans confused and frustrated at having lost their edge in race. This takes us to our second challenge. How can we make sure our AI copilot provides smooth, transparent, and agency-preserving interventions? If we take a closer look at the safety value function, it turns out it is actually a valid control barrier function. Taking advantage of this, we introduced a new notion of state action CBF, or a QCBF, which allows us to impose a completely model-free safety constraint. This results in smooth safety interventions that deviate minimally from the user's intended action, preserving their agency as much as possible. We perform a user study with over 80 human participants divided into 3 groups, a control placebo group who never actually received AI assistance, a group assisted by our human-centered safety filter, and a group assisted by a last resort safety filter. First, we observed that both safety filters significantly reduce safety failures compared to unassisted driving. Here you can see our human-centered safety filter provides smooth but timely interventions on the steering and braking to keep the vehicle from colliding or veering off track. Second, our human-centered filter does a significantly better job of preserving human agency than the last resort filter. Here is a side-by-side comparison of the two filters during typical overtaking attempts. While our human-centered filter helps the driver pass the opponent without collision, the last resort filter keeps aborting the maneuver altogether. Finally, our human-centered filter intervenes significantly more smoothly than the last resort filter. Here is the same track segment driven by 2 of our participants with the 2 filters. Pay attention to how rapidly the assistance indicators change. The human-centered filter avoids the abrupt interventions that we repeatedly see from the last resort filter. Thank you for your attention. Please check out our paper where you can find all the details from our QCBF theory to extensive user study results. And don't miss the opportunity to become a race driver yourself at our demo happening today. Look for a booth with a big racing rig because it's kind of hard to miss. And with that, I'd love to take your questions. Thank you.
So time for the floor here in the middle. Yeah.
Hi, thank you for the great talk.
Thank you.
I would imagine in these highly dynamic racing situations, like latency and inference speed might be a concern. So I'm wondering, in this work, do you pay special attention to this, to resolve the latency, or is this a generally something to be cared about? Thank you.
Thank you. That's a great question because in such highly dynamic environment, it is critical that we provide the exact magnitude of interventions at a very low latency. And thanks to our optimization problem, you can look more about this in our paper, but the optimization problem can be solved in real time. So we provide a control rate of 30 Hertz, which is more than enough to handle such a time-critical, highly sensitive environment.
We have one more here, the middle part, yeah.
Thank you for the presentation.
Thank you.
Have you considered looking into, like, I'm assuming it's a shared control intervention which you're doing right now. Have you considered looking into like some sort of multimodal intervention? Like,
Oh, I'm sorry, the sound is a little echoing. Can you try again? Sorry.
So if my understanding is correct, right now you're doing shared control for the intervention. Have you considered using multimodality, such as like language as an intervention, and what are the challenges with that?
Actually, that's a great question, because we're also looking into methods that we can provide not only like physical interventions on the control channels, but also to cue the human driver with any kind of visual cues or audio cues using large language models.
So thank you, Dongkwon all.
Thank you so much.
So this concludes our session, and we will move to the coffee break, but do not forget to come back at 11 o'clock for the early career spotlight session. And thank you very much for joining the session.
Oh, welcome back, everyone. I hope you had a good break and enjoyed some sunshine. And I'm really honored to introduce Zachary Manchester for this next session. Zachary is right now still an assistant professor with the Robotics Institute at Carnegie Mellon, and is the director of the Robotics Exploration Lab. He's a roboticist, but also an aerospace engineer with a very broad research interest in dynamics, control, estimation, and optimization. One of the key features of his research is to take advantage of advances in computation and embedded electronics to build robotic systems that are smaller, smarter, and more agile. And with this research, he aims at enabling robotic systems to match or exceed the level of agility, efficiency, and robustness demonstrated by humans and animals, especially in challenging environments. So, welcome Zachary Manchester for this talk with a great applause.
All right. Hey, everybody. So I'm going to talk about, I guess, my and my lab's work over almost the last decade, running, I guess, roughly my own very tiny space program. And these are a few of the satellites we've flown that I'll talk a little bit about. But I wanted to kind of start off first with just, I've been doing a lot of, introspection lately on kind of, where robotics as a field is going and like my place in it. And I think this is mainly coming maybe from me getting a little older and having kids now and having to think a lot harder about how I spend my time. And looking around here, like a lot of what I'm seeing is this kind of stuff, right? We're looking at like folding laundry and washing dishes and foundation models and humanoids. And this is all really exciting, and I don't want to downplay the value of this work, but if I think about myself and what got me excited as a kid and what made me want to do all this stuff, it wasn't folding laundry, right? I feel like the 12-year-old version of myself might have been a little disappointed. And for me, though, robotics has always really been about, rather than like imitating ourselves, trying to like transcend our biological limitations and sort of go places that we couldn't go, otherwise, right? It's like this kind of stuff. This is what, and I have to say even now, right, this is the stuff that really gets me excited and makes me want to like get out of bed in the morning and go to the lab and like stay up late obsessing over things like that. That said, right, so I've been a lifelong space nerd. And one of the things that's always kind of bothered me and that's driven me over the last, say, 10 years or so has been trying to make this stuff more accessible and put it out there and make it available to more people, right? And so this was a thought experiment that I kind of did as a grad student that sort of became a real experiment, and I'm going to talk a little bit about that. But I think there's like some really fun things to contemplate here. So I'd love to kind of seed this in your minds and maybe think about it a little bit while I'm talking, and then maybe we can revisit it at the end or talk about it over drinks later. But I think, yeah, what if flying a satellite costs less than your smartphone? We're used to these things being huge and, you know, governments and militaries doing this stuff, but I think there's a lot more we could do if we could sort of drive the size, weight, cost, reduce the barriers to entry down, right? So that's been a lot of my focus, actually. And so there's a few things I would do that I'll just throw out there that I think are kind of interesting that we're kind of not doing so much right now. One, it turns out that the second largest consumer of Earth remote sensing data after sort of national defense and militaries and that stuff is actually the ag industry. And it turns out taking imagery like this from satellites down to like the square meter level in the last, say, 5-10 years with advances in, you know, big data and all this kind of stuff, people are now mining this imagery for things like crop moisture levels, soil nitrogen levels at the square meter level, and then precision targeting where to apply water and fertilizer and things like this to reduce, you know, to improve yields, reduce, use of resources, all this kind of stuff. Problem is the data right now is too expensive. So you can only afford to do this on very high yield crops in expensive areas like California, and not so much in places like, you know, drought-prone, you know, developing countries where it would do the most good, right? So driving the cost down of this, I think, pretty compelling. Another one, these are 3 pictures that I just kind of cherry-picked from the last couple of years from a startup called Planet Labs that operates a big constellation of a couple hundred of very small satellites. And they currently have the highest what's called revisit rate in the industry, meaning they get the most frequent new pictures of any given spot on the ground. They get you a new picture of kind of anywhere on Earth every 12 to 24 hours. And these represent just lucky shots. So the one in the top left there, that's a forest fire in Northern California from last year. And so, you know, you can imagine remote areas where we don't have people around. These are actually quite hard to detect, and detecting them from space like this is kind of a big deal. The next picture on the right there, you might notice a streak across the image. That's actually a tornado in Wyoming last summer. And it's just, again, lucky shot, but catching the path of a tornado in real time is kind of an awesome thing. And then the bottom one is actually a picture of Kathmandu in Nepal immediately after the earthquake that happened there a few years ago. And if you zoom in, you can actually see individual buildings, which ones have collapsed, this kind of thing. So for kind of these disaster response applications, near real-time imagery like this is huge. The problem is right now, we have to get lucky, right? And to get this kind of minute-by-minute imagery, we actually need sort of orders of magnitude more coverage, just more satellites in orbit to do this kind of stuff. The last one I'll mention is very near and dear to me. We've actually worked quite a lot on this problem over the last 10 years or so. This is a global wildlife tracking. So the globe picture there with the tracks on it, that's the migratory pattern of just a particular bird, the Arctic tern. It travels halfway around the world twice a year, and it's mostly over open ocean. So you can imagine if you're trying to track this thing, you really can't do it with terrestrial infrastructure. It's in the middle of the ocean, it's all over the world. You really need to do this from space. And this isn't just sort of a, you know, like, about understanding, you know, migratory patterns and that kind of thing. It's actually really, it's also about conservation and enforcement. So you imagine things like illegal whaling. This stuff's happening in the middle of the ocean in international waters, and we don't have any visibility of it right now. So this kind of stuff can enable, you know, actually enforcing our existing international agreements and stuff like that, which is hugely important. Okay, so that's some stuff I might do and some things we've maybe worked a bit on. I'd love to hear what you guys think of doing with these things. And now I kind of want to get into a little bit of like my personal story, how I got into this. This is baby Zach, about 10 years ago, my very first rocket launch of something I put in space. It's actually the 3rd ever Falcon 9 launch down at Kennedy Space Center. And this was kind of what we were doing there. This was most of what I spent my PhD on. This is called the Sprite. It's still the smallest spacecraft ever flown. It's a 3.5 by 3.5 centimeter little printed circuit board. We sort of ambitiously called this a chipsat, weighs about 3.5 grams. It's got solar cell, little tiny microcontroller, you know, compute on there, radio, IMU, and we did actually put a variety of other sensors on these things to do kind of fun stuff. So we built these things, and then, you know, you've got these really tiny, cheap satellites. I should mention also, back to that smartphone thing, these are about $20 to make, and at current launch prices, if you just kind of, you know, divide it up by mass, and these are maybe $100 to $200 to launch. So we're actually, you know, at this level of a few $100 to put a satellite in space, at least in theory. and I'll mention why it's in theory. Okay, if we have tiny, cheap satellites, you can have lots of tiny, cheap satellites. So this kind of idea came about and seemed fun. You can imagine that the space debris folks might have not loved this, and that there's a long story for later over drinks if you want to hear it about this. But after years of trying and pushing and dealing with government regulators, we were actually able to pull this off. So this is KickSat-2. There was, in fact, a KickSat-1. Space is hard. There's a sad story there, again, for later over drinks. This is the real thing, though, in my lab back in 2018. And this is actually the last footage of KickSat. This is on orbit, getting kicked out of the, this was an ISS resupply mission that we hitched a ride on. And there goes KickSat-2 out into space, never to be seen again. But we actually did, so we were able to close the comms link with this guy, command that deployment that you saw the artist rendering of. And a couple days after that deployment video I showed you, we were able to get the first signals down from those little tiny chip satellites from these guys, actually. These guys are awesome. So this is the Dwingaloo radio telescope in the Netherlands. It's one of the largest steerable dishes in the world. And it's like an old retired decommissioned radio telescope that a bunch of amateurs own now. And they're on Twitter and they're awesome guys. And if you're nice to them and send them swag, they'll help you talk to your satellite. So they actually found these things first. You can see the little waterfall plot. And this is the actual Twitter DM thread from me talking to them, them showing me the data. So it's super cool. Okay, so that's kind of origin of how I got into this and this kind of drive to make these things smaller and cheaper. And now I kind of want to talk a bit about the research we've been doing in my group over the last 5 years or so. Really trying to make space, again, smaller, cheaper, make these things more autonomous, more capable, and get it out there for more people. So the first one I'm going to talk about is a bunch of the work we've done on navigation, sort of finding our way in space. So first problem we've looked at quite a lot is we have these small, cheap satellites. We can have lots of them. We want to coordinate them, do things like swarming, formation flying, et cetera. So relative navigation, just understanding where your buddies are, is really important. It turns out we can do two-way time of flight ranging with our radios on these guys almost for free. And so we have ranges between the satellites. Unfortunately, right, just having range data, you have this ambiguity where you kind of understand the shape of the triangle, but you could arbitrarily translate and rotate that triangle, and it doesn't change the data. But it turns out if you have one additional range measurement to what we call an anchor node, so one additional range measurement just from any single node to something that has a known location, that disambiguates everything. And now you can actually recover sort of global configurations where everybody is, all that good stuff. So we actually, a couple years ago, built a bunch of satellites called VREX to try this out, 3 of these little sort of 1 kilogram CubeSats. We had this idea in a brainstorming session on a whiteboard in December of 2019. And if you remember, there's some interesting things that happened in the beginning of 2020, shortly after this. We actually built this whole thing in just about 12 months during the pandemic, during lockdown. Most of the hardware was built in a garage and a dorm bathroom, doing reflow soldering in the shower or bathtub. So we did this in 12 months during the pandemic. We flew it. Unfortunately, space is hard. Full of disappointments, and this basically sums it up. So these things, for reasons that we could get into later if you want, came out of the deployer pod tumbling crazy fast, and as a result, the energy harvesting chips we were using, the solar charging ICs, because the solar panels kept going in and out of the sun super quickly, never kind of kicked into high power charge mode, and as a result, the batteries never charged, and you can see the power there go down, down, down. So they only lasted a few days, and ultimately we weren't able to run the experiments we wanted to run. Space is hard. So thankfully, we got a chance to try this again. This is a mission called Pi-4 that launched in March of last year, so March 2024. They just re-entered a couple months ago. So we had about a year on orbit with these. So they're 4 spacecraft. They're a little bigger solar panels, a little bit more power, do a few more things with them. And we were actually able to successfully pull off this demo on Pi-4 this past year. What you see here is, so this is just one example data set. We had 2 satellites. We arbitrarily chose one of the spacecraft to be the anchor node using its GPS receiver, and then we just had ranging to the other one. And the plot you see there, so the green dot in the middle is the anchor node. The red lines are about an hour's worth of these ranging measurements, the raw ranging measurements, and then the blue curve is the full 3D relative orbital trajectory that we fit. We were able to actually get the full 3D relative positioning down to about 70 centimeters, which is pretty impressive considering the raw range measurements from these radios are only good to about 2 meters. So a bunch of orbit modeling and fancy nonlinear least squares due to this. So that was super fun. Okay, so another area, so this is relative orbit determination, right? Sort of where are your buddies, formation flying. We also care about absolute positioning in space, right? And you might say, okay, why don't you just use GPS? Well, it turns out doing GPS in space is quite annoying. You can do it in low Earth orbit. You can't do it much higher than that, though, because there's no GPS coverage other places, right, aside from low Earth orbit. And beyond that, it turns out the standard kind of ground GPS receivers you can buy don't work in space, mostly for legal reasons. There's kind of international trafficking in arms restrictions and things like this, so they don't end up on North Korean cruise missiles and stuff like that. But on top of that, there's kind of 3 manufacturers that do make space-grade GPS receivers that you can buy. Unfortunately, they're all big, sort of roughly 10-year-old kind of era GPS chipsets. They draw way too much power. They're too big. In fact, this is one over here, this Novatel receiver. That thing costs about $20,000 now, actually. And it's just barely fits in the largest of the CubeSats we operate. And it draws about 2 watts when we turn it on, which is actually the entire average power budget for our satellite. So we turn the GPS receiver on, we can't do anything else. So there's huge problems with this. And on our smaller satellites, it just doesn't fit. So other options, you can rely on ground-based radar tracking. So the government does this, actually. And there's now a private company operating some radar installations. That's one in the Azores from a company called Leo Labs. We've worked with them. We've tried doing this, too. It turns out radar tracking is really hard, and it can take months to uniquely ID your satellite and get tracking data for it. In the meantime, you can't point a high-gain antenna at your satellite because you don't know where it is. And so you can't close a high-bandwidth comms link and get your data down. So it's a huge bummer. Lots of problems with that. What we've been working on lately is a fully autonomous onboard vision-based navigation setup for these kind of satellites. So roughly how that works, we got a bunch of cameras on the satellite. They're basically smartphone selfie cam grade cameras. They're not particularly good or high resolution. We use very vanilla machine vision stuff. We're actually running YOLO V8 on here to do this. Trained on, it turns out you can get lots of geo-referenced image data. So in particular, Landsat data, there's sort of years and years worth of 1 meter level geo-referenced image data you can get. So we train a classifier network on this that can ID landmarks. Essentially, we take those landmarks, the bearing vectors to those landmarks in the camera frame, solve a pretty vanilla sort of pose estimation problem with some tweaks. We're actually estimating out sort of attitude, angular rates, positions, and velocities, so like the full orbital state, by solving kind of a big nonlinear least squares problem. So that's what that looks like. And this actually, in terms of size, weight, and power, the cameras and the compute for this take up less space and less power than the GPS receiver, which is kind of wild. So we've done this in sim a whole bunch. It works, for Earth. And it turns out we've also done this. There's similar like geo-reference data sets you can get for the moon and Mars. So we've tried it for the moon. It actually works incredibly well, like better than it works at Earth because there's no clouds. And it turns out that craters are very uniquely identifiable, somewhat surprisingly. So you just get tons of these bearing vectors all the time. And we can get it down to like 10, 20 meters within minutes at the moon, which is really cool. The main challenge here is that we're running this, remember, inside a box that has only about 2 watts worth of average power. So we've had to work really hard to sort of run this stuff and be clever about the architectures and compressing things to just fit it on board and be able to run it on board. You can imagine, so we've done some stuff with jets and nanos here, and those draw an order of magnitude more power than our average power budget. So you have to be careful about duty cycling and only turning it on once in a while and that kind of stuff. But in theory, this works, and we're actually going to try this. We're building a couple of satellites, a pair of satellites called Argus right now at CMU with a bunch of students. And these are supposed to fly in October or November of this year, so keep an eye out. Hopefully we'll kind of run some really awesome vision-based on-orbit navigation stuff soon. Okay, so that's kind of navigation. The other kind of thing we've been doing a lot of work on is on the actuation side, how to actually move these things around and do fun, formation flying, et cetera, with them. And I think an interesting thought experiment I've indulged in many times here is for terrestrial robots, we talk a lot about bio-inspiration, and a lot of the robots we make look like dogs and people. And there's a lot of good inspiration there, but for this kind of stuff, for stuff in space, we don't have any of that. And our current spacecraft, they have to carry everything with them. They're carrying fuel, they're carrying batteries, et cetera, and they're not using in situ resources very much. So I've often indulged in this thought experiment of what would a sort of natively evolved space thing look like? And I think it always comes back to this living off the land thing. Like, what can you do with the in situ resources so you don't have to carry around a bunch of fuel and that kind of thing? And so we've played around in a couple different areas here that I'd like to highlight. So one is pointing, what's called attitude control. So traditionally, use what are called momentum actuators, basically just flywheels. These are called reaction wheels or control moment gyros, depending on exactly the details. And they kind of look like this. And the one on the top right there is actually one from the International Space Station. It's like a meter across, maybe. And then the other ones here are actually small ones for small satellites that are commercially available. The interesting thing about this, though, is if you kind of like plot the fraction of the total spacecraft mass that's taken up by the actuators here, it scales horribly as you get smaller. So for something like the space station, the actuators, that actuator is this big, but the space station is the size of several football fields. So the actuators are like, 0.1% of the overall mass budget of the spacecraft. But when you get down to the small satellite scale, it's half the spacecraft mass budget or more. And when you go to the really small stuff, you just can't put these flywheels in there. They just don't fit. So what do? So we've been playing around a lot with what are called magnetic torque coils. The idea is you just have electromagnetic coils. These can be made in a PCB flat. So they take up almost no space. And you run a current through there, you get a magnetic moment, that's the M, and you get a torque based on this kind of cross-product relationship where M's your magnetic moment you're generating with your coils, B's the Earth's magnetic field, local magnetic field vector, and you get this torque out. And basically you can think about this as you're turning your whole satellite into a big compass needle. The problem here is that this is inherently underactuated, right? Because that cross-product, it can only ever get 2 degrees of freedom worth of torque at any given moment in time. So I can make M whatever I want. I don't get to pick B, but B's moving around, it turns out, right? So the Earth's magnetic field is actually very wiggly and messy. And if you're a little bit clever and you know your orbit and you have a map of the magnetic field, you can predict what that B vector is going to be ahead of time. And now you have a motion planning problem. So we've kind of set this up, as a trajectory optimization problem, because that's what I know how to do. And, kind of standard stuff, dynamics, actuator limits. We have kind of a pointing error loss that we try to minimize. The tricky part here is that the state actually is kind of this weird Lie group thing, right? So we had a paper at IROS a couple of years ago called Planning with Attitude that's basically me wrestling with all this Lie group stuff and kind of a optimization on Lie groups for dummies kind of paper. It's kind of fun. So we did this stuff, and it turns out on that Pi 4 mission that we just pulled off this year, we were able to actually demo this on orbit by doing sun pointing. The reason we did sun pointing is that we had sun sensors on board already. They're very cheap and easy, and so we didn't have to work too hard at the state estimation part of this, and it was very easy to verify what direction we were pointed in. So this is kind of the artist rendition of what we were trying to do. Here's the real data from the sun sensors. So what you're seeing is the sun vector in the body frame of the satellite. Black is before we turned on the controller. Green is once we turned on the controller. And that blue circle is the 10-degree error circle around the sun vector. So you can see it kind of spirals in towards that sun vector. And we actually stopped trying. We turned off the controller once we got within 10 degrees because we didn't do a very good job of calibrating our sensors or actuators, and that was kind of within the noise of how good we thought we could do. So we just stopped once we got to 10 degrees. But we actually ran this successfully across all 4 of those Pi 4 satellites multiple times, and it worked super well. We got to this kind of sun pointing configuration within about 20 minutes, which might sound slow. It kind of is, but we did this without kind of, taking up any volume for the actuators, which was very cool. Okay, so that's pointing. The other thing you might want to do, right, is kind of move your satellites around, do some formation flying, coordinate them in some way. And for that, you need propulsion. These are kind of some examples of traditional propulsion systems that have been put on small sats. You got cold gas thrusters, you got chemical prop, you've got ion thrusters, and the things on the bottom left are maybe the most fun. These are called electrospray thrusters. These are really, really tiny. The problem with them is all these are big, and even those electrospray ones, the thruster itself is very tiny, but it needs a big high voltage power supply behind it to run it. So all of these involve valves, high voltage, big stuff, and they don't scale well once again, right? And you have to carry propellant around with you. So we've tried to, and I think another rough heuristic is that putting any of these in your spacecraft is going to 10x your cost and size, weight, and power. So we've tried to sidestep this by being a little clever. In low Earth orbit, there's still some atmosphere, there's some drag, and by kind of manipulating your attitude and flying kind of edge on or face on to the wind, so to speak, you kind of effectively have a brake, and you can do some fun stuff with that. You can bleed off altitude, and you can also affect your phase, sort of your long track separation between satellites this way, right? And this has been done, so that company Planet I mentioned, they do this actually to make what's called a string of pearls formation. The problem with this, you can put your satellites in a line, but for a lot of applications, like the wildlife tracking application I mentioned, you actually need cross-track separation as well. You can't just have everything in a line to do triangulation. So we were thinking really hard about how to get cross-track separation without a prop system. And this is where I got to teach a little orbit mechanics. This thing called the J2 effect. So it turns out the Earth's a little fat around the equator. And that effectively, you can think about it as exerting a torque on the orbit that causes the orbital plane to precess around the North Pole. And it turns out this is very altitude dependent. So now you can see where this is going. I can bleed off altitude with drag. As I go lower, this precession rate speeds up. So if I have 2 satellites, I can sort of bleed altitude off one of them. It goes lower. Now the precession rate speeds up and it starts to accumulate cross-track separation. I wait for that to integrate up, and I drop the altitude of the other satellite down to match, and now they're kind of synced up again. So this way I can actually generate things like boxes and all kinds of kind of fun formations, again, all without a prop system. And this is an example of this controller we developed. It's an optimization problem, on brand. We actually, motivated by this, right, I mentioned the pointing and the formation flying. These are both kind of MPC-flavored problems, but we're trying to run these on really resource-constrained microcontrollers. So this led to a paper at ICRA last year called Tiny MPC, where we developed a really, really lightweight MPC solver that can actually run on board these things. This is showing it running on a crazy fly at a couple hundred hertz, all on board on the little ARM chip. And this is something that we can feasibly run these algorithms on board the spacecraft with. Okay, so to kind of wrap it up here, bring it back home to this kind of idea of putting these things out there for more people, and kind of building an ecosystem for more people to get involved in space. This is the class at CMU where we're building these Argus satellites. I'll mention, so really for me, we have to build all this stuff from scratch. We can't go buy these things like you can now go buy a quadruped or whatever, right? So this is the open source avionics stack we've developed over now several years and multiple missions. It's called PyCubed. It runs Python, hence the Pi part of that name. And it has everything you need on here for kind of your basic small sat avionics. It's got radios, compute, you can put GPS receiver on this, power conditioning, solar charging stuff, battery management stuff, all the basic stuff you need. It's all in GitHub. You can take the files and send it to a board house and populate these and make these for a couple $100s yourself. So if you're kind of space curious, this might be a good place to get started. One thing I didn't mention on that Pi 4 mission, Space is Hard, we actually had the satellites start to drop out on us and go dark randomly after about a week on orbit. And after kind of pulling our hair out for several weeks and trying every possible thing, looking for software bugs, et cetera, in desperation, we kind of had no other options. We started to suspect that it was a radiation-induced issue. I'd never done radiation testing before because it always seemed scary and expensive. Turns out not so much. This is our PyCube board from Pi 4. We went and did radiation testing. And the way you do this on the cheap is actually in a hospital in the kind of the beamline that they use to irradiate tumors for cancer treatment. So you can go in there late at night. And the really cool thing about this is, when they zap a tumor, they have to be very precise about the dose and the spot, right? So it turns out you can target this thing very precisely. You can adjust the spot size. You can precisely hit the dose you want. And this lets you run your board with all your software and individually zap particular chips on that board while it's running, which is super cool. So we threw it in here, and the first thing we did was try the main ARM processor, and it latched up instantly. So we kind of found the problem very quickly. Unfortunately, we couldn't fix it on orbit, but the new rev of these boards that's going on Argus now has a new processor. It's been fully radiation tested, which is kind of cool. And I should mention also there's about a half dozen other universities who've now flown their own small sats based on our kind of hardware software stack here. Let's see. I mentioned we're doing this in a class right now with a whole bunch of students called Spacecraft Design, Build, Fly at CMU, about 25 students right now. That's kind of a last prototype rev of the spacecraft. You can see one of the cameras there. This is actually, we're finishing up this summer. It's getting delivered in August, hopefully to fly in October and demo that on orbit vision stuff. And just a quick plug for something, again, getting this stuff out there, getting more people involved, something I really enjoyed. On Pi 4, we had these deployable panels with a lot of extra area on them. And we decided we had this idea of running kind of a space art outreach program. So there's a thing in Pittsburgh called the Moonshot Museum that's kind of attached to Astrobotic, which is a local CMU spin-out that's doing commercial lunar landers. We brought a whole bunch of fourth graders in from a bunch of local schools. And I had a friend who works at NASA who's just really into the history of art in the space program come and talk about the history of the space program and like the Voyager records and all this kind of stuff to the kids. And then we let them loose with art supplies to kind of draw their own stuff. We scanned their art, laser etched it on Kapton tape, which is basically space duct tape, and then stuck it all over any extra open area that was left on our PCBs and all over the outside of the satellite. And we flew the artwork of about 100 Pittsburgh fourth graders in space on this Pi 4 mission. We followed up, we had like a launch watching, kind of thing, and it was just a really cool thing that I'm hoping now we can kind of reproduce every time we go fly this kind of stuff. And with that, I want to also very much highlight, all the students who really do this stuff. These guys are the ones in the trenches really, kind of building everything and making this go. And this is how you can find me, and I will now shut up and take questions.
So, thank you very much, Zach, for the very inspiring presentation. And we have some time for questions. So, is there any questions from the audience? Yes, okay. I see one question here, over there, on the left. Yeah.
Hi, thanks for the talk. I was wondering if the radiation in outer space would affect the camera working.
It does, yeah.
Like, would that, did you try to try something to actually protect that? Because I know that several years ago, when the Fukushima accident happened, people are also trying to think about using drones to inspect the nuclear power plant. And one of the major problem was the radiation actually affect the camera working on board.
Yeah, so what ends up happening with cameras specifically is that individual pixels die over time due to sort of high energy particles hitting them. So there's actually been work on using CCD sensors as kind of crappy radiation sensors by just looking at the accumulation of dead pixels over time. Short answer is you can't really shield for this stuff, so we don't really bother. And the reason we can get away with it is that our missions are really short, like a year or two. So the accumulated dose over a couple of years is not that bad. And with careful board level design, like protection circuitry for overcurrent, kind of events, latch-up events, you can kind of get away with flying consumer grade stuff a lot. And now that we've tested everything, problems do come up, but we kind of have gotten good at dealing with them.
Okay, thank you. Yeah, we have two more questions. So one on the back over there, and if we get time, the last third question.
Thanks for the talk, really inspiring. You talked a lot about the robots, but not about the vision part. So how close are we to actually tracking these? Hello? Oh.
You just stand up and yell.
Yeah, so how close are we actually to tracking flights of birds on planet Earth? So is there some technical challenges left?
Yeah, so it's, I guess to be clear, right, we're tracking these little radio transmitter tags using RF. We're not tracking them with vision. That would be really hard, right? You need really large apertures.
I see. Okay.
But the RF-based tracking, the way to think about that is basically backwards GPS. So the satellites listen, and the thing on the ground transmits.
Okay.
But that's how we do it, yeah. And that's kind of motivating a bunch of the formation flying and the cross-linking and the relative navigation.
All right, thanks for clarifying.
Okay. And quick question on the first row. Yeah, almost.
What's the path forward for longer missions, for things like that, where you actually do want, say, 10 years worth of life or something like that, but at this scale, this cost, this something?
So yeah, this is something we've thought quite a bit about, actually. So a guy named Max Holliday, who was a PhD student of mine at Stanford, who was actually in the materials science department, and I somehow weirdly ended up co-advising him. He was like the hardware guru, the EE guy who did a lot of the, he basically cleaned up all my really crappy electrical engineering work on all these boards. But he spent a lot of his PhD looking at how to mitigate radiation effects in these really cheap, COTS components without having to go crazy and do, custom semiconductors. And really interesting stuff. So it turns out, if you put radiation sensors in your satellite and look at the dose, it's actually really spiky. So there's these periods where it's really high, but most of the time it's pretty low. And it turns out if you turn off your stuff just for the sort of 1 or 2% of time when the spikes are really big, you can get a 10x lifetime improvement. It's really interesting. So there's cleverness you can do by basically using onboard radiation sensing and deliberately throttling your electronics when the dose rate's high. So by basically giving up 1 or 2% of your on time, you can get 10x wins in lifetime. So I don't know. That's one way.
Okay, so thank you very much. Thank you, Zach, for the presentation. And let's get a big round of applause for Zach Manchester. And please stay seated. We're following right away with the next session on multi-robot systems.
Okay, hello
Welcome to session 10, Multi-Robot Systems. I'm Jeff Hollinger from Oregon State University.
I'm Harish Ravichandra from Georgia Tech.
And our first talk is going to be Resolving Conflicting Constraints in Multi-Agent Reinforcement Learning with Layered Safety, presented by Jasmine Jerry Allure.
Hello everyone, my name is Jasmine, and today I'll be presenting a work done with my following collaborators. Collision-free operation is a fundamental requirement for multi-robot coordination tasks, such as formation control and autonomous navigation. With a growing interest in advanced aerial mobility applications, developing a scalable, low-altitude air traffic management system is an urgent need. AAM operations are expected to be large-scale, ad hoc, on-demand, and dynamic. In today's airspace, we have airspace separation, centralized air traffic control, and protocols and collision avoidance algorithms on individual aircraft. However, in the era of advanced aerial mobility, some of these layers I just mentioned may not be as effective as before. We could have multiple operators operating in the same airspace, or the introduction of a third aircraft may not lead to safe behaviors. So in our work, we present a layered safety architecture that integrates a CBVF with a multi-agent reinforcement learning algorithm. We train using curriculum learning to balance exploration and safety and demonstrate effectiveness through hardware experiments with crazy flight drones and AM simulations. In this work, we use a model-based safety certificate function called the control barrier value function. Traditional safety approaches generally offer guarantees when only a single set of constraints is involved. However, with multiple agents, resolving a constraint between two agents may conflict with a constraint that involves a third agent, resulting in a gridlock. The inability to simultaneously satisfy all constraints could lead to collision becoming inevitable. Additionally, the intersection of individual safe sets may not be the true safe set, and this gap is referred to as the leaky corner. And unfortunately, identifying these leaky corners without recomputing the reachability is still an open problem. So in our work, let's define some distances. We define the collision distance and a potential conflict range. Here we see one agent within the potential conflict range of the ego agent, and this is an active engagement for collision avoidance. However, if there are more than two agents within this range, then there can be potential conflict, and this agent has to avoid the zone to prevent any collisions. In our layered safety approach, we have a safety-informed graphical neural network acting as our MAL policy that learns to avoid these potential conflict regions. We then have a prioritization module that selects the agent pair that is at the highest risk of collision based on CBVF values. And finally, we have a safety filter that updates the action to prevent collisions. In our experiments, we have drones, quadrotors, navigating to goals through waypoints. We compare the safety blind approach to our approach. Notice how this yellow agent misses the waypoint and has to come all the way back again to reach its goal. In our approach, the yellow agent waits till the waypoints are available, therefore preventing conflicts. We also perform simulations of an air taxi operation scenario, combining a merging scenario in San Francisco Bay Area. We again compare the safety blind versus our safety informed approach, and I want you to notice the lower time taken and the lower number of near collisions in the approach on the right. We also check other performance metrics such as goal reaching rate and near collision percentages, and note that our method outperforms other model-based and model-free methods, and when we increase the number of agents, we still get better performance. To summarize, in our layered safety architecture, we combine multi-agent reinforcement learning with the control barrier value function. MAL learns to proactively navigate these potential conflicting constraints and at the same time optimizes for task performance. CBVF, providing a safety-informed reward signal, helps SMART choose behaviors that are both safe and effective. And this enhances both safety and performance to a level that neither can alone achieve. Thank you.
Okay, questions for the speaker? So if you're thinking about a very crowded airspace, say you have 100 vehicles, what kind of challenges would arise in terms of scalability or in terms of performance in that kind of a scenario?
Yes, so when we have really large number of agents, it really comes back to the multi-agent reinforcement learning algorithm that prevents congestion to happen in the first place. So some form of a strategic behavior where they prevent showing up early, maybe loitering around before so that you show up when the airspace is more free. And when it does come to that last stage of congestion where everyone's at the same place and they all need to go through the same waypoint or route through this at the same time, then we probably have to have these safety filters do pairwise interactions. And there is a possibility that sometimes they may not work as well, but ideally the combined effort should prevent such things happening. But yeah.
Other questions? Over back there?
Hi. Yeah, this is really cool stuff. I'm kind of curious, actually you kind of just addressed it, but I'm kind of curious about the deadlock resolution, and in particular, what happens if you've got like a lot of agents right next to each other? Do you train for like, is the CBVF like handling like multiple agents all at once, or is it for a specific number of agents?
Yeah, so the CBVF is only pairwise. So the prioritization module picks which pair is like most risk of collision and then tries to filter out their actions and then the next and so on. So the CBVF is only pairwise at this moment so that we can make it scalable.
Thank you.
Okay, thank you very much. We're moving on to our second talk now. And this will be Fermi, flexible radio mapping with a hybrid propagation model and scalable autonomous data collection. This will be presented by Yishi Kai, and there will be no Q&A after this talk.
So, hi. As the authors cannot be here, so I'll help them to present their work on wireless signal prediction for multi-robot system communication. Yep, so in multi-robot collaborative tasks, robot can communicate with nearby robots or human operator to interact or change information. However, in real world, wireless signals can behave really complex, so obstacles can cause signal attenuation, while interactions like reflection can conversely boost signal strength. To flexibly maintain or adjust communication links, we need to accurately predict wireless signal strength at any given location. So more specifically, our research question is, in a scene with no geometry, given locations of a Wi-Fi transmitter and a receiver, how can we predict the signal strength and receiver? So accurate signal prediction presents two main challenges. The first challenge stems from the inherent complexity of signal propagation. Effects like attenuation, reflection, and diffraction make precise modeling extremely difficult. Consequently, previous methods based on physical models or data-driven methods often have to compromise between accuracy and the need for massive data sets. And the second challenge is the efficiency and large labor of current data collection methods. They typically require manual and repeated deployment of transmitters and receivers. Yeah, so to tackle these two main challenges, their work Fermi offers a comprehensive solution. It has two key parts. For the signal modeling problem, they propose a hybrid hyperpropagation model that combines explicit direct path propagation with implicit multipath propagation. This approach allows for accurate signal strength prediction for any unseen transmitter, receiver localization combinations using only a small amount of collected data. For the data collection problem, they designed and implemented an autonomous multi-robot data collection system suitable for any number of robots achieving efficient and parallel collection. So they also evaluate the Fermi's generalization probability. I think I'm a little bit ahead of the video. Yes, so they evaluated Fermi's generalizability. So in the simulation, they used a 1.5 meter grid resolution to render the signal strands for the entire scene at given transmitter locations via offline ray tracing. So they then randomly selected data from several TX locations for the training and the data from other TX locations for the testing. They compared their methods with SOTA methods in both robotics and wireless communication fields. The results demonstrate that the Fermi achieved significantly lower error than the benchmark on unseen TX RX positions. The visualization on the right provides a qualitative comparison. And to evaluate their planning method for autonomous data collection, they compared it against a greedy algorithm as a baseline. Their method demonstrates significant advantage in reducing the number of movements, minimizing the total path length, and enhancing real-time computational performance. The right side shows the robot's movement sequence during a real application. And finally, they validate their overall system performance in a real-world indoor environment. So experiments were conducted on a single floor of a building, measuring 94 by 64 by 3 meters. The left side illustrates a part of their data collection. When the transmitter is within a red box, the collected receiver data points are shown in blue. On the right, you can see a signal strands visualization for fixed TX location collected densely. On this real data set, their method also achieves significantly lower error compared to the benchmark methods. And yes, so thank you. So they said their code will be open source, and thank you all for the listening.
Okay, the next talk of the session is going to be online competitive information gathering for partially observable trajectory games, and this will be presented by Mel Krusniak.
Yes, hello, my name is Mel Krusniak. I'll be presenting online competitive information gathering for partially observable trajectory games. So humans are constantly sensing information about other humans in their environment, and we'd like robots to do the same. To that end, we became interested in game theoretic conceptions of adversarial, continuous, and partially observable robot environments. In particular, we were interested in a procedure called Model Predictive Gameplay, or MPGP. MPGP, if you're not familiar, is pretty similar to MPC, except for instead of solving a regular trajectory problem at each time step, we solve an adversarial trajectory problem, or essentially a game. The nice thing about MPGP is it's very good at solving games like Pursuit Evasion or Tag. But the downside is that MPGP doesn't natively handle imperfect information games. So on the right, you can see an example of a Pursuit Evasion game. Blue is the pursuer, red is the evader. The pursuer is randomly begun at either the right or the left side, unknown to the evader. And in baseline MPGP, the evader can only sort of just run away from the average location of the pursuers. It doesn't really know how to look around and localize the pursuer. That's the intended behavior, and that's what our process handles. So you might think that you could use just some sort of a kind of belief space approach for this, but it turns out that reasoning with beliefs gets really complicated in multi-agent scenarios, especially adversarial ones, because suddenly you have to reason recursively about other players' beliefs, about your belief, and so on. So for that reason, we actually reason directly about observation histories, and specifically, we reason about an infinite number of possible opponent observation histories. And even more so, we actually reason about an infinite number of possible ego observations as well, because our imagined opponents don't necessarily know what we know. This forms a partially observable Markov game with an infinite number of players. And we can solve this partially observable Markov game by sampling these players and running gradient play. This gives us our own policy and imagined policies for all other players. We can insert our own observation history, our real one, into our policy, execute it, and this gives us a real-world action. We represent this game with a stack of particles. Each particle is essentially a joint observation history across all players. And the nice thing about doing it this way is essentially we can update these particles simply by rolling out these policies in a way that's completely agnostic to our own information. So if we do this right, all players in the game are maintaining essentially the same distribution. In practice, this doesn't always happen. it is possible for these distributions to diverge for various reasons. It can be because there aren't enough particles to fully represent the real observation histories for all the players, and it's possible that players might not agree on the equilibria, so there could be multiple equilibria in the game. To handle the first problem, we essentially occasionally on particles treat them like regular particle filters, so we kind of plug in our real observation histories and recondition. This has the downside of essentially we're modeling opponents that know a little bit more about our observations than they actually do. It's also possible for players to disagree on the equilibrium. So for instance, in tag, we could go left or go right. And we actually handle this simply by solving the game multiple times. This relatively simple procedure actually turns out to be pretty competitively advantageous. So for our results, we tried this on the regular tag game that I showed you earlier. We also tried it on a sort of tag chain with n players instead of just 2, a hide-and-seek version that had visual and physical obstacles, and just for fun, a partially cooperative version taking place in a warehouse simulation where one player is completely unaware of the other player. And as you can see, in all cases except one, using our procedure, which is marked here as active, essentially gives a benefit to cost, which is reported here, for all players. If you're curious why hide-and-seek is the one exception to this improvement, you can ask us at our poster, at poster number 32. To summarize, we've presented a novel enhancement of MPGP to handle imperfect information games. We've described a simple online solver method that handles these situations. We've given evidence that this method achieves active information gathering in 4 scenarios. And although I haven't talked about it in this presentation, we have experimental data on timing and equilibrium agreement when this is run in a fully online scenario using our method. And if you're curious about that, again, find us at poster 32. So with that, thank you, and I'll take questions.
Questions for the speaker? Question there?
Very interesting work. I'm curious how you handle occlusions in the environment, if you have visibility occlusions.
Did you ask collisions?
Occlusion.
So, occlusions.
Yeah.
So that's sort of only relevant for the hide-and-seek example, right? You mean? Yes. So that's basically, this is a fully model-aware version, model-aware conception of these games. So the occlusions are basically physically, they're just tacked onto the cost, so we just want to avoid these areas, and they just affect the observation function, basically.
Thanks.
We have one more question. So it seems like, given that you're trying to hallucinate these different scenarios, it seems like that would require kind of a lot of hallucination because it's this Markov game. I mean, how do you keep the number of samples down and still have good performance?
Yeah, so that's where some of this sort of partial conditioning happens. So that allows us to make sure that we're at least somewhat grounded in the real world, even if it kind of gives a slight disadvantage because we're playing against players who don't necessarily know what we know. We can actually assume that, well, maybe they do sometimes, and that sort of helps keep us grounded even at a slight cost.
Okay. All right, let's thank our speaker again. Okay, the next talk in the session is going to be Collaborative Object Transportation in Space via Impact Interactions, presented by Joris Verhagen.
All right. Hi, everyone. So as introduced, we're talking about collaborative transportation in space, and we try to use impact interactions between robots and objects to facilitate that. So imagine a scenario. Okay, I'm going to have more time. Okay, imagine this scenario. We have this toolbox, this red piece on the top of the ISS, and we somehow want to transport that to the bottom. We have 3 robots to do these tasks. Now, what is an example of how you could tackle this? You could make a rigid connection between robot and object, or you could connect cables between, and you could essentially drag it down if the video would play. You missed it, but you can imagine how it looked like. Okay, you're going to miss the cool animations that I worked very hard on. But in space, there are some advantageous properties, namely that at least locally, there's no gravity and there's no friction. So what does it mean? Well, you can push something in a certain direction and will keep moving in that direction. So if we can plan for that, that would be great, and we could transport objects in such a manner. From a more high-level perspective, we are interested in having objects perform some high-level specification. For example, it might visit either region, region A or B, within a certain time interval. And the way we do that is formulate the specification with a formal language, such as signal temporal logic, which is has binary and temporal operators over real-valued signals. In this case, a real-valued signal would be the position of the object. All right. So something from like a somewhat natural language can be transformed into a temporal logic formula. And what we're trying to look for is trajectories of robots and impacts between robots and objects, such that the toolbox will satisfy a specification. There is such a formula. All right, so I hope you can imagine that this is quite a challenging planning problem. So not only do we have disjunctions and temporal flexibility that's normally apparent in signal temporal logic motion planning, but now we also need to determine when, how, and with whom do objects have to impact in order to satisfy this. And to alleviate some of the problems, in the high-level planner, we use a point impact model. And we parameterize our trajectories using Bézier curves, which can take up arbitrary space and time. But this simplification brings some issues with it, which means that during planning, the biggest source of uncertainty is the impact interaction between robot and object. And what we've been looking at in this work is, okay, we have this simple impact model during planning, but can we maximize this source of uncertainty while satisfying the high-level specification? So can we add an additional term, delta, for robust satisfaction of the STL spec. So what does it mean? It means that instead of planning for deterministic trajectories, we are actually planning for somewhat, in a sense, funnels of object trajectories in the future. And what does it mean? It means that the second robot now has to consider the existence of valid trajectories which point the object to the other way. I doubt this animation is going to work, but what it would show is that we perform software in the loop and hardware validation of our method on our recently developed space platform at KDH. And this is a 2D equivalent of free floaters. So here the specification is to move the object from the top to the bottom to the green region while avoiding the obstacles. We have two robots on the left and right, and we have the object in the middle. And you can see with just 4 impacts, we can ensure that the object satisfies this specification. All right, so perhaps it sounds a bit far-fetched, but we also validate on hardware. So here again, a specification. This is the conclusion slide. We missed one. Yeah, okay, a slide is being skipped, but I would recommend to check out the QR codes where we have the code. There it is. Okay, so here the specification is to move to each blue region in arbitrary order and to finally end up at the green region. And we see, if you can see the yellow lines, how there's a pre-planned trajectory and there's replanning going on. There's a whole pipeline, and please check out the poster if you want to know more about that and how we deal with that. So in conclusion, we have a way of having objects satisfy high-level specifications. And these objects are completely passive, but we plan trajectories for the robots and impacts for the objects. So we can maximize any STL robustness metric, but also the uncertainty. And please check out the QR for the videos without any stuttering. Thank you very much.
Question there on the right.
Okay, thanks for the nice one. So I assume that the model is for a collision between the rigid objects, right? So how your model can be generalized to the like a soft impact like between sub-objects?
So good point. So currently, the method only works, like you said, for rigid objects and also for circular objects. So in that sense, we're quite lucky that our robot looks like that. I'm actually currently pursuing that, and we are looking into kind of a sampling-based replanning approach, where you use the physics that you might not be able to plan in a closed form for, and using rollouts and selecting parts of those.
More questions? Question there, yeah.
Are you worried about damaging the robots at all when they hit each other?
Yeah, excellent point. So impacts allow us to formulate this in the planning problem quite nicely. If this would be executed around or in the ISS, I would look much more in the direction of velocity matching. There's work out there on that, and we're currently trying to extend our method to that. It's a more difficult planning approach and a more difficult execution approach because there's interaction between thrusters that affect the object. But yeah, excellent point.
Okay, let's thank our speaker again for this presentation.
Thank you.
Next presentation will be Apex MR, Multi-Robot Asynchronous Planning and Execution for Cooperative Assembly, presented by Philip Wang.
Hi, today I'll be presenting our work on multi-robot asynchronous planning and execution for cooperative assembly tasks such as Lego assembly. Multi-robot assembly faces many key challenges. For example, robots need to avoid collisions at all times, incorporate complex manipulation policies that may also have uncertainties, scale to long horizon assemblies, all while maintaining efficiency. Many existing work in this area, but have some key limitations. For example, they either assume sequential or synchronous execution, assumes open loop execution of the plan, or the planning just takes too long to be computed. We need to decide on the tasks, grasps, trajectories, and also coordinate collision-free execution. So first, we generate a sequential task plan with integer linear program. Then we use single agent RT planner to generate a motion plan for each task. And the key part of this work is this idea called temporal plan graph, which then post-processes the motion plan for asynchronization and execution. So how can we build a TPG? Given a sequential task plan, we first take all the transit trajectories and generate a set of corresponding post nodes for each of them. Then, for all the manipulation skills such as pick, place, or handover, we generate a corresponding scale node for every one of them. We use edges to represent precedence constraints. So what does that mean? For example, in your task plan, you may already have some precedence constraint between tasks according to your assembly sequence. So we copy them to our TPG. We then scan for collisions, and for every collision that we find within our post nodes, we add a motion dependencies or a constraint from an earlier node to a later node. And since this TPG is a graph, each robot can execute on its own pace asynchronously as long as they satisfy the incoming type 2 motion dependencies and task dependencies. So during execution, we host the TPG in a central server, which monitors the execution and schedules each robot. Each robot maintains its own controller execution and sensor feedback loop, and they also have an action queue. Any node that are up to any incoming dependencies can be safely executed, and they're sent to each robot's action queue. And then the robot then starts executing and updates its status back to the centralized TPG server, so that new nodes that become safe can be added back to each robot, and the execution continues. We evaluate with two baselines. First is a sequential turn-based plan, and the second is a synchronous plan, where each robot has to wait for all the other robots to complete their tasks before they can proceed to the next task. So in simulation, we run all our manipulation skills deterministically. On the left is a sequential plan, and on the right is the same sequential plan, but after TPG post-processing, where they can execute asynchronously, and this minimizes the wait time as long as it doesn't introduce any new collisions between the two robots. So we use make-span improvement to evaluate the performance of applying TPG. So the blue dashed line shows the make-span of the sequential plan. The orange bar shows that for a synchronous plan, And we can apply TPG to both either a sequential plan or a synchronous plan. And we can achieve performance improvement for both of them. We evaluate on 9 Lego assembly tasks, and we can achieve performance improvement of up to 42% in terms of make span. We also show the runtime of our algorithm here. And note that our method can scale to very long assembly tasks with over 250 components. That equals to about 1,000 tasks in under 10 minutes, something that's quite challenging for existing method. So in summary, we present an asynchronous planning and execution framework for multi-robot cooperative assembly tasks. Our TPG execution framework can significantly improve the make span, and this is the first robotic system capable for assembling customized design using commercial standard Lego bricks. So for more detail, please check out our website for code and more videos, and I welcome you to talk to me during the poster session. Thank you.
Questions?
Oh, there's one there.
Is there one?
Oh yeah, great. Thanks a lot for the talk. How about scaling beyond 2 robots?
So our method can scale beyond, so we tried a little bit of experimental scaling to 3 robots and 4 robots. So it is a limitation that the method scales quadratically with the number of robots, but it is possible. And in this work, we kind of focus on scaling to longer horizon assembly sequence, because unlike mobile robots, you usually don't want to put like 10 manipulators in the same scene.
Awesome, thank you.
Do you have one more question for the speaker? You have a question there?
If you have a bimanual robot and sometimes you need to decide whether to do 1 hand or 2 hands cooperatively or taking turns, how would you bring that into this framework?
So this framework is not really, so the key idea is that you have already decided which robot is doing, after you've already decided which one of your arm is doing which tasks, then you can kind of parallelize or speed up your execution. So we do have our own optimizer to decide which arm does what so for our assembly tasks, but it doesn't have to be the same optimizer in your case. It can work with any optimizer as long as you end up with a motion plan, and then we can use this framework to speed up the execution and make it more robust.
Okay, let's thank the speaker one more time.
Next up, we have hierarchical temporal logic task and motion planning for multi-robot systems, and we have Zhongxi Wei here to present.
Hello everyone, my name is Zhongqi. This is our work, hierarchical topological task and motion planning for multi-robot systems. Multi-robot systems often need to collaborate each other to finish the given tasks. So the motivation for our work is to have a planning and decision-making system that enable multi-robots efficiently to achieve the complex task specification and robust, safe tasks and behaviors. However, task and motion planning problem is known as the NP-hard problem. It's a combinatorial optimization combined with discrete task allocation and continuous motion planning. The existing methods often solve this problem separately, and they always assume that low-level motion planning can finish the given task. However, in a real-world scenario, predict the feasibility of motion planning is very difficult. Also, somehow task is very difficult to interpret. So in our work, we try to combine the task planning and the motion planning, solve the whole problem together. This is our problem formulation. The decision variable is the all-robot trajectory, and we consider the task constraints and the collision avoidance constraints. Given the non-convex nature of those constraints, this is the mid-integer non-convex problem, and it's very difficult to solve. So the contribution for our work is that we propose a general planning and decision-making algorithm to address these long-horizon multi-robot tasks. Given some high-level task specification, our planner can output the optimal collision-free trajectory to finish the given task. Our method is based on two strong tools. First one is hierarchical linear time logic, which enable complex task specification, can add the task constraints that evolve over time. And also, it's more expressive than the flat version of linear time logic, very suitable for the multi-robot problem. The second one is graph of convex sets. It's a computation tool for the combinatorial optimization problem, and it has a convex realization solution for mixed integer convex programming. So based on those strong tools, our method is that we describe our task by the hierarchical linear time logic, and then we convert it into the DFA, which are kind of a graph to describe all possible states that can finish the given task. And for the motion planning problem, we try to do the convex decomposition of robot configuration space. If any of the convex sets are connected, we can add edges and build a transition system, which is a graph to describe all possible motion robot is physical feasible. And then we do a graph product. If a robot is task feasible and motion feasible, we can add edges. Since this graph can be very large, then we can prune the graph based on the task specification and to find the essential nodes and remove unnecessary nodes which is unrelated to the problem. And then we solve it by the GCS trajectory optimization with the handover constraints. So this is our result. Given the high-level task specification, our planner can output the optimal collision-free trajectory to finish the given task without specifying which robot to deal with which kind of task, and without specifying when and where the robot needs to hand over. And for the computation time result, our problem can solve the problem in the reasonable solving time compared to the baseline. And for the summary, we propose a mixed integer convex programming solution for multi-robot task and motion planning problem. And our planner could find an optimal solution with sound and complete guarantees in a reasonable solving time. And the potential future work is investigating the convex realization for the mixed integer convex programming in our setting. That's it. Thank you.
Are there questions for the speaker? In the front.
Yeah, thank you for the great talk. So what are the states of the system or the observations, like the visions or the point cloud or the depth of the environments do you need for the plannings?
Oh, we only consider the mesh of the environment and add to the system. And we do the collision checking to calculate the standard function.
Yeah, thank you.
Any other questions? Okay, as people are thinking about it, one question I have is, you have the bi-level program here. You're making decisions at the task level and then decisions at the lower level. Do you experience situations where you find this lower level solution is infeasible? And if it is, how do you deal with that?
We try to combine with the task planning and the motion planning. We all generate all possible solutions on the graph. This graph will include some task information and low-level motion planning information, and we solve it by the optimization solver.
Okay, let's thank the speaker one more time. So next up, we have a probabilistic measure of multi-robot connectivity and ergodic optimal control. This is going to be a pre-recorded presentation, so there will not be a Q&A session after this.
I'm Yongche Liu, and today I'm honored to share our recent work, a probabilistic measure of multi-robot connectivity and ergodic optimal control, in collaboration with Professor Richard Ren at the Joint Institute, Shanghai Jiao Tong University. This figure shows a mountainous area with 3 regions to be searched. The joint has 2 key tasks during trajectory planning. first, to collect the information, and second, to maintain connectivity. This leads to our research problem, which consists of two main challenges. First, we want our robot to spend more time in high information areas, which is referred to as ergodic search in the literature. Second, maintaining continuous connectivity is inefficient or even impossible in large-scale scenarios. Therefore, these robots need to intermittently connect to share their gathered data. Intermittent connectivity has been widely studied in recent years, such as building reconnection paths and scheduling connection events among robots. However, these methods typically treat connectivity maintenance as a separate task, which may reduce the overall efficiency of the main task. As shown before, ergodic search gives us the following intuition. As the time horizon increases, the robot's time average statistic approach the information distribution. So, the key question is, given the time statistic, how can we plan ergodic trajectories that also ensure intermittent connectivity in a principled and efficient way? Here, we introduce a probabilistic connectivity measure. These two figures show the robot trajectory with the time domain. Through that, we can derive the robot trajectory time averaged statistic. Rather than maintaining explicit and fixed connection events, we analyze the joint statistic of robot trajectories. That is, based on the joint statistic, we compute the probability that two robots are in the same connection region. This measure is continuous, differentiable, and more flexible than hard constraints. It allows us to encode intermittent connectivity as a soft constraint during trajectory optimization. With this measure, we formulate an optimal control problem. The objective is to minimize ergodicity, to ensure effective information coverage, and we also need to constrain our new probabilistic connectivity measure to ensure robots meet sufficiently often. Theoretically, as shown in the existing literature, we transform the ergodicity as a terminal cost term. Besides, due to the property of the probabilistic measure, we can rewrite the connectivity constraint as a stage-wise form. Therefore, we can derive the necessary conditions using Polyargin's maximum principle. Numerically, we adopt the augmented Lagrangian method and solve the problem iteratively using ILQR, a fast trajectory optimization technique. Our results show two key findings. First, there is a strong positive correlation between our proposed probabilistic measure and actual connectivity. Compared to a baseline, our method achieves lower ergodicity, that is, better information collection, while still maintaining effective connectivity. This video shows our hardware validation. The robots intelligently decide where and when to meet and maintain intermittent connectivity during ergodic search. This balance between exploration and communication is crucial for scalable autonomous multi-robot systems. This slide shows the summary. In Notion, we introduced a flexible probabilistic connectivity measure based on the joint statistic of robot trajectories. In problem formulation, we formulated an optimal control problem and solved it theoretically and numerically. In the results, we demonstrated the positive correlation between the proposed measure and actual connectivity. Meanwhile, our method achieves lower, that is, better performance ergodicity while satisfying connectivity requirements. This is our public code. Thank you for your attention. I'm happy to take any questions.
All right, next up we have How to Coordinate UAVs and UGVs for Efficient Mission Planning by Mohammed Safwan Mondal and colleagues.
Hello everyone, I am MD Safwan Mondal. I'm a PhD student at University of Illinois, Chicago. Let me start by introducing a multi-UAV UGV cooperative routing problem. In many real-world applications like disaster management or surveillance mission, UAVs or drones are tasked with visiting a set of target points or mission points. UAVs are fast, agile. They can visit these mission points very quickly and efficiently. But due to limited battery life, UAVs are need to get recharged very frequently. This is where we can integrate the UGVs or the ground vehicles in the system. the UGV can travel on the road network and can support the UAV by acting as a mobile recharging station where the drone can land. And in this problem, our goal is to physically visit all the target points in the minimum possible time by coordinating the UAVs and the UGVs efficiently. The challenges come from the individual vehicular constraints, like as I said, UAVs are fuel limited and UGVs are speed limited and bound to travel on the road. So in order to visit all the target points in the minimum possible time, first you have to solve a routing problem to get the route sorties of both the vehicles, then a scheduling problem to make the rendezvous between the UAV and the UGVs. And then you also assume that one UGV can support only one UAV at a time during the recharging process. So if the rendezvous instances are not properly scheduled, then other UAVs will have to wait if a UGV is occupied with a particular UAV, and that will delay the entire mission completion. So we are proposing an encoder-decoder transformer architecture. The encoder takes the raw input feature like the 2D mission point coordinates and then gives the encoder embedding as an output by extracting the feature. Then the decoder will take the encoder embedding as an input, and then the decoder also takes the state as an input and creates the context vector. Using the context vector and the encoder embedding, the decoder takes the action. First, it selects the agent, like the UAV or UGV. Then for that agent, you will take action. Now, based on the taken action, the state will be updated, and for the next state, new actions will be taken. So in the agent selection process, first we select the UAV as an active agent. Then for that active agent, actions are taken. Once that UAV has completed the route sortie, then we switch to the other UAV as the next active agent. Once all the UAVs have completed their route, in this process, then we will switch to the UGV as the active agent. And once all the UAVs are recharged by the UGVs, then we will switch back to the UAV for the next cycle, and this process will be continued. In the action selections process, when the UAV is the active agent, we'll select which mission points will be visited by that UAV or which points will be recharged. And when the UGV is the active agent, which UAV will be recharged by that UGV is selected as an action. So in the experiment, as a comparative analysis, we compared our method against the baselines by varying the problem sizes and the scenarios. In the generalization test, we have tested our model on larger problem sizes and scenarios with different settings and scenario settings. As a dynamic planner, we have used our model as an online planner for considering the dynamic changes during the mission. So this snap basically shows the comparative analysis across the different team configurations on scenarios with 60 task points. And as the number of agents have increased, the mission completion time has reduced. But the improvement is not always linear. For example, the 4 UAVs, 2 UGV system performs quite similar to that of 2 UAV, 2 UGV system. And this is because of the improper coordination between the agents, which creates the waiting time and that delays the mission. And this effect is particularly dominant in the case of heuristic baseline that we considered. In general, the learning-based methods, they outperform the heuristic baselines in completing the mission. Our reinforcement learning framework outperforms the learning-based baseline that we consider. This video basically shows the dynamic planning that is occurring. So in case 1, we assume that new task points will be appearing during the mission. And in case 2, assume that there will be changes in the team configurations during the missions. In general, whenever there are changes in the scenario, the encoder space will be updated so that the policy can adapt to the changes and can make changes in their plan. So in the video, we can see that the UAV UGV team, they are adapting to the changes in the scenario. The teams are getting changes, and the team adapt to the new changes during that scenario. And as a summary, we are presenting a reinforcement learning framework for the cooperative routing problem. And it outperforms the baselines and adapt to the different settings. And the major limitations are the consideration of fixed UGV road network and the greedy assignment between UAV and UGV. You can get the paper by scanning the code, and we can meet at the poster session, and I can take questions. Thank you.
Questions for the speaker? Okay, as people think about it, one question I have for you is how much computational gain did you observe by using a learning-based method, and especially compared to an optimization-based method?
Yeah, so in the learning-based method, it depends on how you are, how the decoder is decoding. So there are 2 methods, we can do sampling-based decoding and we can do greedy-based decoding. So the greedy-based decoding is faster than the sampling-based decoding, 10 times faster, and On the other hand, the sampling-based decoding, it can give you better performance, but takes a little bit of time. If you compare that with the heuristic baselines, the sampling-based decoding will be like 10 to 20 times faster based on the problem size and distributions, and the greedy-based decoding will be more faster than the sampling-based decoding.
We might have time for one quick question, if there is any. All right, if not, let's thank the speaker one more time. All right, next up we have influence of static and dynamic downwash interactions on multi-quad rotor systems by Anup Kiran and colleagues.
Hi everyone, I'm Anup Kiran from Brown University, and today I'll be presenting our work on the influence of static and dynamic downwash interactions on multi-quad rotor systems. Quad rotors are widely used for various applications, including search and rescue, aerial docking, and collaborative transport of objects. Across all these diverse applications is the need to characterize aerodynamic interactions, as that informs the allowed proximity of these vehicles near other objects and aerial vehicles, enabling better decision-making for close proximity flight. Conventional approaches in multi-robot settings circumvent downwash by establishing a collision avoidance robot volume due to unmodeled aerodynamics. So our goal is to characterize forces, moments, and velocities acting on a pair of quad rotors. So we performed this experimentally by using load cells that are mounted statically on a pair of quad rotors, providing bounds on the forces and moments as functions of horizontal and vertical separations. In the far field, we can see that thrust equates to the horizontal hover thrust, but as we approach closer separations, there is a monotonic decrease in thrust. We also noticed that when quad rotors are offset horizontally by 2 times the arm length, there is a destabilizing pitching moment. In addition, we quantify velocity to sub-millimeter resolution by using lasers to illuminate seeded tracer particles in the flight environment to capture 2D velocities, axial velocity u in the z direction and lateral velocity v in the x direction. As we extract velocity profiles downstream, we observe that the individual rotor jets merge and downwash transitions from non-uniform profiles immediately below the rotors to unimodal profiles downstream. So this allows us to classify the flow into near field and far field regions based on the merge point. So beyond the merge point, we observe that the maximum velocity, Umax, happens at the center of the jet, aligning with the centerline velocity, decaying in magnitude linearly as we go downstream. It is evident that the downwash jet grows and expands wider downstream of the jet, as we can observe here for the half-width of the jet. Further, in the far field, once we normalize velocity profiles downstream by the corresponding centerline velocity and the half-widths, we notice that the measurements agree well with theoretical predictions based on turbulent jet theory, showing that this really nice data collapse, forming a closed-form representation of downwash flow fields. We expand our work on spatial influence by investigating temporal interaction. The video here shows Crazy Rail, an acceleration mechanism with downwash impacted quad rotor mounted with a load cell to acquire forces and moments and an encoder to record positional information. It's capable of performing interactions at varying frequencies, amplitudes, and minimum separations at the closest interaction point. So we notice that this allows us to modulate these key parameters, obtaining separations and velocities as functions of time. So we average data over multiple interaction cycles and quantify the effect of the interaction velocity, as you can see by the figures here. So here the black dots represent data from the static interaction presented earlier, and the error bars indicate the standard deviations across trials. The trend from static tests reappear for dynamic tests, but we have further insights on approach and retreat phases here. So you can observe that for the static configuration, we have a much broader range of thrust over separation, whereas for the offset configuration, we have a much narrower range. We also, once we look at the pitching moment, we can observe that it comes down to net zero for static configuration, whereas for the offset configuration, we have a decrement in pitching moment as the separation increases. So to reiterate our key contributions, this paper quantifies downwash effect, providing an open access experimental data set for model development and control that is accessible using the QR code here, and more details can also be found in the paper. For mission planning and safety of multi-robot systems, the proposed operating influence bounds can help inform awareness of these effects as functions of spacing between the vehicles. In addition, we also provide an algebraic reduced order model for the downwash velocity that's computationally lightweight so that it can be implemented on board. Future work will focus on physics-based control for close proximity flight in multi-robot scenarios. To learn more about our work, please stop by poster 52. Thank you for your time.
We have time for a quick question. All right, I'll ask you a quick question. So do you think any of your results would dramatically change if you start accounting for multiple robots as opposed to thinking of downwash from one robot on the other? Are there going to be interaction dynamics that get complicated when you account for multiple robots at the same time?
To make sure that I got it right, are you referring to the fact that if we use different quadrotors, does it change?
So instead of having one quadrotor on top of other, if there are two quadrotors on top of one, how do you think this would change?
That's a good question, yeah. So if we have configurations where there are additional quadrotors, I'm sure that will affect the inflow, and the inflow velocity would change as a result of that. So we'd have to model interactions for that case, which is what the current work is focused on. So the scaling part of it, yeah.
Okay, let's thank the speaker one more time. So before we break for lunch, I request that you stay back. There is a couple of important announcements will be made.
Hey folks, super quick announcement from our local chairs.
Hey everyone, during lunch this building is going to be closed, so do not leave your belongings here. And for the restrooms, there are two options. So that green labeled place is currently where we are. And then the red labeled part is where we are going to have lunch. So if you keep walking in that direction, okay, this is not showing the full map, but there is the other building just next to the lunch place. It's called Taper Hall. There are restrooms there. And similarly, if you are near the posters or if you are near this building, on the other direction, there is the student union where there are again restrooms. Yeah, enjoy the lunch.
Yeah, maybe we should get started.
2 or 3.
All right. Hello, everyone, and welcome to the first session in the afternoon and the second session at this conference on manipulation. We have a really exciting lineup of speakers presenting really cool works in the domain of manipulation. My name is Dinesh Jayaraman. I'm one of the area chairs. I'm an assistant professor at the University of Pennsylvania.
And I am Andrea Bobu. I am the other area chair for the session, and I'm an assistant professor at MIT. And we'll start with the first presentation. The paper is called Dexterity Gen, Foundation Controller for Unprecedented Dexterity. The presenter is Zhao Heng, or Alex Yin.
Hello, I'm Alex Yin. Today I will be presenting our work on the Dexterity Gen Controller, a system for generating dexterous manipulation behaviors that were previously out of reach. Okay. In this paper, we study the problem of achieving useful and dexterous tool manipulation. For example, how can we teach a robot to use a pen to write or a screwdriver to turn a screw? Since teleoperation is widely used today, our initial hypothesis was to rely on pure retargeting-based teleop for data collection. To test this, we built an improved and expressive system called geometric retargeting. However, it does not work. Teleoperation provides a coerced motion prior, but it does not translate into reliable actions. The main difficulty is the sensitivity to contact geometry. Another line of work explores sim-to-real reinforcement learning. While it can learn useful primitives, scaling it to tool manipulation is very hard. It needs accurate object models, carefully designed rewards, and complex learning strategies. While neither approach alone is sufficient, we find their strengths are complementary. Teleoperation is good at producing semantic high-level motions, while RL excels at low-level precision. So our idea is to combine them through shared hierarchical autonomy. teleop or some other policies provide coerce high-level motion, and a learn RL controller refine it into useful and safe actions. We implement low-level foundation controller in this work. We first collect diverse multitask trajectories using RL in simulation and distill them into a diffusion model. At inference time, high-level motion is used as a prompt, and our controller then projects it to fine-grained relevant and useful actions. Here is our pre-training data set. Our key insight is that in-hand manipulation is essentially a sequence of grasp transitions. So we propose to use an any-grasp to any-grasp data set. We use grasp RRT to generate diverse grasp and run RL to produce transition data between them. Then at inference, we can generate complex behaviors by chaining learned motion prompt. As long as the state is covered, the controller can reliably steer the robot to realize that motion prompt. This is our model architecture. A key detail is that the model treats motion as gradient guidance during inference, not as input. This avoids issues with out-of-distribution motion inputs, which break naive goal-conditioned policies. Here are the results. In both simulation and the real world, we show that our method can refine unsafe motions into useful actions. As shown in this real-world video, naive teleop does not work at all, and the user can easily drop the object. With our controller to stabilize the action, the user can successfully manipulate the object over a very long horizon. Our controller works across diverse objects and different gravity orientations, and we refer you to the project website for more details. And we can even synthesize long-horizon dexterous two-use trajectories in the real world, demonstrating both flexibility and compositionality of the learned controller. These articulated objects are unseen during training, yet our model can still successfully handle them to perform long-horizon dexterous two-use. Despite its success, the system still has several limitations. First, we don't yet use touch sensing, and the system fully relies on proprioception. We believe that touch can improve robustness significantly. In tasks like insertion, we find a few bits of vision, such as 2 key points, may help improve control accuracy. Finally, we may also need better prompt design to convey human intent more clearly. So in conclusion, this work shows that even complex tool manipulation is achievable. The key is to combine strengths of different modules through shared and hierarchical autonomy. And we are still early in this journey, but I believe the future of dexterous manipulation looks much brighter now. Finally, I want to thank my incredible collaborators at GUM, the Generalizable Useful Manipulation team at Meta AI. This wouldn't have been possible without their support, and thank you for listening.
Thank you. Questions from anyone? Okay, no questions that I can see. Okay, well, I have a question. You mentioned that one of the limitations was the prompt design. Can you speak a little bit more about that and give us some examples of what failure cases you saw?
Okay, I think the issue is about how many bits you are going to feed into the system. So in some cases, we may just want to feed only a few bits, such as plug in that tool tip into the screw and do some screwing. And we do not want to really use complex finger motions to prompt that. So there is some trade-offs here. So only feeding few bits of information can make this system very efficient. But in that case, you may need to design a very task-specific controller because you have to engineer that specific task reward. So there is a very awkward dilemma here. Yeah.
Thank you. Any other questions? Yes, question here in the front.
Yeah, thank you for this incredible work. I have a question. If you train on any grasp to any grasp, how do you learn to grasp a tool in the first place? Like you don't hold anything and then you grasp it.
Oh, so our model does not consider pre-grasp phase, and it only operates when you have firmly grasped the object.
Yeah, so if you want to pick it up, then we cannot do that, right?
Yes, after it's firmly grasped, we can enable this controller.
Okay, thank you.
Okay, thank you very much.
Thank you.
All right, next up is the second paper of the session. Han Zhang will present DO Glove, Dexterous Manipulation with a Low-Cost Open-Source Haptic Force Feedback Glove.
Okay, good afternoon, everyone. I'm Han, the first author of DO Glove. Today, I'm excited to present DO Glove to all of you. So what is DO Glove? It's a low-cost, open-source, haptic and force feedback glove designed for teleoperation and dexterous manipulation. With DO Glove, the human operator could teleoperate the dexterous hand to perform force-aware manipulation tasks. For example, in this video, the operator is teleoperating the lip hand to squeeze condensed milk onto slices of toast. Since we've installed force sensors on the robotic hand fingertips, and thanks to our force feedback system, the operator can actually feel the actual forces at its fingertips. So this allows them to precisely control how much condensed milk is squeezed, more on one slice, less on the other. So how did we make it? We actually designed DO Glove with a few key goals in mind. First, it had to be affordable. Actually, all parts of DO Glove can be sourced for under $600 US. And second, it had to be easy to build. All parts of the DO Glove can either find a 3D printable or find in off-the-shelf components. So ideally, everyone could replicate it. And third, it had to be functional. DO Glove offers 21 degrees of freedom for motion capture and 5 degrees of freedom for haptic and force feedback. It operates at over 60 Hertz, enabling smooth real-time control. So we carefully designed its kinematic structure to align the actual human hand, which could provide both comfortable wearable experience and accurate motion tracking. And the modular design of finger and joints uses a cable-driven pulley system to transmit the torque from the servo to the fingertip for force feedback. And we also installed the linear resonant actuator, which is LRA, at the fingertips to provide vibration-based haptic sensations. So thanks to the rigid connection of the glove, we can easily compute the fingertip position via forward kinematics, then map back to dexterous hand via inverse kinematics. This actually results in accurate motion action retargeting. So for haptic and force retargeting, we install a one-dimension force sensor on the dexterous hand fingertips. And the force reading will then map back to the DO Glove fingertips. We carefully design and choose threshold to determine when to activate or deactivate haptic or force feedback. And to evaluate the effectiveness of DO Glove, we actually conducted a user study. As you can see in this video, several participants who has no prior experience using DO Glove, and we asked them to wear eye mask and headphone so they can only rely on feedback from the glove. So for basic object pairs, all participants can easily distinguish between them. However, for challenging object pairs, we found that force feedback is actually more sensitive to differences in softness, while haptic feedback is more sensitive to the differences in sizes. So this actually supports our combination strategy, as I mentioned before. We also tried DO Glove in different experiment settings. For example, in this experiment, the operator is asked to open its finger, let the carton rotate but not fall. In other words, they need to rotate the carton for at least 45 degrees and then insert it into the bucket. So during this experiment, we found that combining haptic and force feedback actually can increase the task success rate and reduce the average completion time. We also use DO Glove to teleoperate dexterous hand, collect demonstrations for imitation learning. As you can see in this video, the training policy actually achieves relatively high success rates when evaluated autonomously. Yeah, that's all for me. The project is fully open source and the tutorial is available. Just feel free to check our project website, do-glove.github.io. Thank you for listening.
Thank you, Han. Do we have questions from the audience for the speaker? I see one hand right there in the front row, in one of the middle rows. Yeah.
So will us be able to try it on the poster session?
Sure, I'm at the poster 58. Feel free to reach out to me and try this.
Okay, thank you.
Yeah.
I saw another one there. Yeah.
Hello. Hi. It's a very impressive talk. I have a question about your design choice of adding a small tactile sensor on the fingertip. How would you compare that with doing joint level force sensing? Would that be easier, make the hardware more compact?
You mean compare adding?
So either adding a force sensor at the joint or use motor current as a source of force reading?
I see. For the open source project, if you want to a lighter mechanism, the better solution is to use the servo and use a simple cable-driven. Actually, it's a bi-direction cable-driven pulley system to transmit torque from the servo. So if you use other transmission mechanism or other sensors, it will just increase the weight and make the mechanism very, very complex.
Okay, cool. Thank you very much. Very good design.
Thank you.
All right. Thank you. Thank you. Let's thank the speaker once more.
Thank you.
Our third paper is Dexonomy, synthesizing all dexterous grasp types in a grasp taxonomy. And the presenter is Jia Chen.
Hi. Okay. I'm Jia Chen from Peking University. I'm going to present our work, Dexonomy, synthesizing all dexterous grasp types in a grasp taxonomy. Our work studies the problem of static dexterous grasp synthesis, assuming a 3D object model is known. So you might wonder, reinforcement learning can already handle dynamic dexterous grasping, so why should we still care about static grasp synthesis? Well, if you take a closer look at current learned policies, you'll notice that they tend to use almost the same grasp pose for different objects. They lack the diverse and human-like grasp types described in the grasp taxonomy, such as the lateral grasp, tripod grasp, and so on. Even for static grasp synthesis, generating such diverse poses remains a significant challenge for previous methods. Most existing methods for static grasp synthesis optimize force closure metric using either sampling or gradient-based optimization, but there are two big challenges. First, contact events are non-smooth and vary a lot. Some methods randomly change contacts which suffer from high randomness, others fix the contacts on the fingertips. Rarely. Second, the optimization landscape is highly non-convex, especially for complex object geometries. As a result, previous methods often suffer from inefficiency, poor convergence, and high sensitivity to parameters. Our work tackles above challenges with a novel pipeline. The key idea is leveraging human templates to handle non-smooth contact events and combining global sampling with local gradient to handle the non-convex landscape. We start from a human-annotated template that defines hand-drawing angles, contact points, and normals. Importantly, we only need one initial template per hand and grasp type. Then we densely sample and optimize the object pose in parallel to match the hand contacts specified in the template, keeping the hand fixed. Next, we refine the hand pose in a physics simulator to improve contact quality with the object now fixed. Finally, we build new templates from successful grasps to guide the next round of synthesis. Our method generally works for any grasp types, objects, and articulated hands, all with the same parameters. The synthesized grasps are physically plausible, contact-rich, and penetration-free. Our pipeline is also highly efficient. We can synthesize millions of grasps per day. On screen, you can see examples of our synthesized grasps for different types in a grasp taxonomy. The synthesized robotic grasp is shown in the center. It closely matches the human reference grasp displayed in the upper left. Our grasps are also contact-rich and penetration-free. In contrast, previous methods struggle to generate many of these dexterous grasp types. Here are some examples of the same grasp type applied to different objects. Despite the complex object geometries, our methods still produce high-quality results. We also support a wide range of robotic hands, including 6 commonly used types. Using our novel pipeline, we build a large-scale dataset to support research in type-aware dexterous grasping. The dataset contains 9.5 million grasps over 10,000 objects, covering 31 grasp types. This dataset enables the training of a type-conditional grasp generative model. Given a single view point cloud and a grasp type ID, the learned network predicts a target grasp pose. We then use motion planning to generate a trajectory and execute on a real shadow hand. Our real-world experiments achieve an 82% success rate across 13 diverse objects and 12 different grasp types. To further support semantic grasp annotation, we also develop a UI that requires minimal human effort. The annotator only needs to make some clicks, and our algorithm automatically synthesizes valid grasp for desired object regions in just a few seconds. Thanks for listening, and welcome to my poster for a discussion.
Thank you. Any questions from the audience for this paper? Yes, over there in the middle, back. Excellent throw.
Thank you for the talk. I was wondering how accurate should the object model be so that we can use these models? Can a point cloud work? Or it should be more accurate, like a URDF or something?
No, we use object mesh.
So whatever our inputs are, we should convert it to the mesh and then use this model, right?
No, our synthesis pipeline needs the object mesh as input, and after we generate a large-scale data set, we can learn a network that only takes partial point cloud as input.
Thank you.
Okay.
Okay, thank you. One more question there, over on the right.
Thanks for the talk. One of the questions I have is like for your different grasp taxonomies, how do you deal with a hand that has 3 or 5 fingers if you just have as an input a particular taxonomy?
Our algorithm requires an initial template, and you can annotate different number of contexts in the initial template, and then.
So that's an input to the network?
No. This is used in the synthesize pipeline.
Okay, thank you.
Okay, let's thank the speaker one last time.
For the next paper in this session, we have 2 presenters, Jianlong Ye and Kei Wang. And the paper's title is Dex 1B, Learning with 1 Billion Demonstrations for Dexterous Manipulation.
Okay, we present Dex 1B, Learning with 1 Billion Demonstration for Dexterous Manipulation. Data scarcity is a key challenge for Dex hand imitation learning. Previous work like Dex GraspNet and RPYM both leverage simulation to generate million-scale demonstration data sets. But in our paper, we try to generate billion-scale demonstration data. So the question is, how can we generate billion-scale demonstration data set? And the key point is that we should generate it in a very economical way because we don't want to spend 1 month's time for the data generation. And then the next question is, do we really need the billion-scale data set? Is the effort to scale up to the next level worth it? Here are current techniques for data generation. The optimization-based technique, like Dex GraspNet, is efficient, but still too time-consuming for the billion-scale data generation. And the IL-based method still faces the diversity issue. Instead, we try to leverage generative models, which is not only scalable for large-scale data generation, but can also achieve higher diversity. By using the generative models, our proposed Dex 1B benchmark contains 1 billion high-quality and diverse demonstrations. However, in order to leverage generative models for data generation, we still face two challenges. The first challenge is the feasibility. The success rate of a generative model is usually lower compared to deterministic model because of it needs to model a more diverse distribution. To address this, we add a geometric constraint during training. Specifically, we add an approximate SDF loss, which can not only encourage the contact, but also can prevent penetration between robot hand and object, just like this figure shows. This makes model the distribution more physically plausible. By adding the SDF loss, the performance of our proposed model improves significantly in the benchmark. The success rate of our model outperformed previous SOTA by 20% without sacrificing any demonstration diversity. Also, we observe that scaling up the data consistently improves the model performance, which is not only helpful for the data generation process, but also validates the importance of our proposed dataset scale.
In addition to feasibility, the generative model also faces a key challenge in diversity because the model tends to interpolate instead of extrapolating when sampling new actions. So we address this issue by adding local conditions. To be more specific, we have a CVA model which takes hand parameters and local object points as input, and it conditions grasping poses on local object point features extracted by PointNet or SparseConf, so that we can sample new actions on out-of-distribution points. This is our overall pipeline. We first obtain a seed dataset by optimization, and then we train a CVA model to generate a larger dataset in order to guarantee the quality of the data, we use simulation to do filtering, and we also do data debiasing across objects and grasping poses. The curated data is then used to do further training, and so that we can get more data and we can train a better model. And these are demonstrations we generated in simulation for grasping task, and also for the articulation task. And this is our zero-shot sim-to-real transfer demo. We can do continuous grasping for nearly like 30 different objects, which validates our model's object generalizability. And thanks for listening.
Thank you for the presentation. Are there questions for the speakers from the audience?
Have you noticed distribution differences between the generated grasps and something you could do, like if you were doing manually collecting data? What does the distribution look like?
You are saying if we just sample data with the policy? There's no feedback, okay.
The object types and grasp types, if you look at sort of the distribution of the data, what does that look like?
Yeah, we have collected 1 million object asset, and the object type matters for the dataset generation. We try to increase the diversity of the object assets. We collect object from the object-verse dataset. Yeah.
We have time for one more question. There's one at the back right there.
Oh. All right, can you name 3 objects like you fail? Like you cannot grasp, like real objects?
Yeah, like a phone. Yeah, like an iPhone, because the iPhone is very thin. Another one, basically the small objects, any idea? Needle. Yeah.
Okay, so is there a phone in the sim training?
It is, but it's still very hard to transfer to a real.
Okay.
Yeah.
Thank you.
That's all that we have time for. Thank you, speakers. Yeah.
Next paper is demonstrating multi-section item picking at scale via multimodal learning of pick success, and it's presented by Chair Wang and Sumedh Anand Santake.
Hi everyone, I'm Cho Wang.
And I'm Sumedh.
We're from Amazon Robotics, and we will talk about our paper demonstration, a demonstration of multi-section item picking at scale. We have multimodal learning of pick success. So let me introduce you to Sparrow, one of our robots in Amazon warehouses. Sparrow works with individual items. It has to pick an item from a tote using multiple suction cups and place it into another tote. Most of the things that you can buy on Amazon.com may show up here. So this is a very interesting and challenging problem to deal with. Some of our items can be heavy, some are deformables, others are transparent or have weird shapes. Pick failures can be costly. You don't want to drop an item on the floor because they can block other robots. So we want to pick them fast and with a very high success rate. So we work with a critical large-scale industrial setting with large item diversity, high success rate, and speed requirements. The evaluation is performed over a large 430,000 picking item data set. And previous state-of-the-art models at Amazon require expert design features. This model is unique in that it is the first one that operates over a raw multimodal data, and it can outperform the previous solutions without expert features. Our paper provides extensive ablations that reveal key insights. For example, pre-training on multimodal data can improve downstream tasks. Our model is shown here. On the left, we see RGB depth, pick location. These are the image modalities and also the pick features. We have an encoder that is pre-trained on multimodal data and then fine-tuned to predict a score between 0 and 1 for each pick candidate. And here you can see on the right-hand side a heat map of where to pick on the item. And that allows us to select the best place to pick. After pre-training on multimodal in-domain data, the encoder can now reconstruct all modalities with just a small amount of patches, or it can reconstruct other modalities with just a single modality. And being trained on these multimodal data will also improve performance. This approach can outperform the state-of-the-art model that we presented at RSS2025, given this large data set. The demonstrated approach doesn't need any expert features. Again, these are required for the previous solutions. Additionally, our model also works on different settings. For example, partially occluded items or packages instead of individual items.
We study pre-training and fine-tuning from the lens of modalities and ask, does including additional modalities like depth and semantics, both during pre-training and fine-tuning, help? The answer is yes, and the benefit from multimodal pre-training persists even if only RGB is used for fine-tuning. We ask what data is also most useful during pre-training, and we find that including in-domain Sparrow station data is critical for reconstruction to provide an absolute improvement of 6%. Here are some failures on Sparrow. The shadow model encourages with high success rate on these failure grasps, while our approach discourages these grasps. In a real warehouse test, over the course of a week, our model performed 17,000 picks. Compared to the best baseline, it reduces picking multiple items by about 2%, missing to pick items by about 38%, and reduces dropping of items by about 41%. This produces a significant cost reduction if deployed on our entire fleet. You can find way more ablations in our paper, and we have a live demo in our sponsor booth. We encourage you to come check it out, bring items that you think are challenging for manipulation, and we'll try and grasp and place them. So it's an open world picking demo. Feel free to stop by. Thank you so much for listening to us.
Thanks so much.
Thank you for the awesome presentation. Okay, any questions from the audience? Over here in the middle. front floor.
Hi, thank you for your talk. I see you're using like suction cup grippers. How can you grab like porous surfaces like a sponge?
Yeah, so apparently suction cups are only able to grasp like some items, it's actually like a large amount of items, but it cannot deal with everything. So in our case, we do have other projects that work on different types of grippers. But we do find suction grippers to be the most often the most robust and the fastest to use in an industrial setting. So it's very interesting that in warehouse we use them very often, but in academic setting we see more often pinch grabber and, for example, like humanoid hands.
Thank you.
Okay, thank you. I think we are basically out of time, so let's thank the speaker again.
Thank you.
Thank you.
Our next speaker is Shili Yi, and they will present Vibe to Move, in-hand object reconfiguration via fingertip micro vibrations.
Hi everyone, I'm Shili, and I'm glad to present our work, Vibe to Move, in-hand object reconfiguration via fingertip micro vibration. In this work, we explore how we can use vibrations to manipulate objects within a parallel jaw gripper with only gravity, without extrinsic contacts. Reconfiguring objects within a robot's grasp is crucial for dexterous manipulation. In-hand manipulation often requires complex hand design or environment contact. Our goal is to develop a simple and hardware-light solution that enables a reliable in-hand object reconfiguration on parallel grippers, even when external forces are not available. Our key insight is to use vibration to change the friction force to induce object motion. Like you might have seen a cell phone moves when it's vibrating. With this idea, we embed vibration motor into gripper fingertips, and then we can break static friction and allow control sliding of the object within the grasp with high control frequency and fast response. We formulate our problem as follows. In a vertical plane with a non-planar object held by a parallel jaw gripper via robot fingers, given a go robot pose in the object frame, how to obtain the robot input U that can drive the finger to the go pose in this frame. We derived the motion model based on the following assumptions. First, the robot is making patch contact with the object. The system is quasi-static. An object has to slide when there's vibration, and object has to stick when there's no vibration. With force-torque balance of friction and gravity and linear surface model, we can obtain the following equation that can predict the object motion iteratively. Here we show a simulation of object trajectory, and we can find there are only two kinds of motion, rotating motion or translation motion along the gravity, shown on the pink and blue region on the left. Translation motion along the direction of gravity only occurs when the center of mass and contact center lie along the gravity vector. In other cases, the object tends to rotate around the contact center. With these observations, we find that translation only happens towards or away from the center of mass, which means trajectory that doesn't pass center of mass is not feasible. So we propose our heuristic approach with 3 stages. First, center the object by rotating the finger so that the COM is right above the finger. Then start vibration until it's centered. The second stage is positioning to the goal by rotating finger so the goal is right above the finger. Then start vibration until it's at goal position. Finally, we need to adjust orientation by rotating the finger and start vibration. As for details for controlling, please refer to our paper or come to my poster. We deployed our experiment using a KUKA robot with modified fingertips. We tested 6 different objects with 3 types of surfaces. Here we show some demos of the experiment. To be noticed, on the top right video, the yellow object has a non-homogeneous friction properties due to its textured surface from 3D printing. And our system still can handle that. For each object, we randomly chose 10 goal poses, and the final results are shown in the table and the figure. We obtained less than 6 millimeters of position error and less than 2-degree orientation error. Thank you, and I will be at poster 58, and I'm glad to take any question.
Are there questions from the audience? One in the front row right here.
Thank you very much for the nice talk. I have a question regarding the gravity. So how much are you limited by the considering gravity here in motion, in hand motion?
Yeah, actually, that's the only actuating force to the whole system. So you have to have a gravity or kind of acceleration in some way. So we assume everything is in the vertical plane, and that's to maximizing the gravitational force.
Any other questions? Okay, I have one. Do you have to make the assumption in your work that the coefficient of friction is uniform over the entire surface? And are there good ways of handling when there are non-uniformities?
In our assumption, we don't really require that, because in the vibration assumption that whenever you stop vibration, it's going to stop. So that makes the whole motion discretized. So we don't rely on the even distribution of the friction property.
I see. Thank you. That's all that we have time for. Let's thank the speaker once more and proceed to the next.
Next paper is Sim and Real Co-Training, a simple recipe for vision-based robotic manipulation, presented by Abhiram Madhukuri.
Hello, everyone. My name is Avi, and today I'm excited to present Sim and Real Co-Training, a simple recipe for vision-based robotic manipulation. Recent advances in robot foundation models have primarily been achieved by training on a large set of real-world trajectories. While these models have shown impressive capabilities, we're still far from being able to reliably deploy them in the wild, and it is unclear if continuing to scale up real-world data will get us there. Simulation is a promising tool to bridge this data gap, offering 3 key advantages: scalability through automated data generation, visual diversity through techniques like domain randomization and generative simulation, and task diversity, facilitated by large language models and procedural generation. Past work have made notable progress in leveraging simulation data through techniques like domain randomization and digital twins. However, these methods either require extensive manual tuning or are not as effective for more complex real-world tasks. Thus, in this work, we explore the alternative of co-training on a mixture of real-world and simulation data. Our study specifically spans 2 distinct domains: a panda robot in a real-world kitchen and a GR1 humanoid on a tabletop. From here, we look at 3 different types of data sets for co-training: real-world data, which has perfect alignment with our target task, but is expensive to collect; task-aware digital cousin data, which are simulated data sets designed to closely mirror real-world task semantics, but can have significant differences in terms of dynamics, individual object instances, and scene composition. These data sets offer scalable automated data generation, but face the sim-to-real gap and may require some tuning in simulation. And finally, our multitask prior simulation data, which we define as any task-agnostic pre-existing data set. These data sets offer high diversity, immense scale, and immediate out-of-the-box usability, but may have minimal alignment with the downstream real-world task. Putting everything together, our co-training pipeline first starts with the real-world task and some prior simulation data. From here, we collect a small amount of data in the real world, and in parallel, create and collect a small amount of data in our digital cousin environment, upscaling this data via DEX MimicGen. In the final stage of our co-training pipeline, we co-train on a mixture of real-world and simulation data, sampling our simulation data according to alpha, our co-training ratio. Diving into our experiments, we look at 11 different tasks with varying behaviors, such as pick and place, door closing, and pouring. In testing different data compositions, we find that policies co-trained on a mixture of real-world, prior simulation, and digital cousin data outperform policies only trained on real-world data by approximately 38%. Remarkably, co-training with prior simulation and real-world data alone results in significant improvements in performance. Co-training with simulation additionally improves policy generalization to novel object entities as well as novel object poses. In investigating key elements for successful co-training, we look at the impact of different co-training ratios, which represents the probability of sampling simulation data in each training batch. We find that tuning this value has a significant impact on performance, with the best results coming from substantially sampling more simulation than real-world data. Aligning camera poses also matters. Co-training with misaligned cameras reduces performance by 18%. However, perfect alignment isn't necessary, as we can get good results with approximately aligned camera poses. Finally, even as we scale up real-world demonstrations in multitask settings, we find that policies co-trained with simulation data consistently outperform their real-only counterparts. This underscores that co-training remains beneficial even in data-rich settings. In summary, through our work, we have established a systematic study on co-training with the real world and simulation data, demonstrated the effectiveness of co-training with simulation data, and provided a simple set of recommendations to reap the benefits of sim and real co-training. In the future, we look to co-train highly multitask policies on longer horizon tasks and seek to investigate the underlying mechanism which allows co-training to be effective. For more information, please visit our website. Thank you.
Thank you for the great presentation. Any questions from the audience? Over there in the back in the corner on the right.
How do you go about making sure that when you're evaluating the performance of these, that you're actually measuring what you think you're measuring? Like, how do you know that these tasks are actually indicative and informative of what would happen in a more broader range of settings?
Yeah, so one of the emphases of our experiments were like having like diverse tasks. So I'd say like maybe 5 or 6 of them were like pick and place, and then we had some with like digital or articulated object manipulation. We had some pouring. So we tried to make the tasks as diverse as possible to give a good idea that it would be generalized. And another thing is like we had two distinct domains, so the humanoid and the panda, and we made sure to like make them as distinct as possible, right? So different training protocols, we use different types of encoders, different batch sizes, etc.
Is there some procedure or something that you could point to say, here's our advice on how to do that?
Just to clarify, advice on like how to...
How do we make sure we're actually measuring what we actually want to measure in these sorts of experiments and benchmarks?
I'm a little unclear. So we just rolled out the policies in the real world and compared the success rates across the real and the co-train policies.
I'll come to your poster.
Okay.
Thank you. That's all the time that we have. Let's thank the speaker once again.
All right, our next paper is CORD VIP, Correspondence-Based Visuomotor Policy for Dexterous Manipulation in the Real World. Can we welcome the speaker, please?
Hi, everyone. My name is Jiaming Liu, and I come from Peking University. In this video, we introduce CORD VIP corresponding-based visual motor policy for dexterous manipulation in real world. Is the video beginning?
We might have trouble with the video.
Okay. For the introduction of our motivation, recent advancements in 3D-based imitation learning have shown promising results in the field of robotic manipulation. Utilizing point cloud and voxel as representations to help robots preserve 3D environment and reason about the spatial relationship in our real world. And 3D imitation learning exhibit higher learning efficiency and enable the policy to capture the inherent relationship in the manipulation process with fewer examples. Okay, at the same time, it also better captures the intricate spatial relationships and 3D geometric structure, which are crucial for dexterous manipulation. So we also have many challenges in this field. However, obtaining high-quality 3D representation represent two key problems. The first one, I think the quality of the point cloud captured by the single-whip camera or single-whip depth camera is significantly affected by factors such as camera resolution, positioning, and occlusion caused by the dexterous hand. And the second problem is the global point cloud lacks crucial contact information and spatial correspondence, which are necessary for fine-grained dexterous manipulation tasks. So in this way, to address the limitations, we propose Core VIP, a novel framework that constructs and learning correspondence by leveraging the robust six-dimension post estimation of objects and robot. So in detail, we first introduced the Interact Aware Point Cloud, which established correspondence between the object and the hand. Specifically, we employ the triple SR to generate the initial object point cloud and foundation pose, and also use the foundation pose to estimate the 6D pose of the object. In parallel, the hand point cloud is generated based on the robot state. They are combined to construct interact aware point cloud, which demonstrated robust to viewpoint variations. These point clouds are then used for pre-training stage or pre-training strategy, where we also incorporate object-centric contact map and hand-arm coordination information, effectively capture both spatial and temporal dynamics. The pre-trained encoder is subsequently integrated into an imitation learning framework to facilitate tasks in dexterous manipulation, and we conduct 4 real-world real-world tasks. Okay, for our experiment, our method demonstrates exceptional dexterous manipulation capabilities with an average successful rate of 90% in 4-based real-world tasks, and achieved SATA performance into advanced contact-rich tasks, surpassing other previous baselines. Core VIP also exhibits superior performance, achieving higher accuracy with fewer demonstrations. Okay, besides the remarkable effectiveness and efficiency, Core VIP also showcase excellent generalization and robustness to different environments like such as lightning conditions, unseen objects, and different scenarios. Next, for the ablation study, we conduct serious experiments on 4 real-world tasks to evaluate the effectiveness of the different components in our method. These findings emphasize the necessity of both contact and coordination information to achieve robust manipulation. We also find that PointNet outperformed than other encoders in the successful rate, and fine-tuning further enhance the learning of the downstream tasks. That's all. Thank you.
Are there questions from the audience? I see one back there. Yep.
Oh, yes, thanks for your presentation. And I saw that a lot of tasks in your paper is like some atomic task, right? So I wonder if it is possible to handle more complex tasks like long horizon tasks.
Yes, thank you for your question. where real-world tasks were indeed conducted on for automatic tasks. That said, but we believe that our method have the potential to handle some complex tasks, like you said, long horizon tasks as well. For example, now we just build the coordination between the object and the dexterous hand, but we also can enable or construct the coordination between multiple objects and to improve the spatial and temporal relationship in the long horizon task.
Okay, thank you. But how to maybe model the a relationship between different objects? So.
Okay, I think if we have the task language instruction, we can follow the instruction to capture or obtain the foundation pose from each object step by step, and also we can use large visual language model to help us.
All right, thank you.
Okay, thank you.
I'd also request all the audience to maybe keep the questions short and maybe save follow-up questions for the poster. Let's thank the speaker once more.
And our final paper of the session, Complementarity-Free Multi-Contact Modeling and Optimization for Dexterous Manipulation, presented by Wanjin Jin.
Hello, everyone. My name is Wan Xin. I'm presenting my work, Complementarity-Free Contact Modeling and Optimization for Dexterous Manipulation. So the contact-rich dexterity is still a fundamental challenge in robotics. The state-of-the-art has been dominated by learning methods, but they are data expensive and generalizable, less generalizable. The model-based method seems like far behind. Why? Mainly because of non-smoothness of the contact physics and also the hybrid decision space. The recent effort trying to smooth the contact dynamics and also developing efficient planning algorithms. They are effective, but they are slow. I'll take a different perspective. I believe that the contact-rich manipulation can be solved by really fast model-based planning with high successful rate and scalability. All we need is a new context model, which is extremely efficient for planning, but also physics capable. Capture the complexity of contact dynamics. So the classical physics engines are based on the complementarity-based model. So what that means? That means that if you two objects in potential clearance, either their contact forces and distance has to be zero. They cannot be negative. Therefore, in physics engine, at each time step, the physics engine needs to solve a complementarity equation for next velocity v plus and the contact forces. The tricky part is complementarity also can capture the Coulomb friction model with a friction cone. So the complementarity in general is NP hard. Then Anitescu said we can convexify it. The secret is trying to modify the sliding motions. Instead of constraining sliding velocity in the tangential plane, and Anitescu said we can constrain the sliding velocity on the edge of the dual cone. Then at the end of the day, your contact dynamics is a convex optimization, which is good for simulation. But if you think about planning, right, you have to add another layer of optimization on the top of this optimization-based dynamics. If you look at the whole equation, and then the complementarity appear again. So I think about we really need to get rid of the complementarity entirely from planning. So we need to think about the new contact dynamics. So we propose a complementarity-free contact model. I'm trying to avoid the mathematical derivation here, but the key trick I played is if you look at the dual problems, all you need is trying to replace that quadratic matrix with the diagonal matrix K here. Then you end up with an equation which can directly give you the velocity after the contact without solving any optimization and complementarity problem. So actually, it has a very straightforward fixed interpretation. If you look at the term, there are two terms. So the first term is the velocity that is contributed by the non-contact forces. For example, the gravity, the external forces. And because of this velocity, the object or system will penetrate into the dual cone, and then we can also calculate the penetration depth. Then the second term said that we need to correct the velocity to prevent it from further penetration by generating a spring-like contact forces. If you recall the previous K matrix, actually it is stiffness in the dual cone. And we can prove that the Coulomb friction law is automatically satisfied in this equation. And the biggest advantage is that if we there is almost no computational overhead in simulation. If you put this model into your planning algorithm, there is the complementarity free. You don't have to deal with the complementarity anymore, just like you are playing with the smooth dynamics. And compare this model with the other contact physics engines. There are two takeaways. First of all, our model, in terms of fidelity, our model is in the middle ground between the complementarity-based model and the convex optimization-based model. And surprisingly, our model is very similar to the behavior of the Majorco, except our model is a little bit soft because of the spring handling of the contact model. And most importantly, we apply this model in the contact MPCs to solve a variety of challenging problems. And our contact implicit MPC can run 100 Hertz with a state-of-art successful rate and overall accuracy. There is no learning at all. I also try to test it on the hardware because we recently got the very quick tracking system. This is this is a dynamic frictional reorientation objects. The RMPC can run 70 Hertz, very robust. For more information, please come to the poster and check out our code. Thank you.
Thank you for the great talk. Any questions from the audience? Yes, over here in the middle. Here, middle, ground floor. Oh, okay, that works too.
Thank you. Very impressive work. I wonder how can we get the state estimation you get from simulation to the real world for the tasks like Rubik cubes, reorientation stuff?
That's a great question. So all we need is, first of all, we need information about the object pose and everything, every geometry in the scene. And we recently, I'm trying to sell another work. So we recently developed a work which trying to learn, basically trying to build this similar real to same to just use a variant to infer everything very fast. We can go up to 40 Hertz. That work is called twin track. Yeah, thank you.
And now we can have the question in the middle.
Sure, yes, very impressive result. I'm very curious, how does the efficiency of your method change when you deal with multiple items and in cluttered? Because the example looks like the contact dynamics is not too complicated. So how would you generalize to more complicated cases?
So I've never tested like the test beyond this, beyond like this. But I don't think the number of contacts is a problem for this model because there is no complementarity at all. So it's just like I guess it's linear to the number of complementarity. That's it.
Oh, cool.
Number of complementarity. Yeah. Sorry, number of potential contact. Sorry. Yeah.
I see. Yeah. I'll probably read your paper. Very
Thank
impressive.
you. Thank you.
Okay, let's thank the speaker. And this concludes the second session on manipulation. And don't go anywhere, because we're about to have our keynote speaker for today, Professor Trevor Darrell from UC Berkeley, who's going to talk about efficient and robust multimodal intelligence from blind models to 4D representations.
All right. Hi, everyone, and welcome to the second keynote of RSS2025. So in the first keynote on day one, we discussed questions about bioinspiration and minimality of intelligence. Today, we're going to switch gears and talk about richer representations and more complex reasoning. In particular, we're going to discuss opportunities and challenges at the intersection between language, computer vision, and robotics. Towards this goal, it's my absolute pleasure to introduce today's keynote speaker, Professor Trevor Darrell. Trevor is professor at UC Berkeley, where he founded and co-leads BEAR, which is the Berkeley Artificial Intelligence Research Lab. In his previous life, he got his PhD and was on the faculty at MIT. I guess we'll forgive him for moving to Berkeley at some point. That's fine. So Trevor's superpower has been to spot transformative trends long before they go mainstream. He was doing neural net and convolutional neural net before he was cool, and has been thinking deeply for a long while about unsupervised learning, generalization from limited examples, as well as multimodality, among other things. Trevor's work has been deeply impactful. I will just mention a couple of examples here. In 2014, with his team, he released the Café deep learning framework that quickly became one of the most popular platforms for deep learning, in particular in computer vision. Eventually, Café merged into PyTorch back in 2018. As another example of impact, Trevor's work has been recognized with 3 Test of Time awards, including the prestigious Longy-Higgins Prize at CVPR. Beyond academia, Trevor is an advisor to several companies, including startups acquired by Intel, Yahoo, Google, and is also co-founder and president of Prompt AI. In his work, Trevor has been thinking deeply about the question of grounding, meaning in the real world, and trying to understand a variety of machine learning models, from blind models that are just exposed to textual data to truly multimodal models. So if you want to learn more about the future of multimodal models in robotics, and you want to understand if large language models are going to solve robotics, stay tuned, sit tight, start taking notes. Now, without further ado, let's welcome Professor Trevor Darrell.
Thank you so much. It's really wonderful to be here at RSS. And that was the perfect length introduction. All the AV problems got solved while it was underway, so very nice. So I'm really happy to talk to you today about the state of AI, from vision to language to robotics, and maybe even back. And this talk will have 3 acts. The first will be a brief discussion of some philosophical points, maybe even some existential points. And then maybe the longest chunk of the talk will be some cool new tools in vision and learning and a little bit of robotics that I think are really relevant to robotics. I think you'll find them hopefully interesting. And then maybe at the end I'll try and make a conjecture about where I think learning and robotics is going. And we'll see if you agree with me or not by the time I get there. So let's get straight into the philosophy, maybe even the existential philosophy. So, well, which is it? Is vision going to dominate robotics, or is robotics going to dominate vision? It's like, which field is going to absorb the other? It seems like that's what's on everyone's mind. Like, top of mind is, why are all the vision people moving to robotics, right? You've seen it. I mean, it's crazy, isn't it? Or is this actually true? I mean, is this a change, or is it not a change? That's what the next few slides will ask. I mean, why does it seem like all the vision people are moving to robotics? Is it because there's still some unsolved problems there that, you know, Meta and OpenAI can't solve? Maybe. Scary demos. Everyone wants to have the humanoid robot on their team, not on the other guy's team. Or maybe it's just that you guys still have conferences that fit into an auditorium like this at this scale, which is really wonderful. I don't think I've been to such a nice, well-run, highly informative conference like this since before COVID. So I think we're just coming here because you guys are having more fun. And it seems like there's a little bit of existential angst in the air. At least I was here yesterday for the panel, and I saw that the esteemed panelists were worried that ICRA was going to be acquired by CVPR, and RSS was going to be acquired by NeurIPS. So clearly it seems like the roboticists are a little bit worried that they're going to get absorbed by the vision and learning people. But let's argue the other side for a moment. Maybe vision is a part of robotics, or, I mean, well, first of all, we all want to have this shiny new humanoid robot, right? Humanoid robots are all the rage and the craze. This is clearly the output of some Gen AI rendition of a futuristic humanoid robot that's just going to come out of Tesla or one of the other startup companies, right? Is that where this image is from? Anybody remember where this image is? Anyone recognize this image? maybe this is actually robot vision, right? So like this, I'm going to tell you this is computer vision. This image right there, humanoid robot is computer vision. And my evidence is this, which is the cover of the textbook that I used as an undergraduate and a graduate student. And the oldest people in the room used as well. Berthold Horn's Robot Vision textbook. I'm just here to tell you, you may not believe there was a time where this was true, but roughly, before 2000, whatever, computer vision was a subset of robotics in the eyes of many. Maybe that's still not true, but here's my evidence. The 2004 curriculum of machine vision was robot vision, and there's not any robotics in this course, okay? But still. So I wouldn't worry too much, and I think what we're seeing is actually the return of a harmony between topics that were sort of separated for many years, and the new methodologies that we've finally arrived at are allowing vision and robotics and learning and even language to kind of all be the same thing. And I think that's really cool. Vision was robotics until actually vision took a side detour based on social media, and internet vision was defined, and then all of computer vision became internet vision. And then suddenly now we're rediscovering that it's robotics as well. So that's kind of fun. So that's the first bit. I guess I wouldn't worry about which field subsumes the other. I would just constantly go to the one that has the best parties and best conferences. So now the next little piece of philosophy to begin the talk with. I'm going to actually not really talk about vision in the sense that we're going to not have any pixels for a while, maybe, or robotics. And I'm going to tell you something that really surprised me over the last 4 years, which is that I came to the realization that like LLMs, which I'm just going to say are blind LLMs, I mean text-only LLMs, which is what most people mean when they say LLM, they're visually grounded. That should probably not make sense to you, because it wouldn't have made sense to me when I first started thinking about it. What did I think of these LLMs when they first came out, like 3 or 4 or 5 years ago? Of course, they're amazing at text stuff, and they maybe are. I was always very much in favor of vision and language, in contrast to some of my colleagues in the computer vision community. But I always really probably secretly thought of it as a way to communicate, because eventually I wanted a vision system to do something for a person. And maybe or a robot, and maybe language was or natural language was a good space to do that. I wouldn't have thought they were grounded. Like I wouldn't have thought that something that's only ever seen text can really understand the spatial layout of this auditorium, or the relative properties of objects in a scene graph, or color relationships, right? You would have just been kind of laughed out, or you would have ended up gathering around some alcohol and trying to recreate a Chinese room argument or a stochastic parrot argument in the modern incarnation. I hope you're familiar with those references. If not, you should look them up. But you know what? I really changed my mind. And let me show you a few results, like a series of 3 or 4 results, starting with some work that's like 4 or 5 years old, 3 or 4 years old right now, that seems to suggest that these LLMs actually are grounded. And I'm only going to go so far as to talk about the vision. I'll leave the robotics side of grounding as an exercise to the listener. I don't really have any evidence on that yet. But it started with a paper that is about 4 years old, or we started about 4 years ago, on something pretty banal from a roboticist point of view, unsupervised grammar induction, okay? Kind of very much a language person's language problem. What we looked at was how did LLMs improve multimodal, unsupervised grammar induction? And grammar induction is a cool classic NLP problem. You got a sentence, can you figure out how to parse the sentence? And why does it, and it's unsupervised, we want to do this in a purely unsupervised fashion. And this is all subsumed to some degree by LLMs. That's going to be the point of this line of reasoning. But why does unsupervised parsing imply grounding? Well, because if you're going to actually do it right, to know how should I parse the phrase, a cat sipping from the cup on the table, I need to know exactly who's doing what to whom, or who's on top of what, right? Is the cup on the table? Is the cat on the table? Are they both on the table? All sorts of things. And so the theory went, maybe 2002, that actually people have been doing it from text alone forever. They started to use pixels, which was something really cool to me as a multimodal vision researcher. And they won a slew of award-winning papers for like 2 or 3 years by adding, they had a whole history of methods called PCFG methods that they would run with text, and they added pixels to it, and they saw their performance shoot up, as you'll see on the next slide. The adding pixels really helped, which made sense, because where else do you get the knowledge of spatial relations if not by looking at the image? So my students at the time, and also this is work with Dan Klein and Jitendra Malik, their students as well, they were all like, hey, we want to get another award-winning paper. We see the writing on the wall, we can add LLM features to this, and probably multimodal features plus LLM features. We're going to definitely crush that leaderboard. All these best paper award papers in NLP had basically added vision to unsupervised parsing. So then we added LLMs, so we thought our numbers were going to go through the roof. They went through the roof. It was great. Except, actually, turns out when we did that, if we added pixels back, it hurt. And so that started, and that's why this paper took a long time to write, because we ended up basically writing a slightly contrarian paper than the one we set out to write, where it turned out that if you actually have LLM features, in other words, text features that are trained at scale, adding pixels didn't help with this basic kind of grounding. So that's the first point, and it's just a table result because it was an NLP paper. But then maybe it would have ended there, but there were a couple other things that now convinced me these LLMs know something about the spatial world. And indeed, in particular, scene graphs. Like, I really wouldn't have concluded 4 or 5 years ago if you'd asked me, do text-only LLMs, can they generate scene graphs? I'd be like, what are you talking about? That doesn't make any sense. But then let me show you the following work, which was about 2 or 3 years old and was kind of during the heyday of open source diffusion models. They were coming out fast and furious. Stable diffusion had just come out. And like Stable Diffusion was pretty amazing. I mean, not as amazing as today's commercial products, but you could ask for a gray cat and an orange dog on the grass and get an image like this. And so these diffusion models were really, really good, but they weren't really, really good at attribute binding and, if you will, scene graph, generating a scene graph that really was consistent with the prompt. And so like, where's the orange dog in this? And like spatial layouts weren't good. Now, I think state-of-the-art models today, because they probably have machinery like I'm about to present that we published 2 or 3 years ago, 2 years ago actually. But anyway, back then, just simple diffusion models trained as Stable Diffusion was trained didn't have it. And my favorite was ask this model for a man in red when it has the opportunity to dress the woman in red. It would never do it. It would always put the woman in red and the man in blue. It's not. And so that's Stable Diffusion. What one of my students did, which was really cool, it was actually just prompt hacking almost. This was back when you thought that academics couldn't compete. But academics can compete when it's sort of test time engineering, and this is what this was. Turns out that the text-only LLM that's just lightly prompted could solve attribute binding. It could generate a scene graph, right? You could actually ask a text-only LLM, hey, what's the rough layout of the scene, and what should be where? And actually, please just generate some boxes and some text attached to boxes. And the LLM would definitely know that airplanes are in the sky, boats are on the water, parts and wholes have certain relationships, and it certainly wouldn't have no trouble at all saying the man should be in red and the woman should be in blue and one should be here and the other should be there. And so that's what we did. We had this LMD system which would first generate a scene graph in a purely text-only way. And I just had to be surprised, like, where's all this knowledge coming from? I don't know. These LLMs have read a lot of text. There's a lot of text that's been written about the physical world. It's obviously not grounded in the way we used to think of grounding, but it might be, you know, isomorphic to representations that are grounded or something like that. So this is why this is the philosophical part of the scene. Anyway, once you have a scene graph, you can then generate really beautiful images as you can imagine. There's plenty of technical tricks for doing diffusion that's conditioned on a scene graph. We've probably published 2 or 3 in my lab alone over the last 3 or 4 years. And once you do that, no problem. Now you can get a gray cat and an orange dog on the grass, and you don't get any problem with orange golf balls. You can get spatial relationships and numeracy. You can get a man in red and a woman in blue. And you can do this in video as well. Again, these results are 2 years old, so obviously this is not competitive with state-of-the-art commercial video generation. But back then, this is what you got out of state-of-the-art methods that said, you know, a raccoon on a barrel. You got everything but the raccoon on the barrel, but of course we could get it, and so on. The objects should be flying in the right direction, or a brown bear dancing with a yellow Pikachu. This was pretty cute. The previous one didn't work very well. So I'll be done with the philosophy soon. I've just kind of gone through, wow, I didn't think you could do parsing. I didn't think you could do scene layout. I didn't think you could do motion graphs. There's no way it's going to do human pose. Human pose is a vision person's vision problem. But wait, maybe, hold on. How do we get, when we're trying to understand multi-person interaction, people holding hands, people interacting, people kissing, people doing things people do together, where are you going to get that prior knowledge? Well, I mean, go to a classic mocap lab and hire actors to come together and scan them like one does. I mean, that's still in the small sample regime. I mean, there's probably only hundreds or thousands of data, of n equals 100 or 1,000 in data sets like that. At the very most, sometimes it's even a dozen. So actually, this is where you go to a large language model, ask them questions about what's the typical hand-holding behavior, how do bride and groom interact, what is the spatial relationship of the hands, for a particular yoga pose, what are the characteristics that are necessary? And now we're going to blur it a little bit. You could either just do only pixels, or you could do pixels plus a little bit, you could either do only text, or we could have a VLM. But our results in the paper that I'm referring to now also show results for pure text as well. But you can basically use the VLM that's really extracted all this prior knowledge from text about relationships of people and ask it for part relationships and body relationships and get constraints that become useful for 3D pose estimation. If you're interested in that, that was just presented at CVPR, pose priors from language models. Okay, so that's the last of the philosophy for today, that I really wouldn't have thought that blind LLMs are actually visually grounded. And I've only talked about vision, but I'm pretty sure that there's some robotics juice in there as well. I can't believe that every detail of grasping has been written in textbooks, but maybe there's something about moving around the world at a course level that's actually in text. So who knows what signal's out there, and we'll see if we can get it. So that was the first act, philosophy. Vision is robotics, robotics is vision, and you never know what you can get out of a text-only model. And now I want to jump into some really cool vision results that have been coming out of my lab and of my colleagues at Berkeley, and show you a series of 4 methods that we have on dehallucination, active vision, attention for attention, imagination, and humanoid mimicry. Let's start with dehallucination. So hallucination is a big problem for anyone who's thinking about Gen AI. The upside of these models is they have so much prior knowledge, so much common sense. This is what's amazing about them. But then they also often hallucinate, and we don't really want that when we're asking to have a description of what's in the kitchen, especially if you have a robot that's trying to go in there and clean things up or pick things up or manipulate things. You might think I could take a VLM and ask it for a caption, And in this case, you really would want a caption that wasn't like telling you what should be there. You want to know what's actually there. And we've all seen models that hallucinate, and when captioning this image might talk about the fridge because the prior is so strong there. And in fact, if you actually look at the difference between the influence of the prior, you'd see that actually fridge should be downplayed and toaster should be enhanced. So how do we use this signal in a LLM? How do we answer a question like describe this image and get, and it starts with the boy is sharing his umbrella. And conveniently, this image is really small. I should probably blow it up, but now I thought about doing that the last time I gave this talk, but then I realized it's actually good that you can't see it either, because that's the way the VLM is. Like, what exactly is the boy sharing his umbrella with? Well, I'll represent it's actually a cat. Right? And you didn't expect that. You probably thought it might have been a dog. And a typical VLM would actually generate the word dog there. I mean, later on in this talk, I'll talk about high res, and so we could solve this with the observation. But let's just try and fix the prior for a second. Interestingly, a lot of these same VLMs, you can ask them for the caption. It'll give you a caption. But then if you say, wait, is there actually a dog in there? Sorry, is that actually a Frisbee and a dog? The same model will be like, oh, no, I'm sorry, sir. No, I made a mistake. It's obviously not correct. Right? We've all seen that. And this is post hoc verification. That's kind of maybe one of the standard mechanisms in the field right now to deal with hallucination, but it seems awfully expensive. And why can't we do it at the same time? Why can't we have the benefit of check your work, retrospect token, or retrospective thinking approach kind of in real time as we're running inference? And that's what we've done in a project called Reverse, retrospective verification and self-correction. So in a nutshell, while we're doing inference, we're going to generate a special token that is the check your work token. And if it fails, we're going to backtrack immediately rather than have to do a whole pass. So we're kind of simultaneously doing the test time agentic thinking. And I'm going to show you mostly results in vision, but I'll show you a little bit of robotics at the end. And I think there's no reason this won't work in robotics. And I hope I get to do it before you guys do. But we are working on it. But I'd love to see other people take this idea as well. So we're going to generate the next token. This boy is sharing his umbrella. What we would like is for it to generate a token like girl, but then immediately realize it's screwed up. Like the other half of the brain is going to say, nope, that's unconfident. So an unconfident token is going to be generated. And as soon as you see the unconfident token generated, it controls the generative decoding process, which then forces a backtrack through that last noun phrase that was generated. And another thing gets generated. Oops, that's still unconfident. And then finally, it generates a token that, here, cat. And it looks good. It is confident, according to this idealized token that I'm presenting to you, on a rainy day. Well, how do we actually get this to work? Well, the same way we get everything in LLMs to work, we're going to create a training set that has those properties, and we're going to fine-tune a model. So it sort of sounds hard to believe until I just show you how we did it. Get a data set. Data set has a lot of different questions. Take, for example, there's a data set that has an image like this and a question like, what's on the back of the bus? And it says, the back of the bus has an advertisement. And of course, you can find all the noun phrases in this thing. And so you can just syntactically add spans that have the confident token around things that are actually in the image if you have a data set with ground truth sentences, which we do. That's good. Wait, now I can probably, how do I create the negative examples? Well, let's just hallucinate stuff. Let's go take the ground truth and mess with it. Let's go put an object that we know is not there. There actually isn't a window at the back of that bus. Or in these examples, let's change the number of baseball players, or the style of the airplane, or the author. I can easily do that. And now for those, I have training data, and I'll put unconfident tokens. So now the model is going to actually predict confident or unconfident kind of as sort of a detector on the fly to check its work, right? And obviously we shouldn't train on the undata, just train on the confident data. And once you've trained a model, inference goes like this. It'll start generating tokens. Of course, it'll generate a noun phrase, and it'll generate the corresponding confident or unconfident token. For things that are actually in the image, it will say, yep, it's confident, keeps going. And then suddenly it generates, and all along, we're monitoring the probability of the next token that's going to be generated as being the unconfident token, right? And for the first part of this generation, it's all basically 0. But then suddenly when it generates something that the prior really believes in, adding this mechanism for a retrospective sort of thinking, a retrospective thinking token, suddenly realizes, wait, the model's now pretty unconfident because it checked the next token might just be unconfident. So then we'll backtrack. Let's do it again. It's an advertisement. The odds that the next token is unconfident is low, and so on and so forth. And we can either use rejection sampling or query rewriting to get it to not keep repeating the same thing over and over in an endless loop, if that was a concern to you. So I'll refer you to the paper if you want lots of results and details. But here's some 2 qualitative examples where baseline methods would hallucinate a bunch of other people on the field, because I guess it's kind of rare in the training data that there's just one person kicking a soccer ball. Or when you have a cat and a desk, there's often a bowl, so that model hallucinates that. And on various benchmarks, this reverse method outperformed various baselines. It's tunable, so you can trade off expressivity and groundedness. And as I said, we're working on the robotics applications of it. I'll just go forward and tell you, not only can you directly apply it to robotics, but we have a related paper that I didn't have time to talk to you about false premises in vision. When someone asks you to ground an object in the scene, but it's not there, what do you return? If I ask for the green bus, but there's only a yellow truck in the image, you might want to just say, hey, did you mean that yellow truck? And so we've been exploring the same thing in robotics and VLAs, where if the user gives it an instruction that doesn't quite refer to what is in the scene, we have our model actually back off and ask the user what they actually meant, and not just go ahead and blindly do the wrong thing like a lot of traditional VLMs or VLAs will do. We call this instruct, verify, and act, and we're building this on top of our earlier larva model for VLA. And again, we create a data set where we manipulate it with incorrect examples and train the model to back off and handle the method appropriately when the object's not actually there. And at least compared to the baseline method, it obviously does a lot better. And so we can handle these really somewhat toy synthetic examples even when there's really bad specifications. I'm not going to, in the interest of time, I'm going to move forward and just refer you to this work if you're interested. There's actually 3 more cool things I want to show off before I close with the future. I think actually, if anyone has been in the field long enough, actually visual attention isn't just a thing in transformers. It's something that human vision systems and robot vision systems use all the time to sense the world. And we need more of it. And that's why I'm calling this part of the talk attending to attention, because we're really building attention in transformers to allow foveation in larger format images. So the 2 different kinds of attention that are out there in the world. If we're going to continue the progress that we've seen in VLMs and VLAs, we're probably going to have to scale beyond 224 by 224 imagery. It just doesn't make sense, right? But if we try and scale in a vanilla way, I probably don't have to argue to convince you very much that it's not going to scale well. Life's going to get very complicated if I want to have voluminous page-long captions that describe every little detail in the image. But let's not do that. Let's do what any vision person from 20 years ago would have said is obvious, which let's actually have attention. Let's attend to salient things in the scene and only decode those tokens at high resolution. So the caption that relates to the sailboat name in this example, is really could be attached to the fovea, the foveated image, the foveated signal on this. And if you go forward with the same kind of contrastive learning and LLM recipe, the scaling is quite favorable, like 2 orders of magnitude better than the naive approach. So how do we do this? Again, we have data. There's plenty of data of high-res images. And you can take those high-res images and find small regions and caption them, either, even automatically, to be honest, using a multimodal LLM. And so you can get images like this, where you have a big image, you have regions that have been selected, foveated, and like detailed captions on all of those images. And this is the recipe that you need, or these are the ingredients that you need to train the following kind of model, which is a model that's going to start off looking at a low-resolution feature of the image. It's then going to look over the entire image and see, given the prompt, or even given no prompt at all in a bottom-up fashion, the prompt is a top-down fashion, what's the salience score? What pixels would be useful for this, answering this question? And let's go pick those pixels out and decode them at a higher resolution. In other words, let's go just actually run our visual encoder just over the patch of the higher resolution image and provide that to a transformer. So our PS3 model can process 4K by 4K images today, maybe even more in the future, and learn where to look, where to attend to answer important questions. And I think this is obviously going to be super valuable for robotics. We're working on that as well, but hope to have it out soon. So this is a collaboration with our friends at NVIDIA, and so we've integrated this in the Vila family of models called Vila HD. This was also a CVPR paper, a spotlight talk, I think, or a spotlight poster. And it has the following, it yields a multimodal LLM with the following structure. It starts off looking at low-res tokens, and then you get like a question. And then a token is generated that causes the model to decide where it should look next and go get high-resolution tokens, or tokens that are derived from higher resolution patches that are decoded into tokens. And then the question is answered. So if you're trying to say how many men are sitting on the dock, it goes and looks in high res, it attends to, it sort of puts a fovea on the dock and then answers the question. This thing has really, this model has very nice scaling properties. I won't go through this slide or this slide in detail, but they're all in the paper. And obviously it's an NVIDIA paper, so it's got a wall of text results that are very strong. But I will talk through this slide, which is a cool video application. I think sort of autonomous driving is one of the use cases. And you'd like to have something where you could ask questions about scenes, like what exit is coming up, or where does the exit lead to? And you want the model to be able to actually answer questions kind of in real time. And so our model can do that. It's highly accurate and fast. And if you ran the baseline systems, I guess it's kind of trivial given how I set up the talk, but obviously you can either have a model that's accurate but too slow, so you probably have to stop or miss the exit, or it's not accurate enough and you, again, might miss the exit. So attending to attention, cool stuff. Take a look at our CVPR paper. Another CVPR paper I want to point to also that was a best honorable mention for a best paper called Navigation World Models. It was really pushing the state of the art in pure data-driven world models, vision-based, conditioned on some navigation actions. This is kind of really the bleeding edge of like pure data-driven, video-based world models. And let's see where we are right now. So I think to this audience, I don't need to explain the idea of if I could predict future images, why it's valuable. I can kind of imagine a future, if I have certain actions, how will the image change? And then I could roll it out and do an MPC and decide what actions to take if I had such a thing. There's a lot of work on this in many recent years, shown on the slide, Katarina's work. I saw her earlier today. And so we've been looking at this and we wanted to do it specifically for visual navigation, which is a subset of action. let's see if I can imagine the future as I move through an environment. And you might say this has been solved by SLAM, and it sort of has been solved by SLAM, but it's interesting to see how it can also be solved by diffusion models. And essentially completely end-to-end trained diffusion models that only get video as input with an aligned action signal. And then we can either have translation or rotation or time be the action and figure out how to get to a goal image from a model that's been trained in a certain domain. So we can use it for planning. The key idea is, of course, a diffusion transformer, but the key idea to actually make it work is a conditional efficient diffusion transformer. There's lots of data that's relevant here that we exploit. And the key novelty in our CVPR paper was an efficient diffusion transformer that allows computational scale that previously was unavailable by not requiring an n-squared connection to everything in the video. That's obviously not going to work. When you're denoising the next frame, you probably want to pay full attention to the previous frame or the current frame that you're denoising, but only summarize the influence of previous frames, so you have just tokens for the previous frames. And that's much more computationally efficient, sort of linear in time with regard to the number of frames than the prior methods. And so you can follow trajectories and see where you're going to get. And it works pretty well in known environments. Again, it's sort of like an end-to-end differentiable way to do SLAM plus NERF or NERF if you wish. And you can, we have very limited experiments that show selecting controls. It works in unknown models, but I don't, these are, you could call these negative results or positive results, and I wouldn't know how to argue with you. It's just still kind of weird in unknown environments. But you can obviously use it for planning, and in a certain kind of benchmark, it outperforms all the baselines when using this sort of nomad approach of rendering for different actions and deciding which one to pick. Again, if you're interested in that, take a look at our CVPR paper. I want to have time for the last two parts and some questions. So humanoids are really exciting, and a vision person really wants to train with all the data in the world, all the videos of people moving around. And when you have something like the humanoid form factor, it's really appealing to imagine, as many people have articulated, that you can go out and learn from human videos, or you can have sort of natural teleoperation by just walking around and having the humanoid follow what the people have been doing in that environment. And so that's what we've been doing in a recent work that we called Video Mimic, with all the co-authors you saw there, including all the lead students. Anju, Jitendra, and Peter are also involved in this work. And so we built a humanoid controller that's environment specific. It can watch how people have interacted with an environment and recover the geometry of the environment and learn how to maneuver and walk in that environment. We call it contextual control. Visual imitation enables contextual control. So, and so here we have a controller that we can tell the robot what direction, kind of joystick control to move it around, but based on where it is in the environment, it'll have different actions. It'll walk up the stairs, or if we push it onto the bench, it'll actually sit on the bench. So we have a really environment-conditioned control policy that we learn by really state-of-the-art body pose tracking and 3D motion recovery. That's very exciting, and using a lot of the best methods from Anju's lab and her collaborators. So we can track the people in different settings and environments, reconstruct the scene, and then retarget the motion, and then train a simulator and do real-to-sim with or without domain randomization and get it to work. So we start with monocular video input. We reconstruct and track the human body in the environment, both with 3D simple reconstructions and 2D pose detection. We recover purely monocularly the 3D point cloud of the scene We don't use navigation world models here, don't worry. And have the 3D structure that we convert to a mesh. And we align all these together. This is pretty heavy engineering in this particular part of the talk, but it does work, and we get these really beautiful animations. We take the aligned human in the world, or multiple humans in the world. We then retarget the motion of the recovered people to the robotic morphology and kinematic structure. And then we now have the equivalent robot walking through the environment as an imitation signal that we can use and train, we can learn a reward function to train an RL agent. So here's the kind of reconstruction that we get from watching a person walk through the steps on the Berkeley campus in front of the library, and you can see both the scene and and also the rendered viewpoint from the camera here, and from the actor itself, from the robot itself. So we can learn these generalist policies, starting with different levels of knowledge of geometry. We can train a model that knows the actual height map in the environment. We can train with the root conditioning, and then finally train an RL agent that takes all this into account without, only with proprioception, the height map, and the root direction, not having the underlying joints that are from the mocap. And so here's some more results of this method walking inside the BWW lab building, going upstairs, going downstairs. Slightly drunken walk, but it's kind of cool. Again, up the stairs that we saw before. And now moving backward to sit down, because that's the thing that people naturally did at that moment if you push the object back, and so on and so forth. So if you're interested in this, go to the website videomimic.net, and you can see the paper and even more videos that are exciting. So, okay, now I want to close with a few more pieces of eye candy and computer vision machinery and a conjecture about the 4D future. And I'm really going to advocate that as much as the video mimic work is really cool, I would love to have models that have less inductive bias and are closer to the sort of VLA architecture, pre-training and kind of reward shaping approach. But I'm not very happy with the current set of VLAs. I think the pre-training approach that current VLAs have, it just seems like it's really hard to scale. And I think we see this also in pure vision. We haven't seen video models that seem to have the kind of juice that text models have. Maybe we just need 2 orders or 3 orders of magnitude more video than Google has. I don't know how we're going to get that. But we haven't seen this sort of aha moment that we've seen with text, and we keep seeing with text, even with smaller, where this sort of compositionality and reasoning appears. So how might we get that in vision? Let me first, before I talk about the future, indulge me for a little bit more of the past. I think it might be useful to kind of look back a decade and remember how we got to where we are in robotic visual learning. Obviously, I was very excited about the work that Sergey and Chelsea, Peter and I did on the early end-to-end visual motor training models. These were, I think, transformative and cool, but they were so tiny. I think as Chelsea herself mentioned yesterday, the number of parameters here were so small, this thing was actually so brittle. So move to foundation models, says many people. And I think that's where the field moved to, or is moving to. At 2016 to 2022, we started to see larger and larger scale pre-trained models trying to be the visual front end or the behavior engine of these models, either supervised with ImageNet data or unsupervised with MAE, or we called it MVP when we applied it to sort of ego motion manipulation data. I'll do a gratuitous self-referential shout out to the work that Deepak and Alyosha and I did in 2016 called Context Encoders, which really was one of the first visual prompting or representation by reconstruction. This was in painting, but I think we also had extrapolation results, so it kind of next token prediction is similar in some sense, not exactly. But now, of course, everything is transformer-based, LLM-based, often next token prediction, except for the diffusion aspect. I think the relationship of MAE diffusion and next token prediction is such a cool finding the generality there. It's a whole hour-long talk in and of itself. But I think, but even at this scale, I think that the lineage of where we are today still doesn't quite deliver what we want for vision or VLA generalization. We haven't seen the sort of magic generalization that the text people had, and what might we need to do to get there? Well, I think even at this massive scale, pixel-based features seem to ignore the most important problem in computer vision. And maybe people who recognize the Horn textbook can tell me what are the 3 most important problems in computer vision. Anyone remember? At least according to Takeo Kanade, any CMU old-timers? Well, correspondence. That's the number 1. What's the number 2? Also correspondence. What's number 3? That's like real estate. And so we think it's probably the most important in robotics. I think I'm going to argue that 3D point clouds and trajectories are the future. I'm going to call this 4D. And so we want to have representations that go beyond pixels. There have been a variety of approaches that many folks, including myself, have tried, but they still haven't quite worked. I think it's going to be very exciting. Right now, the bet I will make, or the bet I'm making, is that these 4D representations, which are 3D point clouds with implicit correspondence over time, seem to have juice that's very cool. We call them 4D particles. And there's been a lot of new methods in computer vision in the last year or two that have extracted these representations. I'll refer to this work that came out of Anju's lab, but there are others as well. And not only is it a monocular kind of super slam that reconstructs the 3D point cloud, but it also has correspondence. Every point is mapped through the identity of every point is maintained throughout the entire video. That's very cool. And if you want the latest version of this, there's a paper we just released called Star Track that is a collaboration also with Anju, Michael Black, and a number of our students, which has some of the state-of-the-art performance and these kinds of 4D representations where you can take an input video. Sometimes the video loads and sometimes it doesn't. Yes, good. You can reconstruct every frame in the sequence using a feed-forward network of the Duster class to reconstruct the scene, reconstruct every frame in the scene, and maintain the identity of all the points over time. Again, this just seems like a capability that people would have said, you have to have a LiDAR, you have to have mocap, you have to have 1,000 mocap markers on your scene to get this kind of data. It's sort of crazy. But now we can get it for free for in the wild videos. If you're interested, obviously look at the paper. This is a one-slide summary of the difference between Duster and Monster and Star Trek. I'll refer you to our Larva and especially to our most recent paper called ARMOR, ARM4R. The 4 works as an A in that acronym, or that sentence, which just got published, or will be published at ICML this summer, where we explicitly test the claim that if we pre-train on these 4D point clouds, 4D trajectory clouds, I should say, these 4D particles, that seems to transfer really efficiently. We ran some very small scale experiments compared to what other people are doing, but we got very quick transfer. And it makes sense to me that if I'm doing something in world coordinates, I have essentially what's the end of my hand doing in 3D, that maps very cleanly to an end effector of a robot. So we have we can generate either 2D, or sorry, 3D or 4D particles. 4D particles look like, sorry, I'll try one more time. For some reason, that video isn't running today. It ran a minute ago. Yeah, so if you're in, that's the paper at ICML. We run on Ego 4D. We, off the shelf, just extract 3D representations with correspondence over time. I think suddenly I must have just run out of memory or something, because it was certainly playing earlier. Try and get back to where we were. There we go. It's kind of half working. You can see the colored lines showing the trajectory of the 3D points over time. So take a look at the ICML paper. You can see the results on Ego 4D here. And we pre-train a representation for a robotic learning system that's similar to prior methods. This one's not based on a text-based LLM. This is more just based on a observation action paradigm. But we see much more efficient generalization with these representations that are based on 4D than on 2D representations or instantaneous 3D representations. And I think this is early days in this kind of work, but I'm looking forward to seeing what happens. So that was what I wanted to get through today, and I have 30 seconds left on the clock, so I think I did a pretty good job of hitting the time part of the talk. There was really some philosophy, vision, and robotics and learning are really more similar than not at scale, and I think that isn't decreasing that trend. I presented some really state-of-the-art cool new tools, reverse for hallucination mitigation, PS3 for attention, or foveation, navigation world models for the state-of-the-art in conditional diffusers, and video mimic for amazing system that can reconstruct the 3D world and train a humanoid and human motion in the world and train a humanoid to mimic that, learn from that motion. And I've offered this pre-training conjecture that if you keep an eye on the 4D reconstruction methods, pre-training on that is going to be the most effective kind of pre-training that we'll have. You don't really have to throw out the pixels. You can keep them as well and look at our ICML paper if you're interested in that perspective. With that, I'm going to close, and thank you very much for your attention.
A few questions. Let's see if there are questions from the audience. I see one in the first row here in the middle.
So thank you for the great talk, Trevor. And I think one thing is interesting that we're in robotics is we often don't agree on what is the hard problems. Like seems like people tend to believe the problem they are working on harder, including me. So my question is like, did similar thing happen in computer visions? And why do you think is the case? And what do you think is the hardest problem in robotics?
Oh, hardest problem in robotics, I think is, well, I would defer to you all, but I'm really impressed by all the results I see at all the papers today, but we still don't have a general robot that can do much. And all the humanoids in my lab generally are standing there not doing anything, and they're all on tethers. I guess I'd be really excited to see if next year's generation of humanoid robotic results from my own lab don't have someone holding them and can do something useful and not just do something useful with one part of their body, like locomote, but juggle while they walk and also look at the plane at the same time. Those are hard problems.
So there is one here on the right on the ground.
Thank you very much. I have a dilemma because I have two questions, but I have only one to give to you. So I will pick one that is closer to my research. I'm working with uncertainty and robots from another perspective. And the work in reverse caught my eye. I'm very inspired, and I really need to know more. I'm eager to know more now.
I'll be happy to tell you after the talk,
Yeah,
or read the paper.
But my question to you would be, the first thing, maybe you said it, but I apologize. But is the certainty levels that I saw in one of the examples was only in one of them, right? Is in one of them that the certainty, the tag was certainty?
Yeah. Just this, right now, the model that we put forward and experimented with is just the certainty of generating the untoken.
Yeah, and the others were unknown. Is this only
well, you know, it's an LLM at every iteration generates a distribution over all the tokens in the vocabulary. So it's using that same mechanism.
Okay.
Like it could generate the word the, it could generate the word bicycle, or it could generate the word un. And if it generates the word un, we backtrack.
Right, we're at time, but maybe if there is one last quick question. I see one over there in the middle, main floor.
So if I understand correctly, you're taking video and generating point clouds for the 4D, but that information is contained in the video. So how does this intermediate sort of conversion, you think, really is the key?
Yeah, I mean, you're using the standard learning person's attack, which I also agree with and often use, which is why do we want this inductive bias? If we just had if we had a large enough machine and enough scale, we shouldn't need all these pre-processing, these hand-designed features. I don't disagree, but we've been pushing on this for 5 years, and the video people haven't scored a win like the text people. So maybe I'll take this crutch for now and see if this might work in the next 2 to 5 years. Probably if you're thinking 10 or 100 years out, you shouldn't need this crutch, or it should be emergent. I wouldn't disagree with that argument.
All right, folks, in the interest of time, we'll close it here, but let's thank Professor Darrell again. So we're going to break for coffee. We're going to come back at 4:30 sharp for the next session. Thank you.
Hello, hello. Welcome back, everyone. Welcome to the Control and Dynamics session. I am one of your co-chairs. I'm Andrea Baichi. I'm an assistant professor at Carnegie Mellon University.
And I'm Rob Marnie from the Australian National University. And I'll pass over because you're going first, aren't you?
Fantastic. All right, let's just jump right into it. We're going to start with the first talk, Safe Beyond the Horizon, Efficient Sampling-Based MPC with Neural Control Barrier Functions, presented by Ji Yin.
Hello, everyone. My name is Ji Yin. I'm going to present the work Safe Beyond the Horizon, Efficient Sampling-Based MPC with Neural Control Barrier Functions, a joint research project from Georgia Tech and MIT. Safe controls has always been a difficult task for both humans and robots. In adverse weather conditions, limited visibility gives short response time, leading to more control failures. Unexpected road conditions can also disrupt vehicle behavior, resulting in dangers. While self-driving cars are designed to reduce human error, their real-world deployment remains challenging due to unpredictable disturbances. We need controllers that are robust enough to handle various situations. In particular, we're interested in the VI MPC. This category of MPC methods utilize variational inference to approximate the distribution of optimal control sequences. Optimal controls can then be obtained by Monte Carlo sampling in real time. Compared to traditional MPCs, VI MPCs work for arbitrary forms of cost using general nonlinear dynamics. However, VI MPCs need large sample size, requiring expensive GPUs to achieve real-time control. They are also sensitive to disturbances, and there is no recursive visibility guarantees. To preserve the strength of VIMPCs and overcome their drawbacks, we propose the NS VIMPC. Offline, we train a discrete time neural CBF. Online, we use the resulting CBF to supervise an efficient sampling process inspired by particle filter, which we call the resampling-based rollout, or RBR. The optimal controls are synthesized using the safe trajectory samples generated by RBR. We run simulations using the standard MPPI on an autonomous rally car. A neural CBF is trained using the collected data, and its sub-zero level set is defined as the safe set. The resulting neural CBF recognizes the danger at high-risk corners where the car can easily veer off track. The RBR checks sample trajectories at each time step. If a sample state violates the CBF constraints, the state will be removed and its subsequent control sequence will be randomly rewired to a safe sample state and resume propagation. As a result, the RBR enables VIMPC methods to focus all sample trajectories on safe regions. We instantiate a specific version of NS-VIMPC using model predictive path integral and refer to this as NS-MPPI. We compare the NS-MPPI with the standard MPPI. Our method concentrates all samples in safe regions, effectively avoiding collisions in this simulation. In a drone racing task where the drones are set to fly through a narrow tunnel, we compare the NS-MPPI with the shield MPPI, a robust MPPI variant. In the simulation, NS-MPPI can perceive dangers in advance while accounting for ground effects caused by rotor airflow. Let's take a closer look. Our NS-MPPI method perceives the obstacles beyond the prediction horizon and adjusts the sampling distribution in advance to prevent collision. Shield MPPI, which uses standard sampling strategy, results in a crash. We carried out 2 hardware experiments on the auto rally. In the first experiment, the controllers use an adversarial cost function that rewards collision with track boundaries. The standard MPPI was tempted to crash with the nearest track boundary instantly, and the shield MPPI did only slightly better. The NS MPPI was able to complete laps without any accidents. In the second experiment, we track high speeds to mimic speeding. MPPI, tracking a target speed of 50 meters per second, crashes in the second corner of this track. Shield MPPI is safe for 50 meters per second, but crashes at 80 meters per second at 7th corner. NS MPPI was able to complete laps without any collisions. Thank you so much for your attention. We'll be more than happy to answer more questions and discuss the details of this project in the poster session. Thank you so much.
Questions? We have one in the center, bottom floor.
Hi. In this framework, have you considered perception uncertainty? How do you estimate the state of the vehicle? And since you are trying to stay in track, do you get the lane boundaries, track boundaries perfectly, or do you consider any perception uncertainty there?
So basically, initially we use simulated data. We use the standard MPPI controller in the simulation to collect data and then train to know the control invariant set of the track. That is how we deal with all these constraints in all these simulations, including the experiments. Yeah.
All right, let's take the rest of the conversation out to the poster session. Let's thank our speaker.
Thank you.
Thank you. So it's my pleasure to introduce Kensuke Nakamura and talking about generalizing safety beyond collision avoidance via latent space reachability analysis.
Hi, I'm Ken Nakamura, and I'm really pleased to present some joint work done with Lasse Peters and my advisor, Andrea Baichi. So when you think about robot safety, you might think of really great works like these, where increasingly complex systems are able to stay robust to disturbances and even be quite agile but safe. And this is really due to data-driven methods scaling up foundational principles from safe control. But so far, the focus has really been on collision avoidance representations of safety, where the constraint we care about can often be represented with a simple inequality. But what if we want to represent constraints beyond collisions so that we can have robots that prevent and safeguard tearing, breaking, or even spilling? So for example, consider this robot with 2 camera views interacting with an open bag of candy. If it naively lifts up this bag, we get a safety violation of all the candy spilling onto the table. So how can we use safe control to safeguard and autonomously prevent these failures? Well, we run into a few issues with some key assumptions we often make. For example, what is the state of this system? Not just of the robot itself, but also the deformable bag and all the pieces of candy inside it, which are not always observable. Even if we had such a state representation for this type of system, the dynamics are also extremely hard to mathematically model, and simulating this is still not an easy task. And it's still unclear how we could even mathematically model what we mean by a constraint for this type of safety violation. And so in the absence of a state representation, a good dynamics model, or even what we mean when quantifying failure, how is it even possible to synthesize a safe controller? And the key idea that we take in this work is to leverage the latent space of a learned world model, which allows us to specify hard-to-model constraints and then generalize safe control to applications beyond collision avoidance. So how do we get our world model? We first collect a large, diverse range of data, primarily from rolling out random actions in the environment, but also some small amount of teleoperated demonstrations of both safe and unsafe behavior. And I note here that we do not require any notion of task optimality, just observation action coverage. We can use this data set following prior works in world modeling to learn an encoder, which takes these high-dimensional observations and packs them down to a lower-dimensional latent state, and a dynamics model, which predicts future latent conditions on the robot's actions. With this latent space in hand, we now need to do safety specification. And we pose this as a classification problem in latent space. So look, from these 2 sets of image observations, you can actually easily label that one set is not violating the constraint while the other is. And so we can now encode these representations to the latent state and do classification here to regress these safe or unsafe labels. And with these ingredients in hand, we can now do safety analysis within the world model's imagination. So take, for example, this state. The robot has already lifted the bag, but we don't yet see the candy spilling onto the table. While the failure classifier will not actually label this as an unsafe state, no matter what sequence of actions here that we take, we will kind of inevitably end up spilling the bag. And we can find all such inevitable failure states by offline computing the solution to a latent Hamilton-Jacobi-Bellman equation, which just at a high level gives you a value function whose 0 sub-level set encodes all of these inevitable failure states. And we also, for free, get a safety backup policy. Using the value function and backup policy together, we can synthesize a safety filter in the latent space. So here, I'm teleoperating a robot, and the safety filter is monitoring me and deeming this type of pickup safe to execute, and lets me proceed. If I drag the bag side to side along the table, the safety filter slows me down, but otherwise lets me proceed, since ultimately this will not cause a spill. And finally, if I try to pick up the bag like at the beginning of the talk, it completely overrides my teleoperated actions to prevent me from spilling the candy on the table. We also test zero-shot generalization capabilities of this latent safety filter and find that even with out-of-distribution tabletop backgrounds or color bags of the Skittles, we're able to generalize to dynamically similar bags. Come visit poster 29 if you want to discuss, and I'm super happy to take questions now.
Thank you very much. Any questions? Just checking.
Nice.
So, we have a question just here on the bottom left.
Oh, hello. Yeah, it's a quick question for you is, how do you ensure that your latent space has a proper vector space structure?
So here we kind of just generally hope in a matter of speaking, but in the discrete time reachability case, all that really matters is that the dynamics is bounded so it doesn't jump off to infinity, and that we have bounded control inputs. So there's no other real constraints that we need. It's a quite general framework in theory.
time for one more question if we don't. Otherwise, I think we might thank the speaker. We're tight for time, so thank you very much.
Next up, we have Bridging Model Predictive Control and Deep Learning for Scalable Reachability Analysis, presented by Zheyuan Fang.
Hi, everyone. I'm presenting Bridging MPC and Deep Learning for Scalable Reachability Analysis. For nonlinear high-dimensional systems, it's difficult to synthesize the set of all unsafe states from which system failure is inevitable. Formally, given the failure sets and initial states, each possible control policy will result in a corresponding rollout trajectory, where the minimum distance along the trajectories indicates if failures occur. The safety value function is defined as the best minimum distance achievable by any control. With that, the set of all unsafe states is given by the sub-zero level set of the value function. The discrete time value function can be approximately solved via MPC, while the solution of its continuous counterparts can be obtained by solving a Hamilton-Jacobi-Bellman variational inequality at JBVI. For general high-dimensional systems, the solution is learned using self-supervised learning. MPC is robust, meaning that the unsafe set generated will always cover the ground truth unsafe set. But it's often suboptimal, especially for long horizon problems, and it suffers from slow online inference. Learning-based reachability, on the other hand, provides global optimality with instant inference. But the training is unstable due to the weak self-supervised signals. So the key question is that, how can we leverage approximate reachability methods like MPC to guide and accelerate the learning of accurate reachability solutions? Our key idea is to treat the MPC solution as noisy samples of the value function and refine them using the HABVA residual error. Specifically, given a boundary condition that captures the safety specifications, we aim to learn the final time value function. The high-level idea is that we first generate an MPC dataset with a short horizon to warm start neural network training. We then enter the core curriculum training phase, where we incrementally increase the time horizon where we sample the collocation points for self-supervision. We then combine the self-supervised learning PDE loss with the data-driven MPC loss for robust value function learning. Once we reach the current MPC dataset time horizon, we use the learn value function as a terminal cost for MPC to generate more data over a longer horizon and refine data within the current horizon. We repeat this process until we reach the final time zero, where we have the converged unsafe sets. We evaluate our method on a 13-dimensional quadratic system. Our method reduces the potential unsafe volume from 28% to just 6% after verification. And our verified unsafe volume is even much tighter than the learned unsafe volume of neural CBF without verification. What's remarkable is that these results are achieved with only 3 minutes of data generation, really highlighting the data efficiency of combining approximate reachability solutions like MPC to accelerate the learning of accurate reachability solutions for those complex dynamical systems. We also demonstrate scalability on a 40-dimensional publishers Weber system, where we achieve a significant improvement using ATK samples. Lastly, we apply our method to F-110's autonomous racing car, where both the agility and complex boundary conditions make it extremely challenging. All other methods completely fail, while our method learns the extremely accurate unsafe sets. And by integrating the the verified value function as an online safety filter for imitation learning policy, our methods achieve an average speed of 7.5 meters per second without collision, while all other methods collide within 25 seconds. In conclusion, we combine the relative strengths of MPC and deep learning to robustly synthesize the globally optimal safety value function for high-dimensional complex dynamical systems. Future directions include explore important sampling strategies to generate more informative MPC datasets and tackling uncertainty. That's the end. Thanks for listening, and please stop by poster 45 if you are interested.
Questions? Oh, we have one in the bottom right-hand side.
Thanks for the talk. So my question is, do you need to trade off between the exploration and exploitation, like in RL? Like, do you need to randomly explore in the state space? Seems like your current method depends on the quality from your MPC collected trajectories.
Yes, yes. So great questions. So right now, this PIM-based reachability analysis is more focused on where you can randomly sample those states within a whole space. So it's unlike RL, which you basically deploy in for those quadruped systems, where most of the random states are useless. So for this type of applications, we're still moving toward there. I would say important sampling is a good way to do it, and we may need a nominal controller to start exploring the state space. But right now we are more focused on this racing navigation kind of examples where like you can directly sample from the whole state space.
So thank you very much. So we'll thank the speaker. And the next talk will be by Ante Maric, and it is on distilling contact planning for fast trajectory optimization in robot air hockey.
All right, hello everyone. My name is Ante Maric, and I will present our paper on distilling contact planning for fast trajectory optimization in robot air hockey. So robot air hockey is a highly dynamic setting in which we control the system through impact between the mallet and the puck. And in order to play it successfully, we need to take into account different types of uncertainty and different types of constraints in real time. So it's been used as a benchmark for quite some time for both model-based and learning-based approaches. And our system kind of combines both. So on the state estimation side, we take kind of a model-based approach. And then we formulate contact planning as an optimal control problem, which we distill using behavior cloning for rapid online recovery of the contact plans. And then on the lower level, we execute the trajectories using MPC that ensures all the constraints. So for the dynamics model, we model the contact model as a piecewise linear Gaussian with three distinct modes. So one mode where the puck slides freely on the table, and two reflection modes where the puck reflects off the wall or off of the mallet. And we parameterize this model from data, and this allows us essentially to predict the trajectory of the puck and to estimate the probability of the puck entering the goal, as well as the expected velocity of the puck at the goal line. So we then take those two values and construct an optimal control objective as basically a weighted sum, which we can then tune by tuning those weights to produce different kinds of behavior. So we can produce more conservative behavior that prioritizes accuracy, as well as more aggressive shooting behaviors that by ramping up the weight on the expected velocity of the puck. So you can see the different types of behaviors here, so generated for the same puck states. So you can see that the aggressive model tends to do more like side shots, because that way it can basically leverage the kinematic structure of the robot to generate a higher contact velocity. And for any kind of optimal controller formulated in this way, we can essentially generate a data set of state action pairs, so positives and negatives, and use a contrastive loss to train an implicit energy-based behavior cloning model, which essentially learns these cost landscapes or energy landscapes that we can query online to recover our optimal contact plans. And the nice thing about this is that we can use a derivative-free sampling concurrently with the planning loop. So as we actually approach the puck, we refine our action by reducing the variance in sampling and recentering our sampling of the action. And here you can see some behaviors generated online at 50 hertz. So we compare our agents to a model-based and a reinforcement learning-based baseline in simulation and in the real world. And we were able to achieve quite a high accuracy and high puck speed using our method. And also our method transferred quite well to the real world because we relied heavily on the priors that we had of the game. And we also had a nicely parameterized simulation environment that was parameterized on the real system. So this resulted in quite a nice kind of competitive air hockey agent. And I think as future work, it would be interesting to see how this method itself would scale to higher dimensional state action spaces in more complex manipulation tasks. So thank you for your attention. I'll be at poster panel 43, so I'd be happy to chat if you are interested in this work.
Thank you very much. Do we have any questions in the hall? We have a question here in the bottom right. Yeah, thank you.
So has your model, I really like the impact dynamics.
Oh, sorry, okay.
Has your model considered spin yet, or are you looking at straight on shots?
We didn't consider spin. We basically, so since we made our model like stochastic, that basically accounted for the modeling error that we introduced by taking a simple linear model that doesn't take spin into account. So, and you can actually see nicely like in actually how spin affects kind of the trajectory. I don't know if you remember like the photo that I showed, but basically it induces quite a high amount of uncertainty into our model when the puck reflects off the wall, for example, because of the spin precisely. So,
excellent. Thank you.
Thanks.
All right, let's thank the speaker. All right, next up we have Pratik Kunapuli presenting Leveling the Playing Field, carefully comparing classical and learned controllers for quadrotor trajectory tracking.
Hi everyone, I'm here to talk about comparing controllers for quadrotor trajectory tracking. Recently, we've seen many advances in learning-based control for these quadrotor systems, including autonomous racing, disturbance rejection, and even training new policies within minutes. And a common claim from many of these approaches is that learning-based controllers outperform standard baselines for quadrotor trajectory tracking. In order to evaluate this claim, we need to actually compare between learning-based methods and these classical controllers. And we want to investigate the candidate policies from these both classes of controllers, which are reinforcement learning and geometric control. But what we find in recent literature is that this comparison is actually much more challenging. In many classical controller comparisons, they can use the geometric controller but omit reinforcement learning comparisons. And in many learning-based approaches, they omit the geometric controller or include a suboptimal implementation of the geometric controller. In our work, we want to level the playing field and carefully compare across these two very different controller classes. During the literature review, we actually identified different types of asymmetries that occur between comparing these very different controller types. The first is in optimization objective. Reinforcement learning naturally uses a task-aligned reward function, while geometric control is often qualitatively hand-tuned. Reinforcement learning is also generally trained in simulation, getting access to diverse trajectories, while geometric control is often tuned using quasi-static motions, leading to an asymmetry in task data. And finally, reinforcement learning often gets access to a horizon of future waypoints, but this trajectory information sometimes gets ignored or replaced by PID in geometric control implementations, leading to an asymmetry in trajectory information. In order to fairly compare across these two controllers, we need to optimize on the same reward function under the same tasks and allow equal access to the feed-forward information. Having leveled the playing field, we train these policies in simulation on two tasks. The first is trajectory tracking, and the second is hovering for quadrotors. And we investigate the impact of these asymmetries. In terms of optimization, we find that tuning the geometric controller using Bayesian optimization improves performance, and reinforcement learning naturally receives this benefit from the reward signal itself. In terms of task data, we find that both controllers receive benefit by aligning the task data to the evaluation task. This means that training on trajectory data is useful for evaluating on trajectories, and this is also true for hovering. In terms of the trajectory information, we find that both controllers improve significantly when we include the right types of trajectory information for the controllers themselves. And interestingly, we also find that simply leveraging PID does not make up for the suboptimality. After we've compared the best of these controllers, what we find is that reinforcement learning and geometric control performance is actually very close when we hold all of these asymmetries equal and compare them on a level playing field. Looking closely at the best-in-class methods, we can see that for quadrature trajectory tracking, the performance is extremely similar. And this is true for the achieved reward and metrics such as RMSE. We also find that this extends to a more complicated aerial system, like the aerial manipulator, which is a quadrature with an attached end effector. Digging deeply into this aerial manipulator, we actually find that it's able to recover from perturbation and drop the error of the end effector tracking faster than what the geometric controller is able to do, leading us to believe that RL has better transient performance while the geometric controller has better steady state performance. And this is particularly useful for tasks that require a high level of agility, like this simulated ball catching example here. And we see that the reinforcement learning controller is able to achieve a higher success rate for this task than the geometric controller. In conclusion, in this work, we've identified and corrected key asymmetries in comparing reinforcement learning and geometric controllers, including asymmetries in optimization, data access, and the feed-forward information. We've presented an experimental protocol that is useful for comparing these controllers in a diverse set of tasks, and we found that reinforcement learning and geometric controller performance is much closer than previously imagined. And specifically, we find that for complex aerial systems, reinforcement learning performs better in transient motion, while geometric controller performs better in steady-state tracking. This work was done in collaboration with my colleagues at the University of Pennsylvania, and we also have open sourced all of the code used to evaluate these controllers for future work. Thank you all for listening.
Questions? We have one on the bottom right.
Hi, thanks for the talk. I was wondering, why didn't you compare MPC controllers and also adaptive controller? Because in the last decades, also there have it has been a great advancement in these two fields as well.
Yeah, those controllers are absolutely capable of being compared. This work specifically calls out an experimental protocol to compare any sort of controllers for this. So that future work should absolutely investigate how those controller types are equally capable of comparing against reinforcement learning and geometric control.
Time for one brief more question. One right here in the lower left, or center left.
Hello? Yeah. I was wondering if you consider to compare the performance when you deploy it in a real system, because sim-to-real may be a much higher issue for the reinforcement learning policy than the geometric controller.
Yeah, absolutely. The paper goes into this in more detail, but we do actually consider some of those sim-to-real considerations like domain randomization and more accurate model dynamics. And we find that the conclusion of both controllers actually holds fairly true, that the performance is actually very similar under a normal amount of sim-to-real gap.
Thank you very much. Thank the speaker again. So the next talk will be given by Ying Wu, and it is on a generic continuous multi-joint spinal robotic system for agile and accurate behaviors with GNN-MPC method.
Good afternoon. I'm Ying Wu, a PhD student from Sun Yat-sen University. I'm thrilled to present our research on the generic continuous multi-joint spinal robotics system here. Biological spine inspire remarkable motions, cat mid-air twists, and human-level flexibility. Rigid spinal robots lack such agility. Our solution, a biomimetic, replicates neutral representation. enabling advanced controls. And we designed the SGB SMMS. This design offers flexibility, strength, and scalability. Its spine mechanism with serial connected two-dove spherical gear joints around 3D omnidirectional bendings, and the driving modules using a bevel gear differential distribute torque for the precise multi-dove motions with only 2 motors. In addition, the mechanism design shows that a single spinal joint's rotation around one axis, and adding more driving modules increase strength, and 2 connecting joints can rotate and bending in multiple axes, which highlights the design of the design adaptability. As for the control, we designed a GNN MPC-based control system, which uses an adaptive nonlinear MPC to choose suitable dynamic construct for the spinal system according to the environmental and tasks, ensuring the greatest and scalability. Where the GNN quickly learns the link between the dynamics parameter and spinal joints with a little data for easy adaptation to various robots. We conducted a variety of experiments to validate the system efficiency, including basic and advanced ones. The first basic experiment was the spinal accuracy and load test, where a 1.2 kilogram load, the end joint tracked a circular trajectory with an error of less than 0.004 meters, showing great performance. And the second basic experiment was about the flexibility of the dual SGB SMMS, that focusing on its rotation around different axes, including X, Y, and Z. Next, we will introduce the advanced experiments, which simulate the aerial flipping control of the foreign cat under different conditions. In the first scenario, the single SGB SMMS imitates the aerial flip of a foreign cat. And the second scenario presents the SGB SMMS robot's rotation ability around different axes validated by video 1 and video 2, and the flipping robustness under varied situations validated by the video 3. Finally, let's look at this comparative experimental video. It picks up our GNN MPC control algorithm against Jeffries and MPC. Multiple experiments prove that our GNN MPC algorithm effectively raises the robot's flipping success rate. And that's all. Thank you.
Thank you very much. It's time for one question, if we have a question on the floor. No. All right, well, maybe I'll just ask a question then. So you're dealing with stochastic uncertainty. You're trying to estimate the Fisher information. How do you deal with temporal uncertainty of the contacts when a contact occurs? Do you have any information on that, or do you assume you know that exactly?
Sorry, I can't quite get your question. Can you explain once?
So maybe I'll tell you what, because we're out the back after the same, maybe I'll ask the question when we've got a little bit of time to answer it, and then we'll go on to the next speaker, if that's okay. Okay, it's okay. Thank you very much. So we thank the speaker.
All right. Next up, we have Hrishikesh Satyanarayan presenting behavior synthesis via contact-aware Fisher information maximization.
Hello, everyone. I'm here to present my work on contact-aware active learning. My name is Rishi, and I'm a second-year student in Ian Abraham's lab. So contact dynamics are commonly found and across a variety of robot applications, from locomotion tasks where a robot interacts with the ground, manipulation tasks where the robot interacts with the objects around them. So contact interactions are often required or inevitable to perform tasks. But can we use these contexts to improve robot learning? So we pose contact dynamics as an information medium to help robots learn about their environment. So other works introduce a planar block learning problem where a block interacts with a flat ground, and those contact interactions are used to estimate inertial or geometric parameters. So with structured physics models, we can estimate parameters given data measured from sensors. The paper mentions that identification is only effective if external forces are informative enough. But what does that even mean? How do we measure informative contact data for parameter learning? Information-rich contact data in this paper is not precisely defined. So how information-rich do we need to be in order to identify precisely? And how can we more rigorously quantify the information in contact? Can we take advantage of this information quantification in contact? So in this work, we quantifiably measure the information richness in contact and optimize robot interactions to accelerate the parameter learning process. So let's take a step back and figure out how we estimate parameters through contact. So the goal is I have some data set to deal with my sensor measurements and control sequence, estimate my physics parameters data. So what we do is we incorporate physics and contact conditioning in a conventional max a posteriori likelihood problem by lifting the contact force variable as a decision variable. So in doing so, explicitly reasons over the contact modes during estimation. So here we have our contact-aware maximum a posteriori likelihood problem, where we want to estimate these parameters given some data and control inputs, where tau is our state contact trajectory, and we pose the problem to physics. So you can see all the non-smoothness and non-differentiability of contact is all physically feasible constraints. So this makes the problem really tractable, and it prevents us from using anything like saltation matrices. So how can we optimize for information-rich contact then? So let L be the Lagrangian of the parameter estimation problem discussed earlier. And if we approximate L via a Taylor expansion to the second order, we see that a Hessian term pops up. And that Hessian term actually is related to the Fisher information. Fisher information quantifies information richness in a data set. It offers a lower bound on parameter uncertainty, and it measures how sensitive my sensor measurements are with respect to parameters. So by maximizing overall state contact trajectory over this measure improves the information gain of the data set, thus improving parameter estimation precision. So we construct a contact-aware Fisher information measure to quantify and improve data quality for learning. So given a prior with some variance, we send it over with our contact-aware Fisher information maximization controller that climbs over that information landscape. And in doing so, we use that data to estimate parameters that thus converges on parameter uncertainty in the posterior. So we perform information maximization with explicit contact excitations via the contact-aware Fisher information measure. So we perform our approach on a variety of contact-based learning problems to estimate object mass, object material properties, object shape, and the friction coefficient between a wall and the end effector. And we see that the resulting emergent behaviors generalize across a variety of contact-based learning problems. So our information-rich contact excitations actually improve parameter learning. We compare our approach to a baseline that reasons over the contact modes naively, and we can see that by seeking information-rich contacts, we find that we converge on parameter uncertainty over less trials. So our proposed contact-aware Fisher information maximization controller yields interesting and odd human-like tactile behaviors. When estimating mass, we heft the object. To estimate material properties, we pinch. Shape, we contour. And friction coefficient, we rub. So in summary, we present a method that exploits the structure of contact to search for information-rich contacts that improves learning parameters. We show that the structure of contact can provide a medium to transmit information about the characterization of objects or the environment. And the maximization over the contact-aware Fisher information measure yields emergent and optimal learning behaviors. For code and Python examples, please feel free to check out our code or in our website and our paper. Thank you.
Questions? Maybe I'll ask one then. I'm really curious, have you thought about how to fuse maybe multimodal data? For example, RGB information gives me a lot of hints about maybe an object's properties or materials, and how could you maybe use that to inform your prior and change the interaction strategy?
Yeah, so this is actually something that we're working on in future work, where how can we use data-driven models using vision to be able to find somewhat of a coarse prior and then improve that prior using physical interaction. So if we have somewhat of an idea of what our shape is, or somewhat of an idea of some sort of physical object property that we have, we can use contact interaction or contact exploration to be able to refine that prior given vision.
Okay. Thank you very much.
Thank you.
Thank the speaker. So the next paper will be presented by Yan-Hao Yang, and it's on geometric gate optimization for Keynote dynamic systems using a Lie group integrator. Thank you.
Hello, I'm Yan-Hao from Oregon State. I'm here to present geometric gate optimization for Keynote dynamic systems. Keynote dynamic locomotion is characterized by the coupling of kinematic effects that describe how shape changes lead to position changes. Yep, here you are. So Keynote dynamic locomotion is characterized by the coupling of kinematic effects that describe how shape changes lead to position changes, and the dynamic effects that typically appear as the ability to guide. Together, these effects enable agile maneuver with minimum degrees of freedom in robotics. Keynote dynamic systems are common in the real world. For example, in wheel systems like roller racer or snakeboard, motion is initiated through internal shape changes and the non-slip constraints on the wheels. And gliding is achieved by redirecting the momentum. Another example is swimming. Dolphins accelerate by deforming their bodies under anisotropic hydrodynamics, and then glide by redirecting the accumulated momentum. Achieving agile maneuvers in Keynote dynamic systems requires effective motion planning. While standard optimal control techniques can be applied, the numerical discretization might violate dynamic constraints, and their full horizon trajectory planning may accumulate errors over time and require replanning for each new goal. In this work, we explore symmetry and group structure preserving discretization for gate optimization, and the gate-based motion planning to reduce expensive full horizon recomputation. Prior work has taken initial steps by proposing geometric gate optimization based on constraint curvatures, and then compose gates into motion plans. However, this line of work has primarily focused on principally kinematic systems, and the planner does not consider the gate transitions. We generalize this framework to Keynote dynamic systems and consider transitions between gates under time-varying dynamics. In this work, we study Keynote dynamic systems from the real world, including wheel systems such as roller racer and snakeboard, and also a three-link swimmer at the intermediate Reynolds number. Our key contribution is a gate optimization method for Keynote dynamic systems using Lie group integrators, where the discretization for gradient computation preserves the structure and group symmetry. Based on this, we generate both the locomotion and transition gates and use them to construct the full motion plans. We first evaluate our method on a roller racer robot that consists of passive wheels and an edge-aided joint connecting the front and rear carts. This simulation illustrates the full motion plan of the roller racer. Starting from the rest, the robot first accelerates. Once enough momentum is accumulated, it transitions to a steady-state gate, and then perform turns in different directions, and finally ends at a nominal configuration. Since the robot only has one actuator, the resulting gates ensemble traveling waves with different amplitude and asymmetric rising and falling edges. These two frames shows the synchronized view of the two cameras in the experiment. We load the motion plan to the robot and ran it in open loop, with the actuator just checking the desired shape trajectory. Despite the accumulated errors in the open loop control, the robot successfully reproduced the planned behaviors, and the experiment trajectories also demonstrate the good performance of the feed-forward motion planning. We further evaluate our method on the snakeboard robot. The gates resemble circular cycles with varying radii and local deformations. Unlike the roller racer, the snakeboard decoupled inertial rearrangement and the wheel constraint direction with separate control of the rotor and chuck joints. This allows it to effectively utilize the constraint forces for acceleration and enable compliant control of the rotor in steady state. Finally, we test our approach on a three-link swimmer operating at intermediate Reynolds number. Like the snakeboard, it starts with a larger radius gate to accelerate efficiently, then transition to a streamline to minimize jack. The gate exhibits increasing wave amplitude from the head to tail, reflecting the biological strategy seen in fish. Unlike the wheel system that can turn using constraint forces, the swimmer must bend their body and use the jack force to turn. Due to the torque limits, large angle turns requires multiple gate cycles to execute. In summary, we propose the gate optimization framework for kinodynamic systems that leverage Lie group integrators and support gate-based motion planning. We demonstrate its effectiveness on 3 representative systems. Our future work will focus on incorporating closed-loop control, exploring variational integrators for the momentum evolution, and improving the model fidelity. Thank you.
Thank you. Questions? You have anybody? So if we don't have from the floor, then your, the basic idea is that you're storing energy in a dynamic state, right? So you're building up energy and then you're using that to do some maneuvers. So do you actually have categories of maneuvers, some maneuvers that are energy absorbing and some maneuvers that are energy generating? And is that the way to think about it?
Yeah, so the main energy loss is due to for the roller racer robots due to the viscous friction on the wheels, like when they're gliding. And the steering motion basically pumping energy into the system as long as you do enough, you have that asymmetric rising and falling edges, like different paces for the steering direction. You can use the momentum, the inertial rearrangement and the wheel non-slip constraint to pumping energy into the system. And that's why we can do with just one actuator to do like these agile maneuvers.
Okay, no, that makes sense. Thank you very much.
Next up, we have Song-Li Teng. Oh, let's thank the speaker one more time. Thank you. Next up, we have Song-Li Teng presenting Riemannian direct trajectory optimization of rigid bodies on matrix Lie groups.
Hello, everyone. This is Song-Li from Michigan Robotics. Today, it is my great honor to present our work at Robotics Science and System. A wide range of robotic platforms includes electric robots, manipulators, aerial and ground vehicles are composed of rigid bodies. To optimize the rigid body motions, we can apply this direct trajectory optimizations that minimize this cost and subject to the dynamical constraints induced from rigid body motions. However, we know that the rigid body motions are evolving on some complicated non-Euclidean space that has rich geometric and topological structures that is inherently different from the vector space. Thus, we know that it's possible to optimize rotational motions in some vector space, but generally we will have singularities or discontinuities if we do not deal with them properly. The differential geometry establishes that any effort that tries to embed the 3D rotations into vector space, 3D vector space will have singularities. Such example includes the Euler angles, Rodriguez formula, or this modified quaternions that has a root square. To solve such problems, we can directly perform the optimization on manifolds such that we directly manipulate the rotation matrix. But in general, doing so will be more challenging than conventional numerical optimizations. The existing unmanifold optimization has been widely applied in robot perception for unconstrained supervised learning, but we know that all these problems do not consider constraints. In this work, to meet this gap, we proposed to bridge the geometric mechanics on matrix Lie group and constraint optimization to design singularity-free and dynamically feasible trajectories for rigid bodies. The first step toward this goal is to discretize the rigid body motions. For the kinematic part in this work, we separately consider the pose and pose change both on matrix Lie group without continuous time variables. And after that, we can leverage the Lie group variational integrators to derive the equation of motions for the dynamics part, which is the discrete variant of the variational principles. After that, we can show that all the equation of motions will be on matrix that is suitable for Riemannian optimizations. In Riemannian optimizations, we are generally doing the gradient descent in the tangent space and map it back to the manifold via these retractions. To deal with the constraints as we see in the rigid body motions, we consider the Riemannian variant of the classical interior point method that solve a sequence of log barrel problems with taking homotopy parameters. In this work, we consider the specific line search scheme as we do in the IP-opt algorithms. To find the search directions, we need to provide the first and second order Riemannian derivatives to perform the Newton steps. To differentiate the rigid body dynamics, in this work we consider the second order retractions on the manifold. Frankly speaking, the tidal expansion along the curve to extract the gradients and the Hessians. For the matrix Lie group, we can conveniently doing so by induce the constant velocity curve using the bi-invariant metric. Such method can be done by the BCH formulas. To verify the method, we tested the algorithm on joint landing problems where with baseline we choose is a non-singular parameterizations using the quaternions with explicit motion constraints to avoid the singularities. In this work, we consider the cost function as the trace norm to indicate the pulse change and consider the joint dynamics with 4 inputs. The numerical results suggest that the proposed method exhibits a second-order convergence, even with very trivial straight-line neutralization that interpolate between the initial pulse and the goal pulse. When it comes to the baseline, we find that the trivial straight neutralization fails for all the cases because of the explicit manifold constraints. But when it comes to the expert neutralization by global optimizations, it still has low convergence rate and sensitive to the perturbations. Finally, we show that the algorithm is capable of handling general nonlinear inequality constraints for collision avoidance. To conclude, the proposed algorithm can handle general dynamics for rigid bodies and is efficient and free of singularities. And finally, I would like to thank all the authors that make this research possible, and I'm happy to answer any questions.
Thank you very much. Questions? I know my, yep, you got one? Ah, good. In the lower back, yeah.
Have you considered compare this with, for example, Riemannian augmented Lagrangian or Riemannian SQP?
No, this is a local solver, so it's not for SDP. So
no, Riemannian SQP or Riemannian augmented Lagrangian-based methods.
Yeah, I didn't try, but I think the main reason for that is I want to try a real Newton's method, so using explicit second-order differentiation. So I didn't try the quasi-Newton method, but I can do this in the future.
Okay, thank you.
All right, for the sake of time, let's take all other discussions offline. Let's thank the speaker one more time.
Okay, thanks.
Thank you. So it's my pleasure to introduce the last speaker in this session, Bohao Zhang, I believe, and it will be provably safe online system identification. Can I just ask at the end of this session that just let the speaker finish before you move at all, and there will be another session after this one, so just be polite to the speaker, don't leave during the questions.
Hi, thank you. Hi, my name is Bohao, and I'm going to present my work, Provably Safe Online System Identification. This work focuses on the problem of safely manipulating objects with unknown properties. Suppose a robot needs to pick up a set of dumbbells and stack them vertically on a platform in reverse order of their weights while avoiding surrounding obstacles. Importantly, the robot does not know the initial properties of the dumbbells. So this task introduces 2 fundamental challenges. First is safety. The robot needs to avoid obstacles, and notably, the heaviest dumbbell is close to the physical limit of the robot. Second is precision. The robot needs to, this requires very low tracking error from the controller, and there exist several research gaps. So the first is the gap between safe planning and safe control. The controller may not perfectly track the planned trajectory due to model uncertainties. Second is the need for tight parameter bounds, since large model uncertainties usually bring overly conservative behavior. Last is safety during system verification. So in other words, how can we guarantee safety without knowing object parameters in advance? Our proposed solution consists of two components. The first component is a trajectory planner that generates an exciting trajectory in real time, which can be tracked by the robot in a provably safe manner. This planner formulates an application problem that explicitly accounts for collision avoidance, joint, and torque limits to guarantee safety. As the robot follows this planned trajectory, it collects data, which are then passed to the second component, a robust online algorithm for identifying the payload parameters. This algorithm not only produces an accurate estimate of the payload parameters, but also computes an interval bound that is guaranteed to contain the true values if the sensor noise is bounded. So the estimated parameters and their bounds are used to update both the controller and planner, allowing the system to safely track more exciting trajectories. This process is repeated iteratively until the parameter estimates converge, and our entire implementation is available online. So our key idea can be summarized as follows. We show that system unification can be written down as a convex application problem. So here, theta represents the unaffected inertial parameters, including mass, center of mass, and inertia. W is the regressor matrix, which is computed from the data from joint encoders, such as joint positions and joint velocities. U is the torque vector, which is computed from the torque data from torque sensors. So the ground truth data corresponds to a specific optimal solution of this problem, which should be the ground truth parameters of the n effector. However, in practice, the data collected by the robot is affected by the sensor noise. As a result, the corresponding optimal solution is not the true parameters, but a perturbed version of it. It is crucial to understand the relationship between the true parameters and the estimates. So to capture this, we first perform perturbation analysis to derive the derivative of the estimate with respect to the sensor noise. We use this insight in both components. First, in the trajectory planner, we generate exciting trajectories by minimizing the condition number of the regressor matrix, and by doing so, we ensure that the data collected along these trajectories is less sensitive to noise, resulting in more accurate estimates and tighter bounds. And second, during identification, we use this derivative with Taylor interval analysis to compute an interval bound, which is guaranteed to contain the true values as long as the sensor noise stays within a known range. So this video illustrates a complete pipeline of our proposed method. First, the robot picks up the dumbbell, and next it executes our algorithm to follow the stacking trajectories and estimate the payload parameters iteratively. And after that, the robot moves the dumbbell along a predefined trajectory, safely avoiding obstacles, and places it in the target positions. Then the robot repeats the pipeline for the remaining dumbbells. And as you can see, this yellow one is about 8 pounds. So for Keynote arm, you really have to move very carefully. And we can show that for all dumbbells, our method is able to operate safely without collision or exceeding torque limits. We also compare our method with several alternative approaches, and all of these other methods fail when attempting to manipulate the heaviest dumbbell, which is the 8-pound one, while our method succeeds. So thank you. That's the end of my presentation.
Thank you very much. Do you have any questions? Yep, up the bottom right rear.
Hi, this is really cool work. I'm kind of interested about the connection of this to like persistency of excitation. For the W transpose W, that's basically like an observability Gramian, right? Do you have to assume something about the time parameterized version of this? Like, do you need some persistency in that W matrix?
Yes, so we use a similar concept called excitation, but I don't think we're doing persistently because in the planning we're doing receding horizon planning. So I think we're just like trying to find local exciting trajectories because they're just locally minimum solution of this optimization problem. But the concept is similar. Yeah.
Makes sense. So thank you very much. Thank the speaker. That brings this session to an end. So thank you to all of the speakers and thank you to the audience. And I think we'll have a couple of minutes. So if you need to jump up and come back again, then that's fine. And then we'll swap over. There's another session immediately after this one. So get ready for that one as well. Thank you very much.
Okay, welcome to session 13 on mobile manipulation and locomotion. I'm Ram Vasudevan from the University of Michigan.
I'm Xiaorong Wang from UC San Diego. Okay, so we will be starting the session now. So the first paper will be Human to Local Man, Learning Versatile Quadrupedal Manipulation with Human Pre-training. Yaru Liu is going to present.
Hello everyone, I'm Yaru. I'm glad to present Human to Local Man, Learning Versatile Quadrupedal Manipulation with Human Pre-training. In this work, we equip quadrupedal robots with versatile manipulation capabilities. Imagine a robot dog assistant at home that can help you collect toys, organize shoes, scoop cat litter, or even serve a cup of tea. Some of these tasks here were not seen by quadrupeds before. So what makes it possible, and what challenges did we have to tackle along the way? Imitation learning is an effective way to acquire advanced manipulation capabilities for robots. For example, it can achieve long horizon coffee making or kitchen cleaning with tabletop or mobile arms, tea preparation with dexterous hands, and large range object moving with humanoids. However, scaling up imitation learning for quadrupedal manipulation remains challenging. The achieved tasks here are not usually as dexterous and accurate as those by previous robot morphologies. And on the right side is our prior work, a lightweight and human-friendly quadrupedal platform with leg-mounted manipulators. It allowed for a little bit more dexterous and versatile tasks, but it was still tele-operated and quite slow. To achieve effective imitation learning, we typically rely on efficient tele-operation to collect in-domain robot data. To scale it up, many approaches leverage data directly from humans. They usually require kinematically similar systems to the robot or specialized end effectors at the end of the human operator. However, the substantial embodiment gap between quadrupeds and humans brings two challenges. The first, how to collect quadrupedal robot data via human teleoperation in a natural and intuitive way, and to scale up learning how to collect, structure, and utilize human data to train and help quadrupedal manipulation policies. To this end, we introduced Human to Local Man, a system for scalable and versatile quadrupedal manipulation learning. First, we develop a teleoperation and data collection system that efficiently captures both human and robot data and unify them in a shared space to construct this data set. And we propose a modularized cross-embodiment transformer architecture that is pre-trained on the human data and fine-tuned on the robot data to learn the quadrupedal manipulation policy. For data collection, we define a unified frame for humans and different local man embodiments, which is attached to the rigid body, where the main camera is mounted, enabling motion alignment across embodiments. We utilize Apple Vision Pro to capture human motions and map them to the robot, specifically head 60 poses to torso 60 poses, wrist poses to end effector poses, and hand poses to gripper actions. This is an overview of how we collect and unify human and robot data. We use the unimanual shoe organization task as an example. To utilize cross-embodiment data for training, we employ a transformer encoder-decoder architecture where the trunk is shared by all embodiments. We use the embodiment-specific tokenizers and detokenizers, which are modularized to utilize modalities and structure of our collect data. And these modalities usually maintain unique distributions associated with embodiment or morphology. Our train policy can achieve versatile manipulation tasks with limited in-domain robot data. For example, unimanual and bimanual toy collection with toys of different colors and shapes, unimanual and bimanual shoe organization that might require good coordination of whole body motions and several non-prehensile manipulation skills. We also consider more challenging and longer horizon tasks that require task use and higher operation accuracy, like cat litter scooping and bimanual pouring. And from quantitative results, we find that human data pre-training can improve models' generalizability and robustness, and the model design can facilitate positive transfer from the human to the robot. We bring the robot here, so welcome to our poster if you're interested.
Okay, thank you. Any questions from the audience? Yes?
Yeah, so great work. I think it's interesting to see the robot dog acting like a human. So I want to ask the degree of freedom. It looks to me like the robot leg doesn't have enough degree of freedom. So how did you address that?
You mean like the robot and the human has the different degrees of freedoms?
Like the robot dog, right? You are using a robot dog, so...
Yeah, so basically here we, during data collection and teleoperation, we control the safety poses of the torso and also both end effectors of the robot and also its gripper actions. So basically 20 degrees of freedoms. And we have an independent low-level whole body controller to track these safety poses. Yeah.
Okay, gotcha.
Okay.
We can have another question. There.
Your system being generalized to hexapod or maybe more complicated systems?
You mean what kind of systems?
Could your system, your method, be generalized to more complicated system like hexapod or with 5 legs, for example?
5 legs?
5 legs.
Oh, like other morphologies or embodiments?
Yes.
Yeah, that's a good question. So currently, we try to generalize our system to support X-arm or G1 human robots. But currently we haven't. We only tested our method on 2 embodiments of the local man robot, which is the standing one and also the unimanual one. Yeah.
Great. Let's thank the speaker again.
Thank you.
Our next talk is on gain tuning is not what you need, reward gain adaptation for constrained locomotion learning. This is going to be presented by Articha Srichunewang.
Hi everyone. Today I'm going to talk about quadruped locomotion learning and how we can train a robot in the real world from scratch without letting it fall. First, I'm sure that all of you have seen what this kind of robot can do. They can run, climb, jump, and do crazy moves as you can see here. But you know what? These amazing skills require a huge amount of training data to be stable. And this is the reason why we need to train them in simulation before freezing the trained policy and using them on real robots. Well, I don't want to do that. Instead, I want to train my robot using their physical form so that they can continue improving their performance. But the question is, can we really do that, even on simple flat ground? Interestingly, 2 years ago at this conference, this work on the left showed that training a quadruped robot in the real world is actually possible. This is super impressive, but if you look closely, you can see that robot falls during learning, and it falls many times. And this is exactly the gap that I want to fill. So in this work, I create a technique to train my quadruped robot, a big one on the right. In the real world, without simulation, without falls, and without extensive reward tuning. To do this, I use this framework that has 2 key components: sample-efficient reinforcement learning in gray, and reward-oriented gain via embodied regulation, or ROGER, in blue. In the first part, I use things from my previous work, a central pattern generator-based neural control for motor command generation, and parameters-based exploration learning algorithm to optimize those commands. In order to avoid gain selection and ensure safe learning, I recompute all these reward weighting gains online using Roger. At each time step, Roger used this fixed manifold to compute new reward weighting gains. It requires only constraint threshold tau, which represents the maximum physical quantities that the robot should not exceed. For example, first, when the bot is far from the threshold, it uses low penalty gains to prioritize the main objective or the main reward. Later, as the penalty increases, it emphasizes more on stabilities. This is done by lowering the reward gain and increasing the penalty gains. Finally, at the constraint boundaries, the robot uses only the penalty gains, doing whatever it takes to return to safe states. As a result, Roger can adjust each reward weighting gains throughout different learning episodes and throughout different gate phases using repeated interaction with the environment. These strategies have been proven stable using Lyapunov stability analysis, and it also guarantees the increase of the main objective. Compared with state-of-the-art constraint reinforcement learning techniques, Roger is among the 4 techniques that has no more than 5 violations in 50,000 time steps collected throughout different learning trials. Moreover, Roger achieved a significantly higher reward compared to the other, as you can see on the left. Not only that, I can use Roger for other conditions, not just flat terrain and quadruped robots. For example, I can use Roger to achieve all these results without the need to tune any single reward weighting gains. And here's my final message. If you are tired from finding the right reward gains just to make your robot do what you want, stop wasting any more time and give Roger a try. Thank you.
Questions? Oh, I see one on the floor here in the back.
Nice work. Do you think your work can be generalized to more agile or like more extreme tasks?
So basically, from the proof, we have several assumptions, and the assumptions are that our system or our robot should not change like too much. So as long as your condition just follow this, we can guarantee that the robot won't fall or won't violate the constraint. But even so, if your robot or system does not follow this assumption, from what I have tested, we can still use it, and we don't have to tune any reward weighting gains, and we can achieve some kind of improve in performance. And hope that answers your question.
Okay, why don't we thank the speaker again and go into the next talk?
The next talk will be SATER, Safe and Adapted Talk-Based Locomotion Policies Inspired by Animal Learning, presented by Guillaume.
Okay, great. Hi everybody, my name is Guillaume Sartorelli. Today I'll be presenting our work SATA, Safe and Adaptive Talk-Based Locomotion Policies Inspired by Animal Learning, on behalf of my students Pedro and Hongyi, who couldn't be here because of visa issues, as well as our collaborators from EPFL and ETH Zurich. Nowadays, most current learning-based control policies for legged robots output joint positions, which must then be converted into joint talks by a low-level controller. However, this layered control structure solely focuses on maintaining the robot's shape. When facing disturbances or environmental changes, like in these videos from SOTA approaches, the robot can be seen reacting with stiff, abrupt corrections or even flailing, forcing it back to its ideal shape instead of adapting it by reasoning about its interaction with the environment. This shape-first bias compromises the naturalness of motion and weakens the policy's ability to adapt to new or unexpected situations. Instead, our work aims to let the robot reason about its current dynamic state and terrain interactions to directly output talk commands. thereby producing more adaptive behaviors. However, talk control requires higher frequency and inherently results in a much more complex state action space. This makes training dramatically more difficult, especially during early stage exploration. To address these challenges, SATA's novelty lies in two key mechanisms guided by fundamental questions about animal locomotion and early skill acquisition. First, what are some of the main biomechanical mechanisms behind blind animal locomotion? And second, how do animal youngs acquire and refine locomotion skills? By modeling key biological control mechanisms and learning processes, SATA incorporates a range of biologically inspired innovations, allowing us to learn robust talk policies in simulation and deploy them to the real world with no sim-to-real gap. Let's start with our biomechanical model. In biological systems, movement originates in the brain, is modulated by motor neurons, and finally executed via muscle contractions producing joint torque. Inspired by this, we integrate two biomechanical modules into our policy. Activation signals that simulate motor neuron activity to scale and smooth out raw policy output to improve temporal stability of torque commands, and a muscle model that enforces torque limits based on biomechanical principles, preventing unsafe output and avoiding overexertion. These modules are essentially inactive when outputs are reasonable and mainly intervene when abnormal actions arise, acting like biological safety regulators. Next, addressing the question of how animals learn to walk, we note that many quadrupeds acquire basic locomotion skills shortly after birth, during a phase of rapid neuromuscular development characterized by neuron myelination and rapid muscle growth. Motivated by this observation, we introduce a growth mechanism into our training to emulate the progressive release of control capacity seen during early animal development. In SATA, the robot begins its training with constrained torque and low control frequency, creating a low-risk, simplified action space for learning fundamental behaviors. These constraints are then gradually relaxed, allowing the stable learning of a policy that can make full use of the robot's capabilities. This phased approach mirrors biological development and improves training stability, safety, and efficiency by scaffolding the acquisition of locomotion skills from crawling all the way to walking, akin to a form of emergent curriculum learning. You can observe the compliance of our Learn policy in the top left video as we safely lift the robot's legs off the ground without any overreaction. We also demonstrate its robustness through coordinated kicks. We further tested our policy outdoors under multiple disturbances, such as stomping, kicking, and blocking the robot as it walks through a lawn, and tested its stability through a 1.2-kilometer trek around campus over multiple terrains. Moreover, the compliance of our Learn policy also allows the robot to naturally traverse a low-rise passage without any exteroception nor additional training. Despite these benefits, SATA still has a few limitations, such as potentially overly compliant behavior that may reduce performance in load-bearing tasks. That being said, we believe that it offers a strong foundation for tackling key challenges in legged and even general articulated robotics. Thank you for your attention. Come see us at Poster 15, and I'll be happy to take any questions.
Any questions? This one there.
About the, I maybe misheard, but you said that there was no additional training.
Yes.
For when we're scrolling.
Yes. So it's done only by mechanical compliance. When we're telling the robot to move forward at a specific velocity it's trying to track. And by contacting the environment, it feels a force and just complies to it, which is how it goes through this passageway.
Right, but maybe I arrived late. You train them for pressure on the top?
No.
Ever?
No, nothing.
Okay.
We train it with domain randomization with a lot of external disturbances. So it's seen a form of forces applying on the body during training, but we never trained it for this particular force or this particular environment.
Right. Okay. Yeah, but some kind of pressure, I mean, magic?
Yes, it's seen external forces. Yeah, I mean, we're building for compliance. That's the idea of talk. So yes, it's seen like external forces, and it's learned to adapt to those, yeah, okay, in a safe way.
Cheers.
Okay, let's find the speaker. Thank you.
Our next speaker is Nolan Fay, who's going to be presenting on bridging the sim-to-real gap for athletic loco manipulation.
Hi everyone, I'm Nolan, and I'll be presenting on bridging the sim-to-real gap for athletic loco manipulation. The key question for our project was, how can we transfer behaviors from sim to real that push the limits of the hardware? And what better way to answer that than learning athleticism? So far, quadrupedal manipulation has focused on training whole body controllers to track dense reference motions. These works offer great teleop interfaces, but extending them to athletic tasks would require high-quality athletic references, which aren't readily available for most robot morphologies. And even if they existed, they might not capture the truly optimal or athletic strategies that a policy could discover on its own. Similar to previous works, we took a sim-to-real RL approach and designed several tasks in sim: ball throwing, weightlifting, and sled pulling. Instead of tracking rewards, we use simple task reward functions like throw the ball as far as possible or lift the weight as quickly as possible. Using such simple rewards creates two challenges. The first is reward hacking. RL can exploit physical inaccuracies in the sim to collect more rewards. And there's an example of reward hacking. The second is exploration, where RL can struggle to find the optimal coordinated motions inherent in athleticism. During our initial experiments, we recognized that the largest source of the sim-to-real gap was in the arm's actuators. So to address reward hacking, we introduced the unsupervised actuator net, a framework for learning a corrective actuator model. Crucially, our approach does not rely on torque sensing, which is still uncommon in consumer robots. So it's a simple pipeline. You first collect random rollouts in the real world, and then you can train your actuator net via reinforcement learning to close the sim-to-real gap. So the reward here is to match joint encoder measurements, and the actions are corrective torques. And then you can train a policy in this augmented simulator and finally deploy it. To evaluate the UAN, we measured the sim-to-real gap in real-world performance of arm-only throwing policies trained with UAN in baselines. We compared with the default Isaac sim and other standard methods for overcoming the sim-to-real gap, like domain randomization and fitting joint friction and inertia parameters. The UAN had the smallest sim-to-real gap and the best real-world performance. We also proposed a pre-train then fine-tune approach to guide learning with reference trajectories. In the first stage, the policy learns fundamental motion skills, such as walking around and reaching its arm. In the second phase, we provide the policy with a reference trajectory for the task. Simply tracking the reference leads to mediocre performance, but it does give a strong prior that can help overcome exploration challenges. From there, RL fine-tuning improves the policy's performance. Crucially, we train using task rewards rather than tracking rewards. This allows the policy to discover new skills not shown in the demonstration. So that's the policy before fine-tuning and then after. The key here is to treat the reference as a hint rather than strictly tracking it. We performed ablations of key design decisions and compared the throwing distance, speed, and power consumption of the resulting policies. No fine-tuning is the pre-trained tracking controller with no further training. The no pre-training is learning from scratch, and no end-to-end freezes the tracking controller, but learns a high-level policy that outputs a reference. And our approach achieved the farthest throwing distance. So I have videos. So you can see that the throwing skill coordinates the motion of the arm and legs to throw as far as possible. There's a very small sim-to-real gap. Here, the tracking controller struggles to lift the dumbbell, but the lifting skill can lift it. And then on the sled pull, you can see that the policy learned to extend the arm to minimize the joint torques and pull with the legs. Yeah, if you have any questions, I'd love to see you at the poster, and feel free to scan our QR code to see the website. Thank you.
Any questions? Oh, there's one up here in the front.
Hi, thanks a lot for your presentation. Could you elaborate a bit more how the unsupervised actuator network seems to outperform like a normal actuator network, or what are the reasons why it would be doing this?
Yeah, so the original actuator net was supervised by torque measurements, whereas in our case, our robot didn't have torque sensing. And so we just record the joint encoder measurements. And then we can use reinforcement learning to discover the torques that are needed to match up the encoder measurements in real and sim.
Okay, just a small follow-up. Is it possible to just use the current readings to get torques on these kind of arms?
Yeah, so we actually did that as a baseline, and we found that wasn't as accurate, or it didn't perform as well, maybe because of the effects of the gearbox.
Okay, thank you.
Yep.
Okay, maybe we have time for a very short question. If not, we will thank the speaker. Thank you.
Thanks.
The next talk will be adaptive locomotion on mud through proprioceptive sensing of substrate properties, presented by Shipeng.
Thanks for the introduction. Hi, this is Shipeng Liu from University of Southern California. Today, I'm very excited to share my research about adaptive locomotion on mud through proprioceptive sensing of substrate properties. Muddy substrates exist widely in nature environments, yet its complex composition presents significant locomotion challenges to humans, to machines, and to our robots. So, for our robots to efficiently perform field mission, it is crucial for them to be able to sense, to interpret, and then adapt the locomotion to different muddy terrains. So I think the first question here is really how can our robot sense the environments? Unfortunately, the robotic sensors like vision systems fail to detect the subtle differences between different muddy substrates, which are critical for the locomotion success. Adding extra force sensors can help significantly. However, it is often prone to damage in the field and can add significant integration complexity. So to overcome this limitation, we draw inspiration from biological systems that they can use their body-terrain interaction to feel the softness of the terrains. Specifically, we use direct drive motors, which are quite sensitive to the external forces, such that they can even detect a gentle puff of air from your mouse and then turn the direction. So by using the torque from each motor and applying an inverse Jacobi matrix, and then do some system identification, we can estimate the external forces that act on the flipper plate. And we further validate the accuracy of this approach by attaching variance weights onto it. And it turns out that the sensing capability is quite high. Now, with these external forces, how can we use it to help the robot understand those different mud mixtures? So for the viscoelastic forces that this mud mixtures generates, is often quite complex and hard to model and interpret. Even for a simple trajectory, as the flipper penetrates vertically and then shear horizontally and then extract back, the forces shown on the right is still very complex, and we have to take a closer look at the specific features. So these features include the horizontal force during shear and the penetration force during the vertical force during penetration, as well as the negative necking forces when the flipper is trying to extract out of the terrain surfaces. Based on the resistive force theory, we can derive 3 corresponding terrain coefficients from the force measurement during one gauge cycle, and then we can use these terrain coefficients to predict robot locomotion performances. Then, in order to validate the accuracy of the estimated terrain coefficients, we perform experiments using linear actuator and force sensors to get the ground truth. Specifically, we perform 5 sets of experiments on 5 different mud mixtures with different water content, and this will significantly change the terrain properties of these mud mixtures. And it turns out that the estimated terrain coefficients from our robot actually matches with the ground truth, which indicates the potential of using a robot to sense the terrain properties even during locomotion. So to do that, we extend our robotic flipper into a locomoting robots and have it run through. And you can see as the robot runs through, the estimated turn coefficients can clearly indicate the differences of these three terrains. While from the visual, you can hardly identify it. So now we also provide a demonstration of how to use these sense terrain properties to aid with the locomotion. If there's no adaptation, the robot will force into soft yielding failure or extraction failures. But with adaptation, our controller actively adjusts insertion depths to avoid these two possible failures. And our experimental result shows that it works quite well. Last but not least, I'm currently in my final year, and I'm actively looking for a postdoc position. If you know opportunities and drop your message, I would greatly appreciate it. Thank you for listening.
Questions?
So one of the issues is that this penetration restraints is not enough to support the body weight of your robot. I think, how do you counter the fact that the robot will sink into the mud, like as it moves into more dense area?
Yes. To answer this question, I have decoupled into two parts. The first part is that if the penetration force is not enough, you can always increase the penetration depth to increase the desired force you want to get. And then for the body terrain interactions, you can, if the terrain itself cannot even support your body, you might want to use your flipper to generate enough forces to encounter the body gravities. Yeah.
Okay, there's other questions?
Have you tried different angles?
Yes, that's a great question. Because of these complex force responses, we start from a simple gate or robot gate trajectory, but we are currently working on extend this kind of 1D model into 2D so that we can capture the force responses of trajectories of different angle and different curves. And then hopefully that will generalize or improve the locomotion performance even more. Thank you.
All right, let's find the speaker.
Okay, next up we have Heng Liu, who's going to be speaking about discrete time hybrid automata learning, legged locomotion meets skateboarding.
Hi everyone, I'm Hang from University of Michigan. Is this okay? I'm happy to share our recent work here at discrete time hybrid automata learning. So in model-based method, hybrid dynamics is kind of challenging because it will introduce discrete jump into the state space. So previous work using HCD and automata to solve such problem and achieve stable locomotion. And in learning hybrid dynamics domain is still challenging because although previous work advanced in continuous modeling, but still challenging in scalability in high-dimensional tasks, and also they still rely on trajectory segmentations. Therefore, we introduced our method, DHAL. So our method will start with an automata. It will to decide which mode should be activated, and the sub-module activated would predict the future states. So the main feature we introduced is that our method could identify the mode heuristically, which means we only set up a bound number of our mode, and it could identify mode, and also but the action number would be activated is learned autonomously, and also there's semantic information. And also there's a cool videos from the TrueDog, and we are motivated by it, and we want to consider skateboarding as a very challenging task. So first, achieving locomotion, content-rich locomotion, we interact with objects, still challenging, open problem. And also, we're trying to figure out how to identify mode in such high-dimensional task. From the right pictures, we could learn how humans teach a dog to skateboarding. The main idea is kind of similar with reinforcement learning, just reward the dog step by step. But the question is, how to motivate to use skateboard and generate natural skateboarding skill? Based on energy or fun, that is too vague for the task definition. So from these videos, we could learn that it's based on specific contact reward. So based on this, we also learn from this video and extract 3 key points. So from these 3 key points, we could find that it's still hard to elaborate into IL style. So first, how to make robot with explore with the skateboard and use skateboard. We will terminate it far away from skateboard. And second, we want to encourage it to use more contact with skateboard. More contact, more food, more reward. And a big bonus if we can achieve gliding with outfits on the skateboard. And finally, encourage forward motion. Mitigate the sparsity introduced by the contact reward and also prevent converge to single dominant styles. So we introduced 3 different critics for handle different rewards, like one for move forward and one for gliding, more contacts, and one for symmetrical regularization. So as you can see the videos with red background, without multi-critic, the motion either be violent or other weird or with only one leg, but with multi-critic, it will be much more elegant. And also, there's a question in contact-rich problem, should we expand our action space first, or should the policy first utilize the action base first? So in this task, we find that if we're using Gaussian policy would prefer to increase its violence to increase the exploration. So in that case, it could luckily get some contact points. But the motion would be violent and hard to deploy on the real world. Also, it cannot achieve skateboarding. So we find that it might, because the Gaussian policy will always prefer to reach out to the action space. So we introduced the beta policy, which has bounded variance and action space. And as you could see in these videos, we could achieve smooth skateboarding locomotion, and also it could identify mode which consistent with the human intuition. I personally like this failure and the recovery case. It clearly showed that how our automata using different mode to make it back to the skateboard because it's stuck by a hole on the ground. And our method could also generalize to hard terrain like skateboarding park without any other terrain training. And thank you for listening. Please visit our website for detailed information and stop by our poster. I'm happy to take any questions.
Do you think that the skateboarding robot uses less power / energy compared to a walking robot over the same distance?
That's interesting. Actually, in gliding, you will definitely reduce the energy consumption. But for example, if you want to jump onto the skateboard, you will consume a lot. But in the same time, you will bring more risks because it might fail. So it's a more aerodynamic locomotion. So about energy consumption, I would say is in gliding phase, definitely, but we don't maybe need to be so agile, but it's still an interesting task. Thank you.
There's another question here.
So I saw that your reward looks quite complicated. You probably spent some time designing it. Do you have any thoughts on how to do reward design in a more automated way?
So I would say the reward is about engineering effort, and we need to learn. For example, we learn from these videos how humans teach dog to skateboard, and we also I think the key idea is about contact. We need to know these main ideas how to do that. So in this case, we can design great reward for that. Also, you have to pay a lot of effort to do engineering tuning.
Okay, let's thank the speaker.
Thank you.
The next talk will be Safe Mimic towards safe and autonomous human-to-robot imitation for mobile manipulation.
Hello, it's my pleasure to present Safe Mimic, a method for safe and autonomous human-to-robot imitation for mobile manipulation. Imagine a future where robots are part of our daily lives. Users will want to teach them new tasks by directly showing it to them. How can such end users teach robots new tasks? One option is to teleoperate, but teleoperation is quite time-consuming and requires expertise. A more natural way is to directly show a robot how to perform the task. Prior works have tried to tackle this, but are limited to shorter horizon skill-level tasks. However, learning to perform multi-step mobile manipulation tasks from one video is challenging. This requires understanding the semantic segments of each step and adapting the motions of the human to the robot. Some prior works have focused on adapting the human actions to the robot's embodiment. For instance, in our previous work, Screw Mimic, we developed a method to allow the robot to refine bimanual actions in the real world. However, during the refinement procedure, the robot would often reach unsafe states, forcing me to press the E-stop, and also would require me to reset the environment. For scalable action refinement in the real world, the robot needs to do it safely and autonomously. So how do we get robots to learn from a single human demo of multi-step mobile manipulation safely and autonomously? We introduced Safe Mimic, which consists of 3 modules. The first one is the human video parsing module. It inputs a third-person RGB video of the human performing the task. Using off-the-shelf human body tracker and VLM-based video segmentation, it extracts the semantic goals of the human and its low-level motions. It then translates each segment into robot actions. For instance, here is an example of the extracted segments for the task of filling water in a pot. Direct execution of the extracted low-level motion often fails, so Safe Mimic helps the robot refine the actions in the real world. Safe Mimic samples new actions close to the extracted human motion and checks if it is a safe, using our safety queue functions. Only a safe action shown in green is attempted. But what happens if the robot reaches a state where no safe action is possible? Well, human intervening is an option, but that's quite costly. So we develop a very simple and effective mechanism of backtracking where the robot just simply undoes its actions. In case maximum attempts have been reached, the robot backtracks all the way to the last grasp and tries a new grasp mode. This allows the robot to not only adapt in the continuous action trajectories, but also adapt the grasps. At the core of Safe Mimic are the safety queue functions. We train them in simulation because, well, training them in real world is dangerous because the robot needs to actually experience these unsafe states. The queue value is 1 if the current or the next state is unsafe, and 0 otherwise. For example, placing a pot in the sink is safe until it collides with the sink, then the queue value jumps to 1. To help the robot learn from its real-world refinements, we use a policy memory module. It stores successful grasps and trajectories, applies geometric augmentations, and trains a point-net-based model. Given a point-cloud and task description, it predicts the right action, like predicting a side grasp when placing a can on the shelf, but predicting a top grasp when placing it in the box. We evaluate Safe Mimic on 7 challenging tasks involving multi-step navigation and manipulation, articulated object manipulation, and contact-rich manipulation. Here we show the results of the robots safely and autonomously adapting the motions extracted from the human video in the real world for all the 7 multi-step mobile manipulation tasks. You can see here that the robot utilizes Safe Mimic simulation-trained safety queue functions to only execute safe actions. It also utilizes Safe Mimic's backtracking mechanism whenever it predicts that there's no safe action possible, and this makes the process much more autonomous. Here's how Safe Mimic compares with baselines. The x-axis shows the 7 tasks, and the y-axis shows the success rate over 5 trials. Directly executing the human motions often fails, highlighting the need for exploration. Exploration without safety also fails often, highlighting the role of our queue function. Imitation learning performs worse, suggesting that our noisy sim data is good enough to train the safety queue functions, but not for imitation learning, which requires much cleaner and more data. Baselines struggle in these long multi-step tasks, but they do achieve partial successes. However, Safe Mimic is the only one that achieves success in all tasks. In summary, we present Safe Mimic, which enables safe and autonomous human-to-robot imitation for mobile manipulation. We show that simulation is a viable source for learning safety queue functions and deploying them in real world. And backtracking is a simple yet effective mechanism for autonomous robot exploration. Thank you.
Questions? Yeah.
Thanks a lot for the presentation. What happens if backtracking is not possible?
Yeah, that's a great question. So in this task, in our work right now, we have focused on tasks where it is possible, but we would definitely want to extend and try to predict if backtracking is possible. If not, then I think an alternative would be to learn reverse policies or resetting policies. But yeah, that's a great question. That's kind of one of the limitations. Thanks.
Other questions? Oh, okay.
Thank Thanks for the talk. How similar does the environment have to be in sim, and like, does a human have to show in exactly the same kitchen, or can you transfer to the different environment?
Yeah, that's a great question. So for the first question, we do have some similarities in the simulation, but it's actually, I did not have to do a lot of simulation, real to sim. And it's also because you're trying to learn something which is much more general and simple here, which is just to predict given the state and action, if it's going to be safe or unsafe, rather than learning a policy. And secondly, we do experiment with different environments for the same task. We have like 3 different environments, and Safe Mimic was able to perform in all those environments.
All right, let's thank the speaker.
Okay. Next up, we have Ziqi Zheng, who's presenting on demonstrating DVS, Dynamic Virtual Real Simulation Platform for Mobile Robotic Tasks.
Okay. Hi, everyone. I'm Zheng from Tsinghua University. Today, I'm excited to excuse our work, DVS, a dynamic virtual real simulation platform for robotic multitask. As robots become more capable, we expect them to handle complex tasks in daily environment, such as homes, office, and supermarket. But existing simulators feel short in some settings. Most are built for narrow use case or rely on ideal environments. To push real-world robotics forward, we need simulators that are both realistic and flexible. Some simulators offer high-quality indoor scenes, but they are static. In real world, robots face moving people, changing layout, and unpredictable obstacles. To simulate this, we need dynamic virtual agent and environment that can be changed over time. That way, we can better study how robots behave in real-life situations. Another key challenge is the sim-to-real gap. Many simulators offer little support for feedback from real robots. But if we could connect the simulation with real-world data, we would get much closer to how the real robot actually operates. For this, the simulator needs to support real-time feedback, such as the VR-based human-robot interaction and the communication with the real robot via ROS. So we designed the DVS with 3 main innovations. Firstly, the DVS includes human-like pedestrian and multi-robot types and rich indoor environments, such as gyms, supermarkets, and restaurants. This helps simulate complex and real sceneries. Second, we use the motion capture and the ROS to sync physical robots and their virtual twins in real time. This allowed behavior in simulation and the real world to stay aligned. Based on this setting, tasks can be interversed during the execution and to supervise or correct the robot performance in real time. We test several use cases on our DVS. First, in the pedestrian trajectory prediction, we generate indoor scenes using our dynamic agent model. We generate indoor scenes and then test 3 methods based on different models like in several scenes. As we can see, performance of all models dropped in our indoor scenes compared to the outdoor data sets like ETH. This showing the indoor dynamic features are important for the evolution. In the pick-and-place task, we use motion capture to check object movement and apply them to the virtual assets. The movement of the virtual robot agent sync from the trajectory of the real robot. So the virtual motion reflects physical constraints such as the joint friction. We call this the virtual real fusion data. Using this, we observe better generalization across different objects and scenes. We also test social navigation and other mobile robot tasks on our DVS platform. For full details, please check our paper. No. And there's still some conclusion, yes. To summarize, the DVS bridge the gap between the simulation and the real-world deployment. It supports dynamic environment, real-time robot feedback, and interactive supervision. The DVS enables multi-agent, multi-task, and multi-domain research, helping design more robust and adaptable robotic systems. And we also invite you to see our demo booth around the number 35 and see how we generate pedestrian behavior and simulate navigation and advanced tasks for the simulator. Scan our code to to learn more. Thank you.
Any questions? Oh, there's one back here.
Is this work open source now, or like when is the plan to open source the code?
Okay, a good question. Our platform will be open source very soon, and it's also available for demo in the yard, and you can try our demo after the talk. And maybe we will open our 10th indoor scenes and some model deployment code of our platform.
Thank you.
Yes, very soon. Yes.
There's a question in the bottom here in the back.
Hi, really great work. So how you generate a human motion? Do you use kind of like predefined motion and replay it or any other algorithms? And also second question, in high levels, what's the functionality different with hepatitis 3?
Okay, the first question, we just collect thousands of the indoors human trajectory using the motion capture, and then we use the CNN, the neural network to get the feature of the indoors human's trajectory, and then we can generate it in the indoor scenes, and they keep distance with each other and other things. And can you repeat the second question?
Actually, we may have to pause there because we're at the end of time here, but okay. Maybe you can catch up in the poster session.
You can ask me after the show. Yeah, thank you.
All right, the next talk will be Flying Hand, an effector-centric framework for versatile aerial manipulation, teleoperations, and policy learning, presented by Guanqi.
Hello everyone. I'm Guanqi He from Karenji Mellon University. I will introduce our work, Flying Hand, an effector-centric framework for versatile aerial manipulation, teleoperation, and policy learning. So there are many existing works in aerial manipulation, like interaction, pick and place, insertion, wave rotation, and more. However, each of these work builds a drone and a control pipeline for a single task. And the hardware and software are not shared. So the results are very hard to build upon. And our question is that, can we design one platform and with a unified control stack that can execute many aerial manipulation tasks? So to achieve versatile tasks, we use an effector-centric interface to decouple the high-level policy and low-level control. And users can have different policies, but the output is only the effector reference. And then a whole body control layer handles the effector tracking precisely and send the command to the hardware. Yeah, so from the policy side, the low-level control is totally invisible and decoupled. Here is our framework, so consisting of a high-level policy, a low-level MPC, and hardware. And we start with the MPC part for precise effector tracking. So here is the effector tracking problem. It is formulated as a standard MPC, and the objective is the effector tracking post-cost, and the constraints include the robot dynamics and the drone state and action boundaries. So for robot dynamics, we carefully model the arm kinematics, servo dynamics, and the drone dynamics. But MPC is very sensitive to the model mismatch, so we add the L1 module to estimate the disturbance in real time and compensate it, which is the Tor external here. So the L1 module estimates the disturbance in real time and then send the disturbance to the commands. And we have two L1 modules, one for the arm and one for the base. And we evaluate our control performance on various trajectory tracking tasks. We have two baselines. One is without using the L1 disturbance estimator, and the other one is without using the MPC. So for without using L1 baselines, the controller has a steady state error due to the model mismatch. And without the MPC baseline, it suffers from the phase lag because it does not consider the future trajectory. And we also found that the extra degree of freedom of the arm can actually compensate the base tracking error, because the arm is moving faster. For the left side, you can see that robot base is not tracking exactly the figure 8, but the any factor, the blue line, is tracking more precise. Well, for the right side, we penalize the arm move. So you can see the base is tracking exactly the figure 8, but the any factor is much more jittery. And built on top of the robust MPC, we can easily define the manipulation policy in the any factor Cartesian space. So here we developed 2 high-level modules. One is the teleoperation. The teleoperator directly controls the any factor reference by the gamepad. So the user don't need to control the specific move of the base or the arm. And thanks to the any factor interface, we can easily achieve complex tasks such as light bulb mounting and pick and place. And actually, this is our just second trial, and we succeed. It's very straightforward to use. And the teleoption data can also be used as the expert demonstration for our second system, the imitation learning-based policy. We deploy the action trunking transformers, and with only dozens of real-world demonstrations, our system can achieve complex tasks such as rotating wave or pegging hole. To the best of our knowledge, this is the first imitation learning framework for the arrow manipulation. And so if you like, you can also call it the flying embodied AI system if you want. And yeah, in the end, I will summarize our work with 3 points. So first, we formulate arrow manipulation as a general mobile manipulation and using the any factor centric interface to make it. And the second, we use the whole body MPC to do the precise trajectory tracking and decouple the high-level policy from the low-level control. And third part, we successfully deploy imitation learning arrow manipulation. And I believe this is just the starting point. Our framework is capable to integrate other powerful mobile manipulation methods into arrow manipulation. At the end of this presentation, I hope to convince you that manipulation is not just limited to the tabletop settings. We can also target tasks that far beyond the human reach, such as help us changing a light bulb at high altitude. Yeah, that's all for my presentation, and thank you so much.
Thank you. Questions? Maybe I can ask a question. So, what's you didn't use any tactile feedback for the insertion of the light bulb?
Yeah, we didn't use.
So it's only visual egocentric?
Yeah, we have 2 cameras, and yeah, we use egocentric view to do the control. Yeah.
But the teleoperator is seeing from the first-person view, or?
First-person view.
First-person view.
Because this is a drone cage, so we cannot directly see the drone.
Right.
Yeah, it's pretty dangerous. So a good high-level policy is really necessary to achieve complex tasks in that sense.
Okay.
Yeah.
Other questions? Okay. Then next panel speaker. Okay. Thank you.
All right, this is the end of the session, but Robo Nights, food, drinks, everything are outside, so please have fun.